Hello everyone and welcome to this video on the Kubernetes Full Course by Edureka. Kubernetes is an open source platform designed to automate deploying, scaling and managing containerized applications. Initially developed by Google and now managed by the Cloud Native Computing Foundation, Kubernetes offers powerful features like automated scaling, self-healing, service discovery and load balancing. It structures applications into clusters of nodes and pods, ensuring efficient resource utilization and high availability. Kubernetes has become essential in modern DevOps, enabling seamless and reliable management of complex applications across various environments. With that said, now let's outline today's agenda for this Kubernetes full course. In this course, we will start with an introduction to Kubernetes and its role in container orchestration. We will then cover Kubernetes fundamentals, exploring core concepts such as clusters, nodes, pods, and services. You will learn how to perform a Kubernetes installation on Ubuntu and CentOS. Followed by in-depth look at Kubernetes architecture. We will then compare Kubernetes versus Docker to understand their distinct role and uses. Next, we will cover Kubernetes YAML for writing configuration files. Then we will explore Kubernetes networking, including service, discovery, and load balancing, and discuss Kubernetes deployment strategies. Followed by essential concepts such as controllers, services, ConfigMap, operators, and Statefulset will be discussed in detail. You will also learn how to set up multi-master cluster using Kubeadm and understand Kubernetes storage options. The course will include a segment on Kubernetes Ingress for managing external access to services. We will introduce Helm charts in Kubernetes for application management and JenkinsX CI/CD for Kubernetes for continuous integration and deployment. We will also cover Kubernetes monitoring with Prometheus and Grafana, explore deploying Kubernetes on AWS, and provide insight into Certified Kubernetes Administrator exam. Finally, we will discuss Kubernetes security best practices and review common Kubernetes interview questions to prepare you for the real-world scenarios. But before we begin, please consider subscribing to our YouTube channel and hit the bell icon to stay updated on the latest tech content from Edureka. Also, visit the Edureka website for the Kubernetes Certification Training Course Administrator, the link to which is in the description box below. Now, without any further delay, let's get started with our first topic, that is, what is Kubernetes?
With the ever-changing requirements of modern software development, it is known that Kubernetes is one such system that will fulfill these needs. If you are someone who wants to get started with Kubernetes, you're definitely in the right place. Let us start off by understanding what it really is with the help of a simple example. Imagine you're building a web application. So within this web application, the structure might be monolithic. It might comprise several modules, components, or even layers. But externally, it is a single web application, or you could also say it is a single service. Despite having different modules, the application is built and deployed as one service for all platforms, that is desktop, personal computer, mobile, etc., within a single container that is a virtual machine. Let us assume the web application grows over time and becomes large. It is now extremely challenging to make changes over the code accurately. Also, the size of the application can slow down the startup time. Moving on, what if you want to add new updates to this web application? You must redeploy the entire application as one. And during this process, in case you stop and try to restart the service, the customers on your website will not be able to access anything for that period of time, which could eventually lead to a potential loss of money. Also, bugs in any one of the components can bring down the entire process. And since all the components of the application are identical, bugs can definitely impact the availability of the application. Now, what if you have a sudden spike in traffic and have to serve 20 times the number of your usual customers? In such a situation, you have to very quickly deploy new servers, which takes a lot of effort. Later, when traffic dies down to a normal level, you now have 20 times the number of your usual servers. It can also be challenging to scale when different modules have conflicting updates or resource requirements. So instead of creating a monolithic application, we can define each component as a separate, loosely coupled service. And then we could virtualize each of these services using a Docker container. Not only can the application start easily, but the services can also be deployed independently. With Docker containers, We can easily scale any number of instances up and down according to the application's requirements, but this is definitely easy to manage when we're dealing with just 3 or 4 containers. Now let's say we had to deal with 1,000 such containers. How do we really keep track of the containers that are healthy and the ones that are not? Orchestrating and managing these containers at the same time can be an extremely tedious task. And this led to the need for container orchestration tools. So this is where Kubernetes comes into the picture. Kubernetes was originally designed by Google and is now maintained by the Cloud Native Computing Foundation. With Kubernetes, you package your website files as containers or pods, which you can run on any instance in your Kubernetes cluster. As you can see, pods are running on nodes, which are physical systems having hardware components that are a part of the Kubernetes cluster. This implies that every service that you create runs on separate containers, and this will allow you to work and manage services independently. Pods can be running on any available node in the cluster, which has enough resources for a pod to work. In simple words, Kubernetes is an open source system for automating deployment, rolling updates, scaling services, and managing containerized applications. Kubernetes works with Amazon EC2, Rackspace, GCP, IBM Cloud, etc. Also, hypergrowth companies like GitHub, Weaveworks, CloudBoost, Walmart are becoming acclimated to building, shipping, and managing containers via Kubernetes. On average, anyone with Kubernetes knowledge can expect to earn between 5 to 6 lakhs per annum in India, whereas they can expect an average salary of $140,000 per annum in USA. As the Fortune 500 are using Kubernetes, the demand for expertise in this field is rapidly increasing, which in turn requires IT professionals who can work on this tool. So what are you waiting for? Begin your journey with Edureka's interactive Kubernetes certification training that is curated to help you learn how to set up your own Kubernetes cluster, configure a networking between pods, and secure the cluster against unauthorized access.
Before we move ahead with our next module, I have a simple question for you guys. And the question is, which company originally developed Kubernetes before it became an open source project? And the options are A. Amazon, B. Microsoft, C. Google, or D. IBM. And if you know the answer, please leave it in the comment section below. We have covered the basics of Kubernetes. Next, we will explore Kubernetes fundamentals to dive deeper into core concepts like cluster, nodes, and pods.
Why do we need Kubernetes? Now, to understand why do we need Kubernetes, let's understand what are the benefits and drawbacks of containers. Now, first of all, containers are good. They are amazingly good, right? Any container for that matter of fact, a Linux container or a Docker container or even a Rocket container, right? They all do one thing. They package your application and isolate it from everything else, right? They isolate the application from the host mainly. And this makes the container fast, reliable, efficient, lightweight, and scalable. Now, hold the thought. Yes, containers are scalable, but then there's a problem that comes with that. And this is what is the resultant of the need for Kubernetes. Even though containers are scalable, they are not very easily scalable. Okay, so let's look at it this way. You have one container. You might want to probably scale it up to 2 containers or 3 containers. Well, it's possible, right? It's going to take a little bit of manual effort, but yeah, you can scale it up. You're not going to have a problem. But then look at a real world scenario where you might want to scale up to like 50 to 100 containers. Then in that case, what happens? I mean, after scaling up, what do? You have to manage those containers, right? You have to make sure that they're all working, they're all active, and they're all talking to each other. Because if they're not talking to each other, then there's no point of scaling up itself. Because in that case, the servers would not be able to handle the loads if they're not able to talk to each other, correct? So it's really important that they are manageable when they are scaled up. And now let's talk about this point. Is it really tough to scale up containers? Well, the answer for that might be no. It might not be tough. It's pretty easy to scale up containers, but the problem is what happens after that. Okay. Once you scale up containers, you'll have a lot of problems. Like I told you, the containers first of all should have to communicate with each other because there are so many in number, and they work together to basically host the service, right? The application. And if they are not working together and talking together, then the application is not hosted and scaling up is a waste. So that's the number one reason. And the next is that the containers have to be deployed appropriately, and they have to also be managed. They have to be deployed appropriately because you cannot have containers deployed in just random places. You have to deploy them in the right places. You cannot have one container in one particular cloud and the other one somewhere else. So that would have a lot of complications. Well, of course it's possible, but yeah, it would lead to a lot of complications internally. You want to avoid all that. So you have to have one place where everything is deployed appropriately, and you have to make sure that the IP addresses are set everywhere and the port numbers are open for the containers to talk to each other and all these things, right? So these were the two other points. The next point, or the next problem with scaling up, is that auto scaling is never a functionality over here. Okay, and this is one of the things which is the biggest benefit with Kubernetes. The problem technically is there's no auto scaling functionality. Okay, there's no concept of that at all. And you may ask at this point of time, why do we even need auto scaling? Okay, so let me explain the need for auto scaling with an example. So let's say that you are an e-commerce portal, okay, something like an Amazon or a Flipkart, and let's say that you have decent amount of traffic on the weekdays, but on the weekends you have a spike in traffic. Probably you have like 4x or 5x the usual traffic. And in that case, what happens is maybe your servers are good enough to handle the requests coming in on weekdays, right? But the requests that come on the weekends, right, from the increased traffic, that cannot be serviced by your servers, right? Maybe it's too much for your servers to handle the load. And maybe in the short term, it's fine. Maybe once or twice you can survive, but there will definitely come a time when your server will start crashing because it cannot handle that many requests per second or per minute. And if you want to really avoid this problem, what do? You have to scale up. And now, would you ideally keep scaling up every weekend and scaling down after the weekend, right? I mean, technically, is it possible? Will you be buying your servers and then setting it up, and every Friday would you be again buying new servers, setting up your infrastructure, and then the moment your weekday starts, would you just destroy all your servers, whatever you built? Would you be doing? No, right? Obviously, that's a pretty tedious task. So that's where something like Kubernetes comes in. And what Kubernetes does is it keeps analyzing your traffic and the load that's being used by the container. And as and when the traffic is reaching the threshold, auto scaling happens, wherein if the servers have a lot of traffic and if it needs more such servers for handling requests, then it starts scaling up the containers on its own. There's no manual intervention needed at all. So that's one benefit with Kubernetes, and one traditional problem that we have with scaling up of containers. Okay, and then yeah, the one last problem that we have is the distribution of traffic. That is still challenging without something that can manage your containers. I mean, you have so many containers, but how will the traffic be distributed? Load balancing, how does that happen? You just have containers, right? You have 50 containers. How does the load balancing happen? So all these are questions we should really consider, because containerization is all good and cool. It was much better than VMs. Yes, containerization, it was basically a concept which was sold on the basis of scaling up, right? We said that VMs cannot be scaled up easily, so we told use containers, and with containers you can easily scale up. So that was the whole reason we basically sold containers with the tagline of scaling up. But in today's world, our demand is ever more that even the regular containers cannot be enough. So scaling up is so much or in so detail that we need something else to manage your containers. Correct? Do we agree there? We need something, right? And that is exactly what Kubernetes is. So Kubernetes is a container management tool. All right. So this is open source, and this basically automates your container deployment, your container scaling and descaling, and your container load balancing. The benefit with this is that it works brilliantly with all the cloud vendors, with all your public cloud vendors or your hybrid cloud vendors, and it also works on premises. So that is one big selling point of Kubernetes, right? And if I should give more information about Kubernetes, then let me tell you that this was a Google developed product. Okay, it's basically a brainchild of Google, and that pretty much is the end of the story for every other competitor out there, because the community that Google brings in along with it is going to be huge. Or basically the head start that Kubernetes would get because of being a Google brainchild is humongous, and that is one of the reasons why Kubernetes is one of the best container management tools in the market, period. And given that Kubernetes is a Google product, they have written the whole product on Go language, and of course now Google has contributed this whole Kubernetes project to the CNCF, which is nothing but the Cloud Native Computing Foundation, or simply Cloud Native Foundation, right? You can just call them either that, and they've donated their open source project to them. And if I have to just summarize what Kubernetes is, you can just think of it like this. It can group like a number of containers into one logical unit for managing and deploying an application or a particular service. So that's a very simple definition of what Kubernetes is. It can be easily used for deploying your application. Of course, it's going to be Docker containers which you will be deploying, but since you will be using a lot of Docker containers as part of your production, you will also have to use Kubernetes which will be managing your multiple Docker containers, right? So this is the role it plays in terms of deployment. And scaling up, scaling down is primarily the game of Kubernetes. From your existing architecture, it can scale up to any number you want. It can scale down anytime. And the best part is the scaling can also be set to be automatic, like I just explained some time back, right? You can make Kubernetes would analyze the traffic and then figure out if the scaling up needs to be done or the scaling down can be done, and all those things. And of course, the most important part, load balancing, right? I mean, what good is your container or group of containers if load balancing cannot be enabled, right? So Kubernetes does that also. And these are some of the points based on which Kubernetes is built. So I'm pretty sure you have got a good understanding of what Kubernetes is by now, right? A brief idea at least. If you have any doubts, then I would request you to put your comments or queries on the comment section below. All right, my Edureka team will get back to you at the earliest. So moving forward, let's look at the features of Kubernetes. Okay, so we've seen what exactly Kubernetes is, how it uses Docker containers or other containers in general. But now let's see some of the selling points of Kubernetes or why it's a must for you. Let's start off with automatic bin packing. When we say automatic bin packing, it's basically that Kubernetes packages your application and it automatically places containers based on their requirements and the resources that are available. So that's the number one advantage. The second thing, service discovery and load balancing. There is no need to worry. I mean, if you're going to use Kubernetes, then you don't have to worry about networking and communication, because Kubernetes will just automatically assign containers their own IP addresses and probably a single DNS name for a set of containers which are performing a logical operation. And of course, there will be load balancing across them. So you don't have to worry about all these things. So that's why we say that there is service discovery and load balancing with Kubernetes. And the third feature of Kubernetes is that storage orchestration. With Kubernetes, you can automatically mount your storage system of your choice. You can choose that to be either a local storage or maybe on a public cloud provider such as a GCP or AWS, or even a network storage system such as NFS or other things, right? So that was the feature number 3. Now, feature number 4, self-healing. Now, this is one of my favorite parts of Kubernetes. Actually, not just Kubernetes, even with respect to Docker Swarm, I really like this part of self-healing. What self-healing is all about is that whenever Kubernetes realizes that one of your containers has failed, then it will restart that container on its own, right? It will create a new container in place of this crashed one. And in case your node itself fails, then what Kubernetes would do in that case is whatever containers were running in that failed node, those containers would be started in another node, right? Of course, you would have to have more nodes in that cluster. If there's another node in the cluster, definitely room would be made for this failed container to start its service. So that happens. So the next feature is batch execution. So when we say batch execution, it's that along with services, Kubernetes can also manage your batch and CI workloads, which is more of a DevOps role, right? So as part of your CI workloads, Kubernetes can replace your containers which fail, and it can restart and restore the original state. That is what is possible with Kubernetes. And secret and configuration management. That is another big feature with Kubernetes. And that is the concept of where you can deploy and update your secrets and application configuration without having to rebuild your entire image and without having to expose your secrets in your stack configuration or anything, right? So if you want to deploy and update your secrets, only that can be done. So it's not available with all the other tools, right? So Kubernetes is one that does that. You don't have to restart everything and rebuild your entire container. That's one benefit. And then we have horizontal scaling, which of course you people might be aware of already. You can scale your applications up and down easily with a simple command. The simple command can be run on the CLI, or you can easily do it on your GUI, which is your dashboard, your Kubernetes dashboard, or auto scaling is possible, right? Based on the CPU usage, your containers would automatically be scaled up or scaled down. So that's one more feature. And the final feature that we have is automatic rollbacks and rollouts. Now, Kubernetes, what it does is whenever there's an update to your application which you want to release, Kubernetes progressively rolls out these changes and updates to the application or its configurations by just ensuring that one instance after the other is sent these updates. And it makes sure that not all instances are updated at the same time, thus ensuring that, yes, there is high availability. And even if something goes wrong, then the Kubernetes will roll back that change for you. So all these things are enabled, and these are the features with Kubernetes. So if you're really considering a solution for your containers, for managing your containers, then Kubernetes should be your solution, right? So that should be your answer. So that is about the various features of Kubernetes. Now, moving forward, here, let's talk about a few of the myths surrounding Kubernetes. And we are doing this because a lot of people have confusion with respect to what exactly it is. So people have this misunderstanding that Kubernetes is like Docker, which is a containerization platform, right? That's what people think, and that is not true. So this kind of a confusion is what I intend to solve in the upcoming slides. I will talk about what exactly Kubernetes is and what Kubernetes is not. Let me start with what it's not. Now, the first thing is that Kubernetes is not to be compared with Docker because it's not the right set of parameters which you are comparing them against. Docker is a containerization platform and Kubernetes is a container management platform, which means that once you have containerized your application with the help of Docker containers or Linux containers, and when you are scaling up these containers to a big number like 50 or 100, that's where Kubernetes would come in. When you have like multiple containers which need to be managed, that's where Kubernetes can come in and effectively do it. You can specify the configurations and Kubernetes would make sure that at all times these conditions are satisfied. So that's what Kubernetes is. You can tell in your configurations that at all time I want these many containers running, I want these many pods running, and so many other needs, right? You can specify much more than that. And whatever you do, at all times, your cluster master or your Kubernetes master would ensure that this condition is satisfied. So that is what exactly Kubernetes is. But that does not mean that Docker does not solve this purpose. So Docker also have their own plugin. I wouldn't call it a plugin. It's actually another tool of theirs. So there's something called as Docker Swarm. And Docker Swarm does a similar thing. It does container management, like mass container management. So similar to what Kubernetes does, when you have like 50 to 100 containers, Docker Swarm would help you in managing those containers. But if you look at who is prevailing in the market today, I would say it's Kubernetes because Kubernetes came in first. And the moment they came in, they were backed by Google and they had this huge community which they just swept along with them. So they have like hardly left any market for Docker and for Docker Swarm. But that does not mean that they are better than Docker because they are at the end of the day using Docker. So Kubernetes is only as good as what Docker is. If there are no Docker containers, then there's no need for Kubernetes in the first place. So Kubernetes and Docker, they go hand in hand. Okay, so that is the point you have to note. And I think that would have also explained the point that Kubernetes is not for containerizing applications, right? And the last thing is that Kubernetes is not for applications with a simple architecture. Okay, if your architecture, if your application's architecture is pretty complex, then you can probably use Kubernetes to uncomplex that architecture. Okay, but if you're having a very simple one in the first place, then using Kubernetes would not serve you any good, and it could probably make it a little more complicated than what it already is, right? So this is what Kubernetes is not. Now, speaking of what exactly Kubernetes is, the first point is Kubernetes is robust and reliable. Now, when I say robust and reliable, I'm referring to the fact that the cluster that is created, the Kubernetes cluster, right? This is very strong. It's very rigid and it's not going to be broken easily. The reason being the configurations which you specify, right? At any point of time, if any container fails, a new container would come up, right? Or that whole container would be restarted. One of the things will definitely happen. If your node fails, then the containers which are running in a particular node, they would start running in a different node, right? So that's why it's reliable and it's strong because at any point of time, your cluster would be at full force. And at any time, if it's not happening, then you would be able to see that something's wrong and you have to troubleshoot your node and then everything would be fine. So Kubernetes would do everything possible and it pretty much does everything possible to let us know that the problem is not at its end and it's giving the exact result that we want. That's what Kubernetes are doing. And the next thing is that Kubernetes actually is the best solution for scaling up containers, at least in today's market, because the two biggest players in this market are Docker Swarm and Kubernetes. And Docker Swarm is not really the better one here because they came in a little late. Even though Docker was there from the beginning, Kubernetes came after that. But Docker Swarm, which we are talking about, came in somewhere around 2016 or 2017, right? But Kubernetes came somewhere around 2015. And they had a very good head start. They were the first ones to do this. And their backing by Google is just icing on the cake because whatever problem you have with respect to containers, if you just go up and if you put your error there, then you will have a lot of people on github.com and GitHub queries and then on Stack Overflow who will be resolving those errors, right? So that's the kind of market they have. So it's backed by a really huge community. That's what Kubernetes is. And to conclude this slide, Kubernetes is a container orchestration platform and nothing else. All right. So I think these two slides would have given you more information and more clarity with respect to what Kubernetes is and how different it is from Docker and Docker Swarm, right? If you guys still have any doubts, then I would request you to put your comments in the comment section below and my team will get back to you at the earliest. Okay, so now moving on, Let's go to the next topic where we will compare Kubernetes with Docker Swarm. And we are comparing with Docker Swarm because we cannot compare Docker and Kubernetes head on. Okay, so that is what you have to understand. If you are this person over here, if you are Sam who is wondering which is the right comparison, then let me reassure you that the difference can only be between Kubernetes and Docker Swarm. Okay, so let's go ahead and see what the difference is actually. Let's start off with your installation and configuration. Okay, so that's the first parameter we'll use to compare these two. And over here, Docker Swarm comes out on top because Docker is a little easier. You have around 2 or 3 commands which will help you have your cluster up and running. That includes the node joining the cluster, right? But with Kubernetes, it's way more complicated than Docker Swarm, right? So you have like close to 10 to 11 commands which you have to execute, and then there's a certain pattern you have to follow to ensure that there are no errors, right? Yes, and that's why it's time consuming and that's why it's complicated. But once your cluster is ready, that time Kubernetes is the winner because the flexibility, the rigidness, and the robustness that Kubernetes gives you cannot be offered by Docker Swarm. Yes, Docker Swarm is faster, but yes, not as good as Kubernetes when it comes to your actual working. And speaking of the GUI, once you have set up your cluster, you can use a GUI with Kubernetes for deploying your applications, right? So you don't need to always use your CLI. You have a dashboard which comes up, and the dashboard, if you give it admin privileges, then you can use it. You can deploy your application from the dashboard itself. Everything just drag and drop, click functionality, right? With just click functionality, you can do that. The same is not the case with Docker Swarm. You have no GUI in Docker Swarm, okay? Period. So Docker Swarm is not the winner over here. It's Kubernetes. And yes, going to the third parameter, scalability. So people again have a bad misconception that Kubernetes is better. It is the solution for scaling up, and it is better and faster than Docker Swarm. Well, it could be better, but yes, it's not faster than Docker Swarm. Even if you want to scale up, right? There's a report where I recently read that the scaling up in Docker Swarm is almost 5 times faster than the scaling up with Kubernetes. So that is the difference. But yes, once your scaling up is done, after that, your cluster strength with Kubernetes is going to be much stronger than your Docker Swarm cluster strength. That's again because of the various configurations that should have been specified by then. That is the thing. Now, moving on to the next parameter we have is load balancing. Requires manual service configuration. Okay, this is in case of Kubernetes. And yes, this could be a shortfall, but with Docker Swarm, there is inbuilt load balancing techniques, which you don't need to worry about. Okay, even the load balancing, which requires manual effort in case of Kubernetes, is not too much. There are times when you have to manually specify what are your configurations. You have to make a few changes, but yes, it's not as much as what you're thinking. And speaking of updates and rollbacks, what Kubernetes does is it does the process scheduling to maintain the services while updating. Okay, yeah, that's very similar to how it works with Docker Swarm, wherein you have like progressive updates and service health monitoring happens throughout the update. But the difference is when something goes wrong, Kubernetes goes that extra mile of doing a rollback and putting you back to the previous state, right, before the update was launched. So that is the thing with Kubernetes. And the next parameter we are comparing those two upon is data volumes. So data volumes in Kubernetes can be shared with other containers, but only within the same pod. So we have a concept called pods in Kubernetes. Okay, now pod is nothing but something which groups related containers, right? A logical grouping of containers together. So that is a pod. And whichever containers are there inside this pod, they can have a shared volume, okay, like storage volume. But in case of Docker Swarm, you don't have the concept of pod at all. So the shared volumes can be between any other container. There is no restriction with respect to that in Docker Swarm. And then finally, we have this parameter called logging and monitoring. So when it comes to logging and monitoring, Kubernetes provides inbuilt tools for this purpose. Okay, but with Docker Swarm, you have to install third-party tools if you want to do logging and monitoring. So that is the fallback with Docker Swarm, because logging is really important. One, because you will know what the problem is. You'll know which container failed, what happened, where is exactly the error, right? So logs would help you give that answer. And monitoring is important because you have to always keep a check on your nodes, right? So as the master of the cluster, it's very important that there's monitoring. And that's where Kubernetes has a slight advantage over Docker Swarm. Okay, so that's my take on the difference between Kubernetes and Docker Swarm. And I would also love to hear what's your take on this, right? I would like to know if you would use Kubernetes or Docker Swarm, and I would also know why. If you prefer simplicity or if you prefer stability, that choice could be yours. And it's something that's arguable, right? It's a debatable topic. So I would like to hear what are your thoughts. So please drop in your comments at the bottom. We have a comment section, right? Our videos. So put it right there. and probably in one of our future videos we will discuss about that. But before I finish this topic, there is this one slide I want to show you which is about the statistics. So this stat I picked it up from this platform 9, which is nothing but a company that writes about tech. Okay, and what they've said is that the number of news articles that were produced, right, in that one particular year had 90% of those covered on Kubernetes compared to the 10% on Docker Swarm. Amazing, right? That's a big difference. That means for every one blog written or for every one article written on Docker Swarm, there are 9 different articles written on Kubernetes. And similarly for web searches. For web searches, Kubernetes is 90% compared to Docker Swarm's 10%. And publications, GitHub stars, the number of commits on GitHub, all these things are clearly won by Kubernetes everywhere. So Kubernetes is the one that's dominating this market, and that's pretty visible from this stat also, right? So I think that pretty much brings an end to this particular topic. Now moving forward, let me show you a use case. Let me talk about how this game, this amazing game called Pokemon Go, was powered with the help of Kubernetes. I'm pretty sure you all know what it is, right? You guys know Pokemon Go. It's the very famous game, and it was actually the best game of the year 2017. And the main reason for that being the best is because of Kubernetes. And let me tell you why. But before I tell you why, there are a few things which I want to just talk about. I'll give you an overview of what Pokemon Go is, and let me talk about a few key stats. So Pokemon Go is an augmented reality game developed by Niantic for your Android and for iOS devices. Okay, and those key stats read that they've had like 500 million plus downloads overall and 20 million plus daily active users. Now that is massive. Daily, if you're having like 20 million users plus, then you have achieved an amazing thing. So that's how good this game is. Okay, and then this game was actually initially launched only in North America, Australia, New Zealand, and I am aware of this fact because I'm based out of India and I did not get access to this game because the moment news got out that we have a game like this, I started downloading it, but I couldn't really find any link or I couldn't download it at all. So they launched it only in these countries, but what they faced, right, in spite of just releasing it in these 3 countries, they had like a major problem. And that problem is what I'm going to talk about in the next slide, right? So my use case is based on that very fact that in spite of launching it only in these 3 countries or in probably North America and then in Australia, New Zealand, they could have had a meltdown, but rather with the help of Kubernetes, they used that same problem as the basis for their success. So that's what happened. Now, let that be a suspense. And before I get to that, let me just finish this slide. One amazing thing about Pokemon Go is that it has inspired users to walk over 5.4 billion miles in a year. Okay, yes, do the math. 5.4 billion miles in 1 year. That's again a very big number. And it says that it has surpassed engineering expectations by 50 times. Now, this last line is not with respect to the Pokemon Go, the game, but it is with respect to the backend and the use of Kubernetes to achieve whatever was needed. Okay, so I think I've spent enough time over here. Let me go ahead and talk about the most interesting part and tell you how the backend architecture of Pokemon Go was. Okay, so you have a Pokemon Go container which had 2 primary components. One is your Google Bigtable, which is your main database where everything is going in and coming out. And then you have your programs, which is run on your Java cloud, right? So these 2 things are what is running your game. MapReduce and Cloud Dataflow were something which was used for scaling up. Okay, so it's not just the container scaling up, but it's with respect to the application, how the program would react when there are these increased number of users and how to handle increased number of requests. So that's where the MapReduce is the paradigm comes in, right? The mapping and then reducing that whole concept. So this was their one deployment. Okay, and when we say into 5, it means that they had their server capacities which could go up till 5 times. Okay, so technically they could only serve X number of requests, but in case of failure conditions or heavy traffic load conditions, the max the server could handle was 5x, because after 5x the server would start crashing. That was their prediction. Okay, and what actually happened at Pokemon Go on releasing in just those 3 different geographies is that the moment they deployed it, the usage became so much that it was not X number of times, which is technically their failure limit, and it is not even 5x, which is the server's capability, but the traffic that they got was up to 50 times more than what they expected. So you know that when your traffic is so much, then you're going to be brought down to your knees. That's a definite and that's a given, right? This is like a success story, and this is too good to be true kind of a story. And in that kind of a scenario, if the requests start coming in are so much that if they reach 50x, then it's gone, right? The application is gone for a toss. So that's where Kubernetes comes in, and they overcome all the challenges. How do they overcome the challenges? Because Kubernetes can do both vertical scaling and horizontal scaling at ease. And that is the biggest problem, right? Because any application and any other company can easily do horizontal scaling, where you just spin up more containers and more instances and you set up the environment. But vertical scaling is something which is very specific, and this is even more challenging. Now it's more specific to this particular game because the virtual reality would keep changing. Whenever a person moves around or walks around somewhere in his apartments or somewhere on the road, then the RAM, right, that would have to increase. The memory, the in-memory and the storage memory, all this would increase. So in real time, your server's capacity also has to increase vertically. So once they have deployed it, it's not just about horizontal scalability anymore. It's not about satisfying more requests. It's about satisfying that same request with respect to having more hardware space, more RAM space, and all these things, right? That one particular server should have more performance abilities. That's what it is about. And Kubernetes solved both of these problems effortlessly. And Niantic were also surprised that Kubernetes could do it. And that was because of the help that they got from Google. I read an article recently that the head of Niantic's lab, he met with some of the top executives in Google and in GCP, right? And then they figured out how things are supposed to go. And they, of course, met with the heads at Kubernetes, and they figured out a way to actually scale it up to 50 times in a very short time. So that is the challenge that they were presented. And thanks to Kubernetes, they could handle 50 times the traffic that they expected, which is like a very one-off story, and which is very, very surprising that, something like this would happen. So that is about the use case. And that pretty much brings an end to this topic of how Pokemon Go used Kubernetes to achieve something. Because in today's world, Pokemon Go is a really revered game because of what it could, right? It basically beat all the stereotypes of a game, and whatever anybody could have anything negative against the game, right? So they could say that these mobile games and video games make you lazy, they make you just sit in one place and all these things, right? And Pokemon Go was something which was different. It actually made people walk around and it made people exercise. And that goes on to show how popular this game became. If Kubernetes lies at the heart of something which became so popular and something that became so big, then you should imagine how big Kubernetes or how useful Kubernetes is, right? So that is about this topic. As said before, Kubernetes master controls your nodes, and inside nodes, you have containers, okay? And now these containers are not just contained inside them, but they are actually contained inside pods, okay? So you have nodes inside which there are pods. And inside each of these pods, there will be n number of containers, depending upon your configuration and your requirement, right? Now, these pods which contain n number of containers are a logical binding or logical grouping of these containers. Supposing you have an application X which is running in node 1, okay? So you will have a pod for this particular application, and all the containers which are needed to execute this particular application will be a part of this particular pod, right? So that's how pod works, and that's what the difference is with respect to Docker Swarm and Kubernetes. Because in Docker Swarm, you will not have a pod, you just have containers running on your node. And the other two terminologies which you should know is that of replication controller and service. Your replication controller is the master's resource to ensuring that the requested number of pods are always running on the nodes, right? So that's like your confirmation or an affirmation which says that, okay, this many number of pods will always be running, and these many number of containers will always be running, something like that, right? So you say it, and the replication controller will always ensure that's happening. And your service is just an object on the master that provides load balancing across a replicated group of pods, right? So that's how Kubernetes works. And I think this is good enough introduction for you. And I think now I can go to the demo part, right, guys? If you guys have any doubts, I would request you to again put it in the comment section, and my team will get back to you. And in the meanwhile, let me get to the final part of this video, wherein I will show you how to deploy applications on your Kubernetes via either your CLI or either via your YAML files or via your dashboard. Okay, guys, so let's get started. And for the demo purpose, I have two VMs with me, okay? So as you can see, this is my kube master, which would be acting as my master in my cluster. And then I have another VM, which is my kube node 1, okay? So it's a cluster with one master and one node. All right. Now, for the ease of purpose for this video, I have compiled the list of commands in this text document, right? So here I have all the commands which are needed to start your cluster, and then the other configurations and all those things. So I'll be using these. I'll be copying these commands, and then I'll show you side by side, and I will also explain when I do that as to what each of these commands mean. Now, there's one prerequisite that needs to be satisfied, and that is the master should have at least 2 core CPUs, okay, and 4 GB of RAM, and your node should have at least 1 core CPU and 4 GB of RAM. So just make sure that this much of hardware is given to your VMs, right? If you're using Ubuntu or a Linux operating system, well and good, but if you're using a VM on top of a Windows OS, then I would request you to satisfy these things, okay, these 2 criteria. And I think we can straight away start. Let me open up my terminal first of all. Okay, this is my node. I'm going back to my master. Okay, yes. So first of all, if you have to start your cluster, you have to start it from your master's end, okay? And the command for that is Kubeadm init. You specify the pod network flag and the API server flag. We are specifying the pod network flag because the different containers inside your pod should be able to talk to each other easily, right? So that was the whole concept of self-discovery, which I spoke about earlier during the features of Kubernetes. So for the self-discovery, we have like different pod networks using which the containers would talk to each other. And if you go to the documentation, the Kubernetes documentation, you can find a lot of options there. You can use either a Calico pod, or you can use a Flannel pod network. So when we say pod network, it's basically acronymed as CNI, okay, Container Network Interface, okay? So you can use either a Calico CNI or a Flannel CNI or any of the other ones. These are the 2 popular ones, and I will be using the Calico CNI, okay? So this is the network range for this particular pod, and this we'll have to specify over here, okay? And then over here we'll have to specify the IP address of the master. So let me first of all copy this entire line, and before I paste it here, let me do an if config and find out what is the IP address of this particular machine, of my master machine. The IP address is 192.168.56.101, okay? So let's just keep that in mind, and let me paste the command over here. In place of the master IP address, I'm going to specify the IP address of the master, okay, which I just read out. It is 192.168.56.101. And the pod network, I told you that I'm going to use the Calico pod, so let's copy this network range and paste it here. So all my containers inside this particular pod would be assigned an IP address in this range, okay? Now let me just go ahead and hit enter, and then your cluster would begin to set up. So it's going as expected. So it's going to take a few minutes, so just hold on there. Okay, perfect. My Kubernetes master has initialized successfully, and if you want to start using your cluster, you have to run the following as a regular user, right? So we have 3 commands which is suggested by Kubernetes itself, and that is actually the same set of commands that even I have here, okay? So I'll be running the same commands. This is to set up the environment, and then after that we have this token generated, right, the joining token. So the token along with the init address of the IP of the master, if I basically execute this command in my nodes, then I will be joining this cluster where this is the master, right? So this is my master machine. This just created the cluster. So now before I do this though, there are a few steps in the middle. One of those steps is executing all these 3 commands, and after that comes bringing up the dashboard and setting up the pod network, right? Mine is the Calico pod, so I'll have to set up the Calico pod, and then I have to also set up the dashboard. Because if I do not start the dashboard and this before the nodes, then the node cannot join, and I will have various other complications. So let me first of all go ahead and run these 3 commands one after the other, okay? Since I have the same commands in my text doc, I'll just copy it from there, okay? I'll say Control C, paste, enter, okay? And I'll copy this line. So remember, you have to execute all these things as regular user, okay? You can probably use your sudo, but yeah, you'll be executing it as your regular user. And it's asking me if I want to override the existing whatever is there in this directory. I would say yes, because I've already done this before. But if you are setting up the cluster for the first time, you will not have this prompt, okay? Now, let me go to the 3rd line, copy this and paste it here. Okay, perfect. Now I've ran these 3 commands as I was told by Kubernetes. Now the next thing that I have to do is, before I check the node status and all these things, let me just set up the network, okay, the pod network. So like I said, this is the line, this is the command that we have to run to set up the Calico network, okay, to allow the nodes to join our particular network. So it will be copying the template of this calico.yaml file which is present over here in this docs, okay? So hit enter, and yes, my thing is created. Calico Cube controller is created. Now I'll just go back here and see at this point of time I can check if my master is connected to the particular pod. Okay, so I can run the kubectl get nodes command. Okay, this would say that I have one particular resource connected to the cluster. Okay, name of the machine, and this role is master, and yeah, the status is ready. Okay, if you want to get an idea of all the different pods which are running by default, then you can do the kubectl get pods along with a few options. Okay, you should specify these flags, and they are all namespaces, and with the flag O specify wide. Okay, so this way I get all the pods which are started by default. Okay, so there are different services like etcd for kube controllers, for the Calico node, for the etcd master. For every single service there's a separate container and pod started. Okay, so that's what you can understand from this part. Okay, that is the safe assumption. Now that we know the cluster is ready and the master is part of the cluster, let's go ahead and execute this dashboard. Okay, remember, if you want to use a dashboard, then you have to run this command before your nodes join this particular cluster, because the moment your nodes join into the cluster, bringing up the dashboard is going to be challenging and it will start throwing errors. Okay, it will say that it's being hosted on the node, which we do not want. We want the dashboard to be on the server itself, right, on the master. So first let's bring the dashboard up. So I'm going to copy this and paste it here. Okay, enter. Great, my Kubernetes dashboard is created. Now the next command that you have to get your dashboard up and running is kubectl proxy. Okay, with this you'll get a message saying that it's being served at this particular port number, and yes, you are right now there. You can, if you access localhost, what was the port number again? Localhost, yeah, 127.0.0.1 is localhost. Okay, followed by port number 8001. Okay, yeah, so right now we are not having the dashboard because it is technically accessed on another URL. But before we do that, there are various other things that we have to access. I mean, we have to set. Okay, because right now we have only enabled the dashboard. Now if you want to access the dashboard, you have to first of all create a service account. Okay, the instructions are here. Okay, you have to first of all create a service account for your dashboard. Then you have to say that, okay, you are going to be the admin user of this particular service account, and you have to enable that functionality here. You should say dashboard admin privileges, and you should do the cluster binding. Okay, the cluster role binding is what you have to do. And after that, to join to that or to get access to that particular dashboard, we have to basically give a key. Okay, it's like a password. So we have to generate that token first, and then we can access the dashboard. So again, for the dashboard, there are these three commands. Well, you can get confused down the line, but remember, this is separate from the above. Okay, so what we did initially is ran these three commands which Kubernetes told us to execute, and after that the next necessity was bring up a pod. So this was that command for the pod, and then this was the command for getting the dashboard up, and right after that run the proxy, and then on that particular port number it'll start being served. So my dashboard is being served, but I'm not getting the UI here, and if I want to get the UI, I have to create the service account and do these three things, right? So let's start with this and then continue. I hope this wasn't confusing, guys. Okay, I can't do it here, so let me open a new terminal. Okay, here I'm going to paste it, and yes, service account created. Let me go back here and execute this command where I'm doing the role binding. I'm saying that my dashboard should have admin functionalities, and that's going to be the cluster role. Okay, cluster admin, and then the service account is what I'm using, and it's going to be in default namespace. Okay, so when I created the account, I said that I want to create this particular account in default namespace. So the same thing I'm specifying here. Okay, dashboard admin created. Good. So let's generate the token that is needed to access my dashboard. Okay, before I execute this command, let me show you that once. So if you go to this URL, right, /API/v1/namespaces. Yep, let me show it you here. Okay, so this is the particular URL where you will get access to the dashboard. Okay, login access to the dashboard, localhost 8001 API v1 namespaces /kubesystem/services/https Kubernetes dashboard :/proxy. Okay, remember this one. That is the same thing over here, and like I told you, it's asking me for my password, so I would say token, but let me go here and hit the command and generate the token. So this is the token. I'm going to copy this from here till here. I'm going to say copy, and this is what I have to paste over here. All right, so sign and update. Yes, perfect. So this is my dashboard. right? This is my Kubernetes dashboard, and this is how it looks like. Whatever I want, I can get an overview of everything. So there is workloads. If I come down, there is deployments. I have option to see the pods, and then I can see what are the different services running among most of the other functionalities. Okay, so right now we don't have any bar graph or pie graph showing you which cluster is up, which pod is up and all, because I have not added any node and there is no service that is running, right? So I mean, this is the outlay of the dashboard. Okay, you will get access to everything you want from the left. You can drill down into each of these namespaces or pods or containers, right? Now, if you want to deploy something through the dashboard, right, through the click functionality, then you can go here. Okay, but before I create any container or before I create any pod or any deployment for that matter of fact, I have to have nodes, because these will be running only on nodes, correct? Whatever I deploy, they run only on nodes. So let me first open up my node and get the node to join this particular cluster of mine. Now, if you remember, the command to join the node got generated at the master end, correct? So let me go and fetch that again. So that was the first command that we ran, right? This one. So let's just copy this and paste this one at my node end. This is the IP of my master, and it will just join at this particular port number. Let me hit enter. Let's see what happens. Okay, let me run it as root user. Okay, perfect. Successfully established connection with the API server, and it says this node has joined the cluster, right? Bingo. So this is good news to me. Now if I go back to my master, and in fact if I open up the dashboard, there would be an option of nodes, right? So initially now it's showing this master. Master is the only thing that is part of my nodes. Let me just refresh it, and you would see that even node-1 would be a part of it, right? So there are two resources, two instances. One is the master itself and the other is the node. Now if I go to overview, you will get more details. If I start my application, if I start my servers or containers, then all those would start showing up here, right? So it's high time I start showing you how to deploy it. To deploy it using the dashboard, I told you this is the functionality. So let's go ahead and click on this create. And yeah, mind you, from the dashboard is the easiest way to deploy your application, right? So even developers around the world do the same thing. For the first time, probably they create it using the YAML file, and then from there on, they start editing the YAML file on top of the dashboard itself, or they create or deploy the application from here itself. So we'll do the same thing. Go to create an app using functionality, click functionality, you can do it over here. So let's give a name to your application. I'll just say Edureka demo. Okay, let that be the name of my application. And I want to basically pull an Nginx image. Okay, I want to launch an Nginx service. So I'm going to specify the image name in my Docker hub. Okay, so it says either the URL of a public image or any registry, or a private image hosted on Docker hub or Google Container Registry. So I don't have to specify the URL per se, but if you're specifying a Docker hub, if you're specifying this image to be pulled from Docker hub, then you can just use the name of the image which has to be pulled. That's good enough, right? Nginx is the name, and that's good enough. And I can choose to set my number of pods to 1 or 2. In that way, I will have 2 containers running in the pod, right? So this is done. And the final part is, actually without the final part, I can straight away deploy it. Okay, but if I deploy it, then my application would be created, but I would just not get the UI. I mean, I won't see the Nginx service. So that I get the service, I have to enable one more functionality here. Okay, the servers here, click on the drop down and you will have external option, right? So click on external. This would let you access this particular service from your host machine, right? So that is the definition. So you can see the explanation here. An internal or external service can be defined to map an incoming port to a target port seen by the container. So Nginx, which would be hosted on one of the container ports that could not be accessible if I don't specify anything here. But now that I've said access it externally on a particular port number, then it would get mapped for me. By default, Nginx runs on port number 80. So the target port would be the same, but the port I want to expose it to, that I can map it to anything I want. So I'm going to say 82. All right. So that's it. It's as simple as this. This way your application is launched with 2 pods. So I can just go down and click on deploy. And this way my application should be deployed. My deployment is successful. There are 2 pods running. So what I can do is I can go to the service and try to access the UI, right? So it says that it's running on this particular port number 82153. So copy this and say localhost 32153. Okay, hit enter. Bingo. So it says welcome to Jenkins, and I'm getting the UI, right? So I'm able to access my application which I just launched through the dashboard. It was as simple as that. So this is one way of launching or making a deployment. There are two other ways, like I told you. One is using your CLI itself, your command line interface of your Linux machine, which is the terminal, or you can do it by uploading the YAML file. You can do it by uploading the YAML file because everything here is in the form of YAML or JSON. Okay, that's like the default way. So whatever deployment I made, right, that also those configurations are stored in the form of YAML. So if I click on view or edit YAML, all the configurations are specified. The default ones have been taken. So I said the name should be Edureka demo. That is what has been taken over here. That is the name of my deployment. Okay, so kind is deployment. The version of my API, it's this one, extension / v1 beta 1, and then under metadata I have various other lists. So if you know how to write a YAML file, then I think it will be a little more easier for you to understand and create your deployment, because YAML file is everything about lists and maps, and these YAML files are always lists about maps and maps about lists. So it might be a little confusing. So probably we'll have another tutorial video on how to write a YAML file for Kubernetes deployment, but I would keep that for another session. Okay, let me get back to this session and show you the next deployment. Okay, the next deployment technique. So let me just close this and go back to overview. Okay, so I have this one deployment. Very good. Okay, so let's go to this. Yeah, so what I'll do is let me delete this deployment. Okay, or let me at least scale it down, because I don't want too many resources to be used on my node also, because I will have to show 2 more deployments, right? So I have reduced my deployment over here, and I think it should be good enough. Great. So let's go back to the kube setup, this document of mine. So this is where we were, right? We could check our deployments, we could do all these things. So one thing which I might have forgotten is showing the nodes which are part of the cluster, right? So this is my master. Yeah, so I kind of forgot to show you this kubectl get node. So the same view that you got on your dashboard, you get it here also. I mean, these are the 2 nodes, and this is the name and all these things. Okay, and I can also do the kubectl get pods, which would tell me all the pods that are running. Edureka demo is the pod which I have started. Okay, this is my pod. Now if I specify with the other flags, right, with all namespaces and with wide, then all the default pods which get created along with your Kubernetes cluster, those will also get displayed. Let me show you that also, just in case. Okay, yeah, so this is the one which I created, and the other ones are the default deployments that come with Kubernetes. The moment you install set up the cluster, these get started. Okay, and if you can see here, this particular Edureka demo which I started is running on my node 1 along with this kube proxy and this particular Calico node. So these 2 services are running on master and node, and this one is running only on my node 1, right? You can see this, right? The Calico node runs both on my node over here and on my master, and similarly the kube proxy runs on my node here and on my master. So this is the one that's running only on my node. Okay, so getting back to what I was about to explain you, the next part is how to deploy anything through your terminal. Now to deploy your same Nginx application through your CLI, we can follow these set of commands. Okay, so there are a couple of steps here. First of all, to create a deployment, you have to run this command. Okay, kubectl create deployment Nginx, and then the name of the image that you want to create. This is going to be the name of your deployment, and this is the name of the image which you want to use. So Control C, and let me go to the terminal here. On my master, I'm executing this command, kubectl create deployment. Okay, so the deployment Nginx is created. If you want, we can verify that also over here. So under deployments, right now we have one entry, Edureka demo, and yes, now you can see there are 2, Nginx and Edureka demo. So this is pending. I mean, it would take a few seconds. So in the meanwhile, let's just continue with the other steps. Once you have created your deployments, you have to create the service. Okay, you have to say which is the node port which can be used to access that particular service, right? Because deployment is just a deployment. You're just deploying your container. If you want to access it, like I told you earlier, from your from your host machine or all those things, then you have to enable the node port. If you want to get your deployments on your terminal, you can run this command kubectl get deployments. Okay, Nginx also comes up over here, right? If you want more details about your deployment, you can use this command kubectl describe. You'll get like more details about this particular deployment as to what is the name, what is the port number it's residing on, and all these things. Okay, let's not complicate this. You can probably use that for your understanding later. So once that is done, the next thing that you have to do is you have to create the service on the nodes. You have created the deployment, but yes, create the service on the nodes using this particular command kubectl create service and say node port. Okay, this means you want to access it at this particular port number. You're doing the port mapping 80:80. Okay, container port 80 to the internal node port 80. Okay, so service for Nginx is created. And if you want to check which of the deployments are running in which nodes, you can run the command kubectl get svc. Okay, this would tell you, okay, you have two different services, Edureka demo and Nginx, and they are running on these port numbers and on these nodes, right? So Kubernetes is the one which got created automatically. Edureka demo is the one which I created. Okay, Nginx is again the one which I created. Kubernetes comes up on its own. I'm just specifying to you because this is a container for the cluster itself. Okay, so let's just go back here, and then yes, and similarly, if you want to delete a deployment, then you can just use this command kubectl delete deployment followed by the name of the deployment, right? It's pretty simple. You can do it this way. Otherwise, from the dashboard also you can delete it, like how I showed you earlier. Click over here and then you can click on delete, and then if you want to scale it, you can scale it. So both of these deployments of mine have one pod each, right? So let's do one thing. So let's just go to the Nginx service, and here let's try accessing this particular service. Localhost. Okay, perfect. Here also it says welcome to Nginx, right? So with this you can understand that the port mapping worked, and by going to service you will get to know on which port number you can access it on your host machine, right? So this is the internal container port mapped to this particular port of mine. Okay, now if not for this, if this doesn't work, you can also use the cluster IP for the same thing. Cluster IP is going to basically the IP using which all your containers access each other, right? So for your pod you will have an IP, so whatever is running in your containers, that will again be accessible on your cluster IP. So it's the same thing, right? So let me just close these pages, and that's how you deploy an application through your CLI. So this comes to our last part of this video, which is nothing but deployment via YAML file. So for again deployment via YAML file, you have to write your YAML code, right? You have to either write your YAML code or your JSON code, correct? So this is the code which I have written, which is in YAML format, and in fact I already have it in my machine here. So how about I just do an ls? Yeah, there is deployment.yaml, right? So let me show you that. So this is my YAML file. Okay, so here I specify various configurations similar to how I did it using the GUI or I did it using the CLI. It's something similar. It's just that I specify everything in one particular file. Here, if you can see that I have specified the API version. Okay, so I'm using extensions /b1 or beta 1. Okay, I can do this, or I can just simply specify version 1. I can do either of those. And then the next important line is the kind. So kind is important because you have to specify what kind of file it is. Is it a deployment file, or is it for a pod deployment, or is it for your container deployment, or is it the overall deployment? What is it? So I've said deployment, okay, because I want to deploy the containers also along with the pod. So I'm saying deployment. In case you want to deploy only the pod, which you realistically don't need to, okay, why would you just deploy a pod? But in case if you want to deploy a pod, then you can go ahead and write pod here and then just specify what are the different containers. Okay, but in my case it's a complete deployment, right, with the pods and the services and the containers. So I will go ahead and write other things, and under the metadata I will specify the name of my application. I can specify what I want. I can put my name also over here, like Vardhan. Okay, and I can save this. And then the important part is this spec part. So here is where you set the number of replicas. Do you remember I told you that there's something called as replication controller, which controls the number of pods that you will be running? So it is that line. So if I've set 2 over here, it means that I will have 2 pods running of this particular application of Vardhan. Okay, what exactly am I doing here? Under spec, I'm saying that I want 2 containers. So I've intended a container line over here, and then I have 2 containers inside. So The first container which I want to create is of the name front end, okay, and I'm using an Nginx image. And similarly, the port number that this would be active on is container port 80. All right, and then I'm saying that I want a second container, and the container for this I could rename this to anything. I can say backend, and I can choose which image I want. I can probably choose a HTTPD image also, okay, and I can again say the ports that this will be running on. I can say the container port that it should run on is port number is 88, right? So that's how simple it is. All right, and since it's your first video tutorial, the important takeaways from this YAML file configuration is that under spec you'll have to specify the containers and yes, everything in JSON format with all the indentations and all these things, okay. Even if you have an extra space anywhere over here, then your YAML file would throw an invalid error. So make sure that is not there. Make sure you specify the containers appropriately. If it's going to be just one container, well and good. If it's two containers, make sure you indent it in the right way, and then you can specify the number of pods you want to give a name to your deployment, and mainly establish these rules, okay. So once you're done with this, just save it and close this YAML file, okay. So this is your deployment.yaml. Now you can straight away upload this YAML file to your Kubernetes, okay, and that way your application would be straight away deployed, okay. Now the command for that is kubectl create -f and the name of the file, okay. So let me copy this, and then the name of my file is deployment.yaml. So let me hit enter. Perfect. So my deployment, the third deployment, Vardhan, is also created, right? So we can check our deployments from the earlier command, that is nothing but kubectl get deployments. Okay, it's not get deployment.yaml, sorry, it's get deployments. And as you can see here, there is an Edureka demo, there is Nginx, and there is Vardhan. And the funny thing which you should have noticed is that I said I want two replicas, right? Two pods. So that's why the desired is two. Currently we have two, up to date is one. So okay, up to date is two. Brilliant. Available is 0 because let's just give it a few seconds. In 23 seconds, I don't think the pod would have started. So let's go back to our dashboard and verify if there's a third deployment that comes up over here. Okay, perfect. So that's how it's going to work. Okay, so probably it's going to take some more time because the container is just restarting. So let's just give it some more time. This could well be because of the fact that my node has very less resource, right? So I have too many deployments. That could be the very reason. So what I can do is I could go ahead and delete other deployments so that my node can handle these many containers and pods, right? So let me delete this particular deployment, Nginx deployment, and let me also delete this Edureka demo deployment of mine. Okay, now let's refresh and just wait for this to happen. Okay, so what I can do instead is I could have a very simple deployment, right? So let me go back to my terminal and let me delete my deployment, okay, and let me redeploy it again. So kubectl delete deployment. Okay, so Vardhan, this deployment has been deleted. Okay, so let's just clear the screen and let's do gedit of the YAML file again. And here let's make things simpler. Let me just delete this container from here. Let me save this. All right, and close this. Now let me create a deployment with this. Okay, so Vardhan is created. Let me go up here and refresh. Let's see what happens. Okay, so this time it's all green because it's all healthy. My nodes are successful, or at least it's going to be successful. Container creating. Perfect. So two pods of mine are up and running, and both my pods are running, right? And both are running on node 1. Pods 2 out of 2. Those are the two deployments, and replica set, and then services, right? So it's Nginx, which is the base image which is being used. So well and good. This is also working. So guys, yeah, that's about it, right? So when I tried to upload it, maybe there was some other error, probably in the YAML file. There could have been some small mistake, or it could have been because my node had too many containers running. Those could have been the reasons. But anyways, this is how you deploy it through your YAML file.
Before we move on, I have another question for you guys. And the question is, which of the following is not a fundamental component of Kubernetes? And the options are A, nodes, B, cluster, C, pods, or D, containers. And if you know the answer, please leave it in the comment section below. Having learned the fundamentals, we will move on to Kubernetes installation on Ubuntu where you will see how to set up Kubernetes on Ubuntu.
Let me show you what are the various steps that we have to follow. Now there are various steps that we have to run both at the master's end and the slave end, and then a few commands only at the master's end to bring up the cluster, and then one command which has to be run at all the slave ends so that they can join the cluster. Okay, so let me get started by showing you those commands and those installation steps which have to be run commonly on both the master's end and the slave end. First of all, we have to update your repository. Okay, since I'm using Ubuntu, I'll have to update my apt-get repository. Okay, and after that, we will have to turn off the swap space, be it the master's end or the slave's end. Kubernetes will not work if the swap space is on. Okay, we have to disable that. So there are a couple of commands for that. And then the next part is we have to update the host name, the hosts file, and we have to set a static API address for all the nodes in your cluster. Okay, we have to do that because at any point of time, if your master or if your node in the cluster fails, then when they restart, they should have the same IP address. If you have a dynamic IP address, and then if they restart because of a failure condition, then it'll be a problem because they will not be able to join the cluster because they'll have a different IP address. So that's why we have to do these things. All right, there are a couple of commands for that. And after that, we have to install the OpenSSH server and Docker. That is because Kubernetes requires the OpenSSH functionality, and it of course needs Docker because everything in Kubernetes is containers, right? So we are going to make use of Docker containers. So that's why we have to install these two components. And finally, we have to install Kubeadm, Kubelet, and Kubectl. Now these are the core components of your Kubernetes. All right, so these are the various components that have to be installed on both your master and your slave end. So let me first of all open up my VMs and then show you how to get started. Now before I get started, let me tell you one thing. You have a cluster, you have a master, and then you have slaves in that cluster, right? Your master should always have better configurations than your slave. So for that reason, if you're using virtual machines on your host, then you have to ensure that your master has at least 2 GB of RAM and 2 core CPUs. Okay, and your slave has 2 GB of RAM and at least 1 core CPU. So these are the basic necessities for your master and slave machines. On that note, I think I can get started. So first of all, I'll bring up my virtual machine and go through these installation processes. So I hope everyone can see my screen here. This is my first VM, and what I'm going to do is I'm going to make this my master. Okay, so all the commands to install the various components are present with me in my notepad. Okay, so I'm going to use this for reference and then quickly execute these commands and show you how Kubernetes is installed. So first of all, we have to update our apt-get repository. Okay, but before that, let's log in as su. Okay, so I'm going to do a sudo su so that I can execute all the following commands as sudo user. Okay, so sudo su, there goes my root password, and now you can see the difference here, right? Here I was executing it as a normal user, but from here I'm a root user. So I'm going to execute all these commands as su. So first of all, let's do an update. I'm going to copy this and paste it here. apt-get update updates my Ubuntu repositories. All right, so it's going to take quite some time, so just hold on till it's completed. Okay, so this is done. The next thing I have to do is turn off my swap space. Okay, now the command to disable my swap space is swap off space flag a. Let me go back here and do the same. Okay, swap off with flag a. And now we have to go to this fs tab. So this is a file called fs tab. Okay, and we will have a line with the entry of swap space, because at any point of time, if you've enabled swap space, then you'll have a line over there. Now we have to disable that line. Okay, we can disable that line by commenting out that line. So let me show you how that's done. I'm just using the nano editor to open this fs tab file. Okay, so you can see this line, right, where it says swap file. This is the one which I have to comment out. So just let me come down here and comment it out like this. Okay, with a hash. Now let me save this and exit. Now the next thing I have to do is update my host name and my hosts file and then set a static IP address. So let me get started by first updating the host name. So for that, I have to go to this file host name, which is in this /etc path. So I'm again using nano for that. You can see here it's Edureka-virtualbox, right? So let me replace this and say kmaster as in Kubernetes master. So let me save this and exit. Now if you want your host name to reflect over here, because right now it says root@Edureka-virtualbox. The host name does not look updated as yet. And if you want it to be updated to kmaster, then you have to first of all restart this VM or your system. If you're doing it on a system, then you have to restart your system. And if you're doing it on a VM, you have to restart your VM. Okay, so let me restart my VM in some time. But before that, there are a few more commands which I want to run. And that is set a static IP address. Okay, so I'm going to copy this ifconfig. I'm going to run the ifconfig command. Okay, so right now my IP address is 192.168.56.101. And the next time when I turn on this machine, I do not want a different IP address. So to set this as a static IP address, I have a couple of commands. Let me execute that command first. So you can see this interfaces file, right? So under etc/network, we have a file called interfaces. So this is where you define all your network interfaces. Now let me enter this file and add the rules to make it a static IP address. As you can see here, the last 3 lines are the ones which ensure that this machine will have a static IP address. These 3 lines are already there on my machine. Now, if you want to set a static IP address at your end, then make sure that you have these things defined correctly. Okay, my IP address is .101, so I would just retain it like this. So let me just exit. So the next thing that I have to do is go to the hosts file and update my IP address over there. Okay, so I'm gonna copy this and go to my etc/hosts files. Now over here you can see that there's no entry, so I have to mention that this is my kmaster. So let me specify my IP address first. This is my IP address, and now we have to update the name of the host. So this host of mine is kmaster. So I'm just gonna enter that and save this. Okay, now the thing that we have to do now is restart this machine. So let me just restart this machine and get back to you in the meanwhile. Okay, so now that we are back on, let me check if my host name and hosts have all been updated. Yes, there you go. You can see here, right? Edureka@kmaster. So this means that my host name has been successfully updated. We can also verify if my IP address is the same. Let me do an ifconfig. And as you can see, my IP address has not changed. All right, so this is good. Now this is what we wanted. Now let's continue with our installation process. Let me clear the screen and go back to the notepad and execute those commands which first of all install my OpenSSH server. So this is going to be the command to do that, and we have to execute this as sudo user, right? So sudo apt-get install OpenSSH server, that's the command. Okay, let me say yes and enter. Okay, so my SSH server would have been installed by now. Let me clear the screen and install Docker. But before I run this command which installs Docker, I need to update my repository. Okay, so let me log in as sudo first of all. Okay, sudo su is the command, and okay, I've logged in as root user. Now the next thing is update my repository. So I have to do an apt-get update. Now again, this is going to take some more time, so just hold on till then. Okay, this is also done. Now I can straight away run the command to install Docker. Now this is the command to install Docker. Okay, from the apt-get repository, I'm installing Docker. I'm just specifying -y because -y is my flag. So whenever there's a prompt that comes in while installation saying, do you want to install it, yes or no, then when you specify -y, then it means that by default it will accept y as a parameter. Okay, so that is the only concept behind -y. So again, installing Docker is going to take a few more minutes. Just hang on till then. Okay, great. So Docker is also installed. Okay, so let me go back to the notepad. So to establish the Kubernetes environment, the 3 main components that Kubernetes is made up of are Kubeadm, kubelet, and kubectl. But just before I install these 3 components, there are a few things I have to do. They are like installing curl and then downloading certain packages from this URL and then running an update. Okay, so let me execute these commands one after the other first and then install Kubernetes. So let's first of all start with this command where I'm installing curl. Okay, now the next command is basically downloading these packages using curl, and curl is basically this tool using which you can download these packages using your command line. Okay, so this is basically a web URL, right? So I can access whatever packages are there on this web URL and download them using curl. So that's why I've installed curl in the first place. So on executing this command, I get this, which is perfect. Now when I go back, then there is this which I have to execute. Okay, let me hit enter and I'm done. And finally, I have to update my apt-get repository. And the command for that is this one, apt-get update. Okay, great. So all the pre-installation steps are also done. Now I can straight away set up my Kubernetes environment by executing this command. So in the same command, I say install kubelet, Kubeadm, and kubectl. And to just avoid the yes prompt, I'm specifying the -y flag, okay, which will by default take yes as a parameter. And of course, I'm taking it from the apt-get repository, right? So let me just copy this and paste it here. Give it a few more minutes, guys, because installing Kubernetes is going to take some time. Okay, bingo. So my Kubernetes has also been installed successfully. Okay, now let me conclude the setting up of this Kubernetes environment by updating the Kubernetes configuration. Okay, so there's this file here, right? Kubeadm.conf. So there's the Kubeadm is the one that's going to let me administer my Kubernetes. So I have to go into this file and add this one line. Okay, so let me first of all open up this file using my nano editor. So let me again log in as sudo su, and this is the command. So as you can see, we have these set of environment variables. So right after the last environment variable, I have to add this one line, and that line is this one. All right, now let me just save this and exit. Brilliant. So with that, the components which have to be installed at both the master and the slave come to an end. Now what I have to do next is run certain commands only at the master to bring up the cluster, and then run this one command at all my slaves to join the cluster. All right, so before I start doing anything more over here, let me also tell you that I have already done the same steps on my node. So if you are doing it at your end, then whatever steps you've done so far, run the same set of commands on another VM, because that will be acting as your node VM. But in my case, I've already done that just to save some time, So let me show you that this is my K master, and right here I have my K node, which is nothing but my Kubernetes node. And I've basically run the same set of commands in both the places. But there's just one thing which I have to ensure before I bring up the cluster, and that is ensure the network IP addresses and the host name and the hosts. So this is my Kubernetes node. So first of all, I'm going to do a cat and say /etc hosts. Okay, now over here I have the IP address of my Kubernetes node, that is this very machine, and I've specified the name of the host. However, the name of my Kubernetes master host is not present, and neither is the IP address. So that is one manual entry we have to do. If you remember, let me go to my master and check what is the IP address. Yes, so the IP address over here is 192.168.56.101. So this is the IP address I have to add in my node end. So I have to modify this file for that. All right. But before that, you have to also ensure that this is a static IP address. So let me ensure that the IP address of my cluster node does not change. So the first thing we have to do before anything is check what is the current IP address. And for my node, the IP address is 192.168.56.102. Okay. Now let me run this command, network interfaces. Okay. So as you can see here, this is already set to be a static IP address. You have to ensure that these same lines are there in your machine if you want it to be a static IP address. Since it's already there for me, I'm not going to make any change, but rather I'm going to go and check what's my host name. I mean, the host name should anyways give the same thing, because right now it's Knode, so that's what it's going to reflect. But anyways, let me just show it to you. Okay, so my host name is Knode. Brilliant. So this means that there's just one thing which I have to change, and that is nothing but adding the particular entry for my master. So let me first clear the screen, and then using my nano editor, in fact, I'll have to run it as sudo. So as a sudo user, I'm going to open my nano editor and edit my hosts file. Okay, so here, let me just add the IP address of my master. So what exactly is the IP address of the master? Yes, this is my K master. So I'm just going to copy this IP address, come back here and paste the IP address. And I'm going to say the name of that particular host is K master. And now let me save this. Perfect. Now what I have to do now is go back to my master and ensure that the host file here has details about my slave. I'll clear the screen, and first I'll open up my hosts file. So on my master's end, the only entry is there for the master. So I have to write another line where I'll specify the IP address of my slave and then add the name of that particular host, that is knode. And again, let me use the nano editor for this purpose. So I'm going to say sudo nano/etc hosts. Okay. So I'm going to come here, say 192.168.56.102 and then say knode. All right. Now all the entries are perfect. I'm going to save this and exit. So the hosts file on both my master and my slave has been updated. The static IP address for both my master and the slave has been updated. And also the Kubernetes environment has been established. Okay. Now, before we go further and bring up the cluster, let me do a restart because I've updated my hosts file. Okay. So let me restart both of my master and my slave VMs. And if you're doing it at your end, then you have to do the very same. Okay. So let's say restart. And similarly, let me go to my node here and do a restart. Okay, so I've just logged in. And now that my systems are restarted, I can go ahead and execute the commands at only the master's end to bring up the cluster. Okay, so first of all, let me go through the steps which are needed to be run on the master's end. So at the master, first of all, we have to run a couple of commands to initiate the Kubernetes cluster, and then we have to install a pod network. We have to install a pod network because all my containers inside a single pod will have to communicate over a network. Pod is nothing but a network of containers. So there are various container networks which I can use. So I can use the Calico pod network, I can use the Flannel pod network, or I can use any one. You can see the entire list in the Kubernetes documentation. And in this session, I'm going to use the Calico network. Okay, so that's pretty simple and straightforward. And that's what I'm going to show you next. So once you've set up the pod network, you can straight away bring up the Kubernetes dashboard. And remember that you have to set up the Kubernetes dashboard and bring this up before your nodes join the cluster. Because in this version of Kubernetes, if you first get your nodes to join the cluster, and after that, if you try bringing the Kubernetes dashboard up, then your Kubernetes dashboard gets hosted on the node. And you don't want that to happen, right? If you want the dashboard to come up at your master's end, you have to bring up the dashboard before your nodes join the cluster. So these will be the three commands that we will have to run: initiating the cluster, installing the pod network, and then setting up the Kubernetes dashboard. So let me go to my master and execute commands for each of these processes. So I suppose this is my master, and yes, this is my kmaster. So first of all, to bring up the cluster, we have to execute this command. Let me copy this, and over here we have to replace the IP addresses. So the IP address of my master, right? So this machine, I have to specify that IP address over here because this is where the other IP addresses can come and join. This is the IP address of the master, right? So I'm just saying API server advertise the address 56.101 so that all the other nodes can come and join the cluster on this IP address. And along with this, I have to also specify the pod network. Since I've chosen the Calico pod network, there's a network range which my Calico pod network uses. So CNI basically stands for Container Network Interface. If I'm using the Calico pod network, then I have to use this network range. But in case if you want to use a Flannel pod network, then you can use this network range. Okay, so let me just copy this one and paste it. All right, so the command is sudo kubeadm init pod network followed by the IP address from where the other nodes will have to join. So let's go ahead and hit enter. So since you're doing it for the first time, give it a few minutes because Kubernetes takes some time to install. So just hold on until that happens. All right. Okay, great. Now it says that your Kubernetes master has initialized successfully. That's good news. And it also says that to start using your cluster, you need to run the following commands as a regular user. Okay, so note that log out as a sudo user and as a regular user, execute these three commands. And also if I have to deploy a pod network, then I have to run a command. Okay, so this is that command which I have to run to bring up my pod network. So I'll be basically cloning the YAML file which is present over here. So before I get to all these things, let me show you that we have a kube join command which is generated, right? So this is generated at my master's end, and I have to execute this command at my node to join the cluster. But that would be the last step because, like I said earlier, these three commands will have to be first executed. Then I have to bring up my pod network. Then I have to bring up my dashboard, and then I'll have to get my nodes to join the cluster using this command. So for my reference, I'm just going to copy this command and store it somewhere else. Okay. So right under this, let me just store this command for later reference. And in the meanwhile, let me go ahead and execute all these commands one after the other. These are as per Kubernetes' instructions, right? Yes, I would like to rewrite it. And then, okay. Now that I've done with this, let me first of all bring up my pod network. Okay, now the command to bring up my pod network is this. Perfect. So my Calco pod has been created. Now I can verify if my pod has been created by running the kubectl get pods command. Okay, so this is my kubectl get pods. I can say -o wide all namespaces. Okay, by specifying the -o wide and all namespaces, I'll basically get all the pods ever deployed, even the default pods which get deployed when the Kubernetes cluster initiates. So basically the Kubernetes cluster is initiated and deployed along with a few default ones, especially for your pod network. There's one pod which is hosted for your cluster. There's one pod for your pod itself. And then there's one pod which is deployed for your dashboard and whatnot. So this is the entire list, right? So for your Calico, for your etcd, there's one pod. For your kube controller, there's a pod. And we have various pods like this, right? For your master and your API server and many things. So these are the default deployments that you get. So anyways, as you can see, the default deployments are all healthy because it says the status is all running and everything is basically running in the kube system namespace. All right. And it's all running on my K master. That's my Kubernetes master. So the next thing that I have to do is bring up the dashboard before I can get my nodes to join. Okay. So I'll go to the notepad and copy the command to bring up my dashboard. So copy and paste. So great. This is my Kubernetes dashboard, which has, basically this pod has come up. Now, if I execute this same kubectl get pods command, then you can see that I've got one more pod which is deployed for my dashboard basically. So last time this was not there because I had not deployed my dashboard at that time, right? So I had only deployed my pod network and whatnot and the other things, right? So I've deployed it and the container is creating. So in probably a few more seconds, this would also be running. So anyways, in the meanwhile, what we can do is we can work on the other things which are needed to bring up the dashboard. To first of all enable your proxy and get it to be hosted web server, there's this kubectl proxy command. Okay, so with this, your service would be starting to be served on this particular port number. Okay, localhost port number 8001 of my master. Okay, not from the nodes. So if I could just go to my Firefox and go to localhost 8001, then my dashboard would be up and running over there. So basically my dashboard is being served on this particular port number. But if I want to actually get my dashboard which shows my deployments and all my services, then that's a different URL. Okay, so yeah, as you can see here, localhost 8000/API/v1, right? This entire URL is which is going to lead me to my dashboard. But at this point of time, I cannot log into my dashboard because it's prompting me for a token. And I do not have a token because I have not done any cluster role binding and I have not mentioned that I am the admin of this particular dashboard. So to enable all those things, there are a few more commands that we have to execute, starting with creating a service account for your dashboard. So this is the command to create your service account. So go back to the terminal and probably a new terminal window, execute this command. Okay, so with this, you're creating a service account for your dashboard. And after that, you have to do the cluster role binding for your newly created service account. Okay, so the dashboard has been created in default namespace as per this. Okay, and here I'm saying that my dashboard is going to be for admin and I'm doing the cluster role binding. Okay, and now that this is created, I can straight away get the token, because if you remember, it's asking me for a token to log in, right? So even though I'm the admin now, I will not be able to log in without the token. So to generate the token, I have to again run this command, kubectl get secret key. Okay, so I'm gonna copy this and paste it here. So this is the token, or this is the key that basically needs to be used. So let me copy this entire token and paste it over here. So So let me just save this. And yeah, now you can see that my Kubernetes cluster has been set up, and I can see the same thing from the dashboard over here. So basically by default, the Kubernetes service is deployed, right? So this is what you can see. But I've just brought up the dashboard now, and my cluster is not ready until my nodes join in. So let's go to the final part of this demonstration, wherein I'll ask my slaves to join the cluster. So you remember I had copied the join cluster which was generated at my master's end in my notepad. So I'm going to copy that and execute that at the slave's end to join the cluster. Okay, so let me first of all go to my notepad, and yeah, this is the join command which I had copied, right? So I'm going to copy this, and now I'm going to go to my node. Yeah, so let me just paste this, and let's see what happens. Let me just run this command as sudo. So perfect. I've got the message that I have successfully established connection with the API server on this particular IP address and port number, right? So this means that my node has joined the cluster. We can verify that from the dashboard itself. So if I go back to my dashboard, which is hosted on my master's end, so I have an option here as nodes. If I click on this, then I will get the details about my nodes over here. So earlier I only had the K master, but now I have both the K master and the K node. Give it a few more seconds until my node comes up. I can also verify the same from my terminal. So if I go to my terminal here, and if I run the command kubectl get nodes, then it will give me the details about the nodes which are there in my cluster. So kmaster is one that is already there in the cluster, but knode, however, will take some more time to join my cluster. All right, so that's it, guys. So that is about my deployment, and that's how you deploy a Kubernetes cluster. So from here on, you can do whatever deployment you want. Whatever you want to deploy, you can deploy it easily, very effectively, either from the dashboard or from the CLI. And there are various other video tutorials of ours which you can refer to see how a deployment is made on Kubernetes. So I would request you to go to the other videos and see how deployment is made.
Okay, I have another question for you guys. Which package manager is used to install Kubernetes on CentOS? Options are given on the screen, and if you know the answer, please leave it in the comment section below. After the Ubuntu installation is complete, we will proceed to the Kubernetes installation on CentOS to cover the setup process for this Linux distribution.
Let's look at the prerequisites or the requirements for installing the Kubernetes. Here, first, you need to have 2 or more CentOS 7 servers. Next, you need the Docker. Also, you are gonna need root privileges on all the CentOS servers, and you need a minimum of 2 CPUs and a minimum of 2 GB RAM with complete connectivity among all those servers. And you must have the swap disabled. This is a setting in the OS that can interfere with how Kubernetes operate. So let's go to the demo and see what we can do to get Kubernetes installed on our CentOS 7 system. Here I have 2 VMs. For this demo, we are using EC2 instances. As you can see, I have my instances running, but this is not limited to the AWS cloud. You can have your private servers or other cloud servers as well. If you type into your browser Kubeadm install, you will see a link to the documentation. If you click on it, you will see what is the instructions. In the beginning, it says that you need a compatible Linux host for the installation, and as we discussed in the prerequisites, you need 2 GB minimum of RAM and you need 2 CPUs or more. You also must have the swap disabled and you must have full connectivity among all the systems. Now, since we are going to be installing this on our CentOS 7 system, we will be looking at these instructions, which are Red Hat based distribution, because CentOS 7 is a Red Hat based distribution. So these are the instructions that we need to run in our command line. But before that can happen, we need to install Docker on both our worker and our master node. So let's get started. So I connect with my master and my worker node. And the first thing that we are going to do is we will type sudo yum check update. And I'll do the same in the worker node as well. Now that is done, I will go ahead and install the Docker. So I'll copy this command and I'll run this on my worker as well. After this is done, what we'll be doing is we'll be installing the Docker and we will be starting the Docker service and we will enable the Docker. And after that, we will escalate some privileges. Now, let's do the starting of Docker. Now, I'll type the same command in my worker node as well. Now, let's check the status of our Docker. So as you can see, the Docker is active and running, but the service is still disabled. To change that, we will change the status to enable. And now, if we check again the status, it should say that our service is enabled. So we do the same thing on our worker as well. And let's confirm the status. So both our master and worker are now configured, and now we can move on to the next step of installing the Kubernetes. So let's go to our documentation and then copy all of these commands into our notepad, because this is all the commands that we will be running. And because this command is a comment, we will just remove this. So I have my notepad set up here, and then I'll go ahead and delete this comment. As you can see, it will be creating a Kubernetes repo file and it will have some checks. So it has a GPG check, it has a repo GPG check, but I'll be just changing this to 0 just to help install the Kubernetes faster on the system. So let's copy all of these commands and then paste it into our terminal. Now in our terminal, all the commands get executed one by one. And we do the same thing on our worker as well. And now on our master node, we are now ready to start the Kubernetes initialization. So to do that, the command for that is Kubeadm init, and then you pass on the API server advertise address. And this address is the private IP address of the instance. So we'll go to our AWS console and then find out the private IP of the master. So as you can see, this is the private IP. So what I'll be doing is I'll paste this into a command here. And then I'll type pod network CIDR. And for this, the ranges that we are going to be using is this. And now let's hit enter. It throws up an error message saying we are not the privileged user. So let's change that. Now let's run this command again. So as this is initializing, what I'll do on my worker node is that I'll keep this active. And I can do that by typing this command. So now this session won't log out and I can continue working with my master. So as you can see, it starts throwing up some errors. And this is what I wanted to show you, because following the documentation doesn't actually lead to us getting the proper results. So we were able to find a workaround for that using community questions as well as some documentation. So let's close this and then let me show you the configuration that we have used. So this is the workaround that we have come up with for installing Kubernetes on CentOS 7. So if we look at the documentation, you can see here, if we scroll up, under this portion, letting IP tables see bridge traffic, this was one of the workarounds that we were able to fix. What we have essentially done here is we have copied all of these commands and we have pasted this. And other such things have been used to fix the Kubernetes. So I'll copy these commands and I'll paste this into our master node. And here I'll be pasting this to get the Kubernetes to work on our master. Now these commands reload the daemon and then it restarts the Docker. And essentially afterwards the Kubeadm initialization should essentially work. Okay, now let's try running the initialization again. So it starts throwing up some errors. So what we can do is I'll type Kubeadm reset to reset everything, and then type in yes. And now let's run the Kubeadm init again. So as you can see, it says that we were successful and now we can start using our cluster. But before we can do that, we need to run these commands. And afterwards, we can join our worker nodes by using this command. So what I'll be doing is I'll be copying all of this into my notepad. And then I'll paste it here. Now I'll execute these top 3 commands right away. Remember, this has to be done on the master. That is, these commands have to be run on the master. Okay, now that we have done this, we should be able to see our nodes. So to do that, what we'll type is kubectl get nodes. And as we can see, the master is now active, but it is not in the ready status. We can also check the status of the pods by typing this command. So in here, as you can see, the core DNS, that is the first 2, are still in the pending status and everything else is running. What this means is that the networking is not yet smooth. And to fix that, what we can do is we can use the Calico installation to fix everything. So if you type into your browser install Calico, you should go over to the documentation. And because in our case, we are using less than 50 nodes under this section, we can follow these 4 steps and then we'll have a proper working master. So the first step is to copy this command and paste it. So I'll paste this into our master and then let's see what the documentation says. So if you're using pod CIDR, which we did before the initializing, then we can skip on to the next step. So let's skip this. And the third step says that you can customize the manifest as necessary. Now, we don't need that. So we'll directly go over to the 4th command, which says the applying of the manifest using the following command. So I'll just copy this command and I'll paste this in my master. And now let's see the status of our pods. So as you can see, this is now working, and if we click hitting refresh, we should be able to see the status change. So it is still in the initialization phase and now it seems like it is working. But let's wait. And as you can see, now the network is properly set up. So right now, what we can do is we can go ahead on our worker node and then try to connect it to our master. But before that, some configuration things have to be done. So to keep this session active, I'll again type in this command and I'll go on to my worker node and then try to configure. Now these steps are what I found works in my case because the CentOS 7 needs some type of configuration to be done before it can work smoothly with the Kubernetes. So for that, I have come up with this workaround. And then I'll restart my daemon and the Docker. And then I restart the kubelet. Now I'll type in systemctl enable kubelet service. And now I should ideally be able to connect to the master. And to connect my worker node with my master, what I'm gonna do is I'll copy this command, which was an output from the master, and then I can copy this command into my worker node, and then we should be able to connect with our master node. Now in here, it says that we were able to get this connected. Now let's type in this command on our master to see if it was successful or not. And now, as you can see, we have been connected with our master. And we can see the status over here as ready. So, now that you have some idea on how you can install Kubernetes on your CentOS 7 system, feel free to experiment and then learn more about this. It might be possible that some commands that we have run today might not exactly work for you, but this is the major way that things are going to be done. So, as long as you follow the documentation properly, you should be able to get your Kubernetes working properly and then deploy your cluster with the Docker. And that's it.
Now that you have installed Kubernetes on CentOS, we will look at Kubernetes architecture to understand how the different components fit together.
Let's look into the architecture of Kubernetes. Kubernetes architecture has mainly three components: the master nodes, the worker nodes, and the distributed key value stores like etcd. Talking about the master node is responsible for managing the Kubernetes cluster, and it is the entry point for all the administrative tasks. So we can communicate to the master node via the CLI or GUI or APIs. So for the fault tolerance purposes, there can be more than one master node in the cluster, and if we have more than one master node, then there would be high availability mode and only one of them will be the leader performing all the operations. All the other master nodes would be the followers of that node. Also, to manage the cluster state, Kubernetes uses etcd and all the master nodes connect to it. So etcd is a distributed key value store, which I'll tell you in a little while. Also, let me tell you that the key value store can be the part of the master node, and it can also be configured externally, and in that case, master nodes would connect to it. So now that I've told you what a master node is and what are the responsibilities of the master node, let's discuss the components of master nodes. A master node has mainly four components: the API server, the scheduler, the control manager, and etcd. So now let me tell you about all these components one by one. So starting with API server, all the administrative tasks are performed via the API server within the master node. A user sends the REST commands to the API server, which then validates and processes the request. After executing the request, the resulting state of the cluster is stored in the distributed key value store. After that, we have scheduler. So as the name suggests, the scheduler schedules the work to different worker nodes. The scheduler has the resource usage information for each worker node and also knows about the constraints that the users may have set. Before scheduling the work, the scheduler also takes into account the quality of service requirements, data locality, affinity, anti-affinity, and many other such parameters, and then the scheduler schedules the work in terms of pods and services. The next component that we have is controller manager. Now, what do you think are the responsibilities of controller manager? Well, as the name suggests, controller manager manages different non-terminating control loops which regulate the state of the Kubernetes cluster. Now, each one of these control loops know about their desired state of the object it manages, and then they watch their current state through the API servers. Now, in a control loop, if the current state of the object it manages does not meet the desired state, then the control loop itself takes the corrective steps to make sure that the current state is same as the desired state. So what does a controller manager do? It basically makes sure that your current state is same as the desired state. After that, the last component that we have is etcd. So as I mentioned earlier, etcd is a distributed key value store which is used to store the cluster state. So either it has to be a part of the Kubernetes master or you can configure it externally. So guys, that were the various components of master node. Now let's move on to the next component of Kubernetes architecture, that is the worker node. A worker node is a machine or a virtual machine or any physical server which runs the applications using pods and is controlled by the master node. So you understand the master-slave concept. It has its own machine, but yes, it is controlled by the master node. Now pods are scheduled on the worker nodes which have the necessary tools to run and connect them. So you can say that the pod is basically the scheduling unit in Kubernetes. It is a logical collection of one or more containers which are always scheduled together, and to access the applications from the external world, we have to connect to the worker nodes and not the master nodes. So now that I've briefed you about the worker node, let's discuss the various components of worker node. So a worker node has mainly three components: the kubelet, the kubeproxy, and container runtime. So let's start the discussion with container runtime. So a container runtime is basically used to run and manage a container's lifecycle on the worker node. So some examples of container runtimes that I can give you are the container, RKT, LXT, etc. Now, it is often observed that Docker is also referred to as container runtime. But to be precise, let me tell you that Docker is a platform which uses containers as container runtime. Alright, so now that you've understood what container runtime is, let's move on to the second component, that is kubelet. So kubelet is basically an agent which runs on each worker node and communicates with the master node. So if you have 10 worker nodes, then kubelet runs on each and every worker node. Then it receives the pod definition via various means and runs the containers associated with that pod. It also makes sure that the containers which are part of the pods are healthy at all times. So what does a kubelet do? It basically runs in all the containers. It makes sure that your containers which are part of various pods are always healthy at all times. So the kubelet connects to the container runtime using the container runtime interface, which consists of various protocol buffers, gRPC APIs, and libraries. So as you can see on the screen, the kubelet connects to the CRI shim to perform containers and image operations. Now, CRI implements two services, that is the runtime service and the image service. The image service is responsible for all the image-related operations, while the runtime service is responsible for all the pod and container-related operations. So these two services have two different operations to perform. Now let me tell you something interesting here. Container runtimes used to be hard-coded in Kubernetes, but with the development of CRI, Kubernetes can now use different container runtimes without the need to recompile. So any container runtime that implements CRI can be used by Kubernetes to manage pods, containers, and container images. So now let me give you an example of a CRI shims. So Docker shim and CRI container are two examples of CRI shim. With Docker shim, containers are created using Docker installed on the worker nodes, and then internally Docker uses container to create and manage containers. With CRI container, we can directly use Docker's small offspring containers to create and manage containers. So these were two simple examples of CRI shims. Now let's move on to the third component of worker node, that is kubeproxy. So kubeproxy is the network proxy which runs on each worker node and then listens to the API server for each service point creation or deletion. So for each service point, kubeproxy sets the route so that it can reach to it. So guys, that were the components of the worker node. So now let me move on with the session by discussing the third component of Kubernetes architecture, that is etcd. So as I mentioned before, Kubernetes uses the etcd to store the cluster state. So etcd is a distributed key value stored based on the raft consensus algorithm. So the raft allows a collection of machines to work as a coherent group that can survive the failures of some of its members. So basically this algorithm works in such a way that even if some of the members fail to work, it can still work. At any given time, one of the nodes in the group will be the master and rest of them will be the follower. As I told you before in the starting of the session, that there can be only one master and all the other masters have to follow that master, right? Not only this, but let me tell you that etcd is written in the Go programming language. Besides storing the cluster state, etcd is also used to store the configuration details such as the subnets and the config maps.
After understanding the architecture, we will compare Kubernetes versus Docker to highlight their role and differences.
What is Docker? Docker is a containerization platform that packages your application and all its dependencies together in form of a Docker container to ensure that your application works seamlessly in any environment. It is basically an open platform for developing, shipping, and running applications. Now, Docker enables you to separate your applications from your infrastructure so you can deliver software very quickly. With Docker, you can also manage your infrastructure in the same ways you manage your applications. By taking advantage of Docker's methodologies for shipping, testing, and deploying code very quickly, you can significantly reduce the delay between writing code and running it in production. Basically provides the ability to package and run an application in a loosely isolated environment called a container. The isolation and security allow you to run many containers simultaneously on a given host. As we've already discussed, containers are lightweight and contain everything needed to run an application, so you don't really need to rely on what is currently installed on the host. You can easily share containers while you work, and be sure that everyone you share with gets the same container that works in the same way. Now, there are some important features of Docker that I'd like to address. The first feature is that it is extremely fast and there is a consistent delivery of your applications. Now, Docker streamlines the development lifecycle by allowing developers to work in standardized environments using local containers, which provide your applications and services. Containers are great for continuous integration and continuous delivery workflows. Now, let me explain this with a tiny example. Your developers write code locally and share their work with their colleagues using Docker containers. Now, they use Docker to push their applications into a test environment and execute automated and manual tests. When developers find bugs, they can easily fix them in the development environment and redeploy them to the test environment for testing and validation. Now, when finally testing is complete, getting the fix to the customer is as simple as pushing the updated image to the production environment. This is how easy it is to use Docker and to get your work done. The second feature is that it has a responsive deployment and scaling. Docker containers can run on a developer's local laptop, on physical or virtual machines in a data center, on cloud providers, or even in a mixture of environments. Its portability and lightweight nature also makes it very easy to dynamically manage workloads, scaling up or tearing down applications and services as business needs dictate in near real time. The third feature is running more workloads on the same hardware. Docker is lightweight and fast. It provides a viable, cost-effective alternatives to hypervisor-based virtual machines, so you can use more of your compute capacity to achieve your business goals. It is perfect for high-density environments and for small and medium deployments where you need to do more with fewer resources. So there is a relationship between Kubernetes and Docker. We're going to discuss them now. So if Docker is containers and Kubernetes is container orchestration, why would anyone ask, should I use Docker or Kubernetes? Now, in reality, the two tools are actually complementary to each other and help build cloud-native or microservice architectures. Docker is mostly used during the first days of a containerized application. It really actually helps build and deploy the application's container or containers. In cases where the application's architecture is very simple, Docker can address the basic needs of the application's lifecycle management. Now, if the case or the scenario where the application is broken down into multiple microservices, with each of these services having their own lifecycle and operational needs, Kubernetes comes into the picture. It is not only used to create the application containers, it actually needs a container platform to run, and Docker being the most popular one, it runs on that. Kubernetes integrates with a large toolset built for and around containers and uses it in its own operations. Containers created with Docker or any of its alternatives can be managed, scaled, and moved by Kubernetes, which also ensures failover management and health maintenance of the system. As you can see in the diagram, the container lifecycle has been explained. You can see that in the Docker, there is the build and deployment of the application that has been successfully done. Once the Docker has been successfully deployed, then Kubernetes takes the responsibility to monitor and scale the application. There are great benefits to using Kubernetes with Docker. Firstly, the applications are easier to maintain as they are broken down into smaller parts. Also, these parts run on an infrastructure that is much more robust, and the applications are more highly available. Here, applications are able to handle more load on demand, improving the user experience and reducing resource waste. As applications become more scalable, there is no need to pre-allocate resources in anticipation of load peak times. Now here, both Docker and Kubernetes are backed by strong open source communities and are part of the Cloud Native Computing Foundation, a Linux Foundation project aiming to advance container technologies and align the industry around specific standards. Now that we understand that Docker and Kubernetes have a really great relationship together, let's move ahead and address the main topic of today's session, that is Kubernetes versus Docker. Firstly, we will compare them in terms of setup and installation. as you can see on the screen, Kubernetes really requires a series of many manual steps to set up the master and worker node components in a cluster of nodes. It's really hard and complicated to install Kubernetes. But on the other hand, that is, installing Docker is a matter of one-liner commands on Linux platforms like Ubuntu and CentOS. So compared to Kubernetes, Docker is much more easy to install and set up. Moving on to the next difference, that is logging. Kubernetes provides no native storage solution for log data, whereas logging driver plugins are available in Docker 17.05 and much higher. So in terms of monitoring Kubernetes applications, you can use various open source tools like Prometheus, Grafana, InfluxDB, etc. Docker, on the other hand, also has tools like Prometheus, Docker API, etc. for monitoring purposes. Kubernetes supports up to 5,000 nodes, whereas Docker supports only up to 2,000 nodes. And in terms of compatibility, Kubernetes is more comprehensive and highly customizable, whereas Docker is less extensive and customizable. So for all of y'all who don't know what load balancing is, it is an efficient distribution of network or application traffic across multiple servers in a server farm. So usually each load balancer sits between client devices and backend servers, receiving and then distributing incoming requests to any available server capable of fulfilling them. As you can see in Kubernetes, you must manually configure your load balancing settings, whereas in Docker, it does auto load balancing. That is, it is automated. Now, there are various companies that use Kubernetes and Docker. Companies like Google, Shopify, Udemy, Slack, Robinhood, Delivery Hero, Stackshare, Nubank, etc. use Kubernetes every day. On the other hand, various companies like Twitter, Business Insider, Spotify, PayPal, eBay, Oxford University Press, the New York Times, New Relic, all of these companies and organizations make use of Docker. Now that we've compared Kubernetes and Docker, let us understand in what situation to use Kubernetes and Docker. So what are the choices when it comes to Kubernetes and Docker? What happens if you do choose to use only one and not the other? So there are three scenarios that I'll be addressing. The first one is Docker without Kubernetes. The second one is Kubernetes without Docker. And the third one is Kubernetes with Docker. We've already discussed the benefits of using Kubernetes with Docker, but we'll just brief up that again. So firstly, let's understand the scenario where Docker can be used without Kubernetes. Docker by itself will allow you to build container images, manage them in a registry, run containers, and communicate with them, and eventually put them together in a multi-container application using Docker Compose. So is Docker all that you need? Now, when it comes to producing and managing container images and putting containers into operation at the runtime level, the answer for the most part is definitely yes. It has become the industry standard for creating containers and getting them off the ground. Now, under Docker's current developer-centric definition of its mission, however, it has moved away from earlier attempts to go beyond its core functions. It is no longer attempting to compete with Kubernetes and other companies at the infrastructure or orchestration level. Now, let's talk about the second scenario. Kubernetes does not include functionality for creating or managing container images, and it does not by itself run containers. It really needs to work with an external container source and runtime. It is, however, capable of using containers from a variety of sources, and it is compatible with runtimes other than Docker, so it is not inherently dependent on Docker and Docker alone. What Kubernetes does is it provides a rich and a very flexible and powerful framework for defining applications and orchestrating containers at scale. It is very well designed for key enterprise-level tasks such as automated scaling, maintaining high availability, and operating in a multi-platform environment. It also has a large community of users and developers with a corresponding large number of add-ons and support tools. So finally, in the third scenario, what is the best choice? This is a tricky question, and the answer is most obvious, that is, use both. The truth here is that although Kubernetes can use other container sources and runtimes, it is designed to work well with Docker, and much of Kubernetes documentation was very well written with Docker in mind. The most basic Kubernetes use case is Kubernetes plus Docker, and Kubernetes includes Docker-centric tools such as Compose, which converts Docker Compose commands and settings so that can be used by Kubernetes. For its part, Docker has embraced Kubernetes and has in fact offered its very own integrated Kubernetes distribution. So the bottom line is that Kubernetes and Docker are both industry standards in their respective core areas of expertise, and together they provide a well-integrated platform for container management, deployment, and orchestration at scale. It was never really a question of Kubernetes versus Docker. It was always Kubernetes and Docker, and today this is even more true.
With the comparison done, we will move to the Kubectl and Minikube to learn about essential tools for managing Kubernetes locally.
What is Kubectl? So the Kubectl is simply a command line interface. So the Kubectl command line tool lets you control these Kubernetes clusters that you create. Now for configuration, Kubectl looks for a file named config in the home.kube directory. Here you can specify other kubeconfig files by setting the kubeconfig environment variable or by setting the kubeconfig flag. This overview covers Kubectl syntax, describes the command operations, and provides various common examples. Now, if you look at the syntax of the screen, which is used to run Kubectl commands from your terminal window, you can see that it is simply Kubectl, command, type, name, and the flags, where command specifies the operation that you want to perform on one or more resources. For example, if you want to create, get, describe, delete, any of that. The next one is type, which specifies the resource type. Resource types are case sensitive, and you can specify the singular, plural, or abbreviated forms. Now, for example, you can, type in the following commands, which produces the same output. For example, kubectl get pod1, kubectl get pods pod1, kubectl get po pod1. All of these commands produce the same output. Name, on the other hand, specifies the name of the resource. Names are case sensitive. Now, if the name is omitted, details for all the resources are explained or displayed. For example, kubectl get pods will really give you an entire overview of all the pods that are running on your cluster. When performing an operation on multiple resources, you can specify each resource by type and name or specify one or more files. To group resources if they're all the same, you can use the syntax type1, name2, etc. And to specify multiple resource types individually, you can just use the syntax type1/name1, type1/name2, type2/name3, etc. Flags, on the other hand, specifies optional flags. For example, you can use the -s or -- server flags to specify the address and port of the Kubernetes API server. Now that we know what is Kubectl, which is just a command line tool that lets you control Kubernetes clusters, and also its syntax in detail, let's move ahead and talk about what is Minikube. So Minikube is a tool that lets you run Kubernetes locally. Minikube runs on a single node Kubernetes cluster on your personal computer, which includes Windows, Mac OS, and Linux PCs, so that you can try out Kubernetes or for daily development work. All you need is Docker or similarly compatible container, or also a virtual machine environment, and Kubernetes is a single command away. That is, you can use Minikube start to get it running. The advantages of Minikube is that it supports the latest Kubernetes release, it is cross-platform, and it can be deployed as a virtual machine, a container, or on a bare metal. It also contains multiple container runtimes. So Minikube is basically a tool that lets Kubernetes run on your local machine without any installation except for the Minikube library. So in summary, Minikube is a tool that lets you use Kubernetes on your local machine without any installation except for the Minikube library. It takes advantage of your local hypervisor and launches a virtual machine that runs Kubernetes in a single node. Now, to install the Minikube and Kubectl, you can get the latest release or build from the official website. So without much ado, let's go and install them. So now currently I'm on my Oracle VM VirtualBox and we are working on Ubuntu. So we'll be installing the Kubectl on Ubuntu, and we'll be installing using native package management, that is Debian-based distributions. So the first thing that we're going to do is we are going to update the apt package index and install packages needed to use the Kubernetes app repository. And for that, I am going to type in the command sudo apt get update. Okay. So I have the list of commands already on my notepad. So I'm just going to copy this command and I'm going to paste it. So new packages will be installed and also the existing ones will be upgraded. So once the installations and updates have been done, I'm just going to clear the screen. And what I'm going to do now is I'm going to download the Google Cloud public signing key. Okay, and for that, we're going to use this command, followed by which we can add the Kubernetes apt repository. So I'm going to copy and paste this command. So finally, I'm going to update the app package index with the new repository and install kubectl. Now, once it's successfully installed, in order for kubectl to find and access a Kubernetes cluster, it needs a kubeconfig file, which is created automatically when you create a cluster using kubeup.sh or successfully deploy a Minikube cluster. Now, by default, kubectl configuration is located in the .kube/config. So now that we've installed kubectl successfully, I'm going to test to ensure the version that we've installed is up to date. So for this, I'm going to execute the command kubectl space version space -- client. Now we can see the Git version and we can see the major version. All of the information is given here. We have successfully installed kubectl. Now let's clear the screen. So now that we've installed kubectl, let's move ahead and install Minikube to run a local Kubernetes instance. So as we've already talked about it, Minikube is a tool that lets you use Kubernetes on your local machine without any installation except for the Minikube library. You will have to install Docker and you'll have to install VirtualBox before you can install Minikube. Otherwise, Minikube will not work. So once you do all of that, then all you can do is you can just install the Minikube library into your system. So for this, we're just going to use these commands. I'm just going to copy them and paste them. And once Minikube is installed, you can verify the version that is running. The following command, that is Minikube version. You can see that we've installed version v1.20.0. So you can start the Minikube by using the command sudo minikube start. Now, once the startup phase has finished, which will take some amount of time, your Kubernetes client, that is kubectl, will have a Minikube context and will automatically start using this context. So you can also see that kubectl is configured to using Minikube cluster and default namespace by default. We'll talk about namespace in a bit. Now let us just check what nodes we will have in our cluster, which will return the Minikube hostname. And for this, I'm just going to clear my screen and type in the command sudo kubectl get nodes. You can see there is a node Edureka. Its status is ready. So let us check out each of the commands that are available, some of the basic commands that are available. So first one is the get command. So what it does is the first command, it lists all the pods in PS output format. Okay. There is another type of command which lists all pods in PS output format with more information such as the node name. For that, we can just use the command kubectl get pods -o wide. Currently, we do not have any resources in the namespace, so it's not going to display any. Now, to test that kubectl can authenticate with and access your Kubernetes cluster, you can use the cluster-info command. So you can type in the command sudo kubectl cluster-info. And if kubectl is successfully authenticated with your cluster, you should see the following output. So kubectl is configured using kubeconfig configuration files. And by default, kubectl will look for a file called config in the home/.kube directory. Now to view your kubectl configuration, you can use the view sub command. So I'm just going to type sudo kubectl config space view. And this will give you the API version that is V1, the cluster, that's Minikube. So you can see the API version, that is V1, you can see the clusters, you can see the contexts, and you can see the correct context, kind, preferences, users. Okay, now I'm just going to clear the screen. Now to fetch a list of clusters defined in your kube config, you can just use the get-clusters command. So I'm just going to type in sudo kubectl config get-clusters. So the output will be the list of clusters that is defined in our kube config file. And as you can see that in the output is the Minikube. So you can also delete a cluster from your config using the delete-cluster command. I'm not going to show you the output of this, but I'm just going to type in the command. Okay, so what this does is it only deletes the cluster from your config file. Okay, it does not delete the actual Kubernetes cluster. So this is really important to know. Now moving on, you can also see a list of all the configured contexts. For that, you can just use the command config get contexts. And what it does is it gives you the name of the cluster and the authentication information and the namespace. Okay, this is like just, it gives you like a list of contexts that are available. So I haven't explained you what exactly a context is. A context in Kubernetes is an object that contains a set of access parameters for your cluster. It consists of a cluster, namespace, and user triple. Contexts really allow you to quickly switch between different sets of cluster configurations. If you want to see your current context that you are working on, you can just use the current context command. Okay, and you can see that we are currently on the context Minikube. Okay, now to set a particular context, you use the set context command. So for this, I'm going to type in the command set context1. So I'm just going to name my context1, cluster -- cluster is equal to your cluster name. I'm just going to name this cluster1. User is equal to user1. And you can also have a namespace. We know that we have one namespace that is our default namespace, right? So I haven't really talked about namespaces either. So let me explain it to you now. So Kubernetes uses namespaces to organize objects in the cluster. You can think of each namespace as a folder that holds a set of objects. By default, the kubectl command line tool interacts with the default namespace. Now, if you want to use a different namespace, you can pass kubectl the -- namespace flag. So we're going to set a context, and we are also setting the namespace for that particular context. So I hope this is clear. So you can see that context1 has been created. Now you can switch between contexts with the use context command. So for that, I'm just going to type use context. And I'm just going to type the context name. So we created a context that was named context1. So I'm just going to switch to that. So it says switch to context1. If you want to check the current context, we can just use the current context command, and you can see that it has been switched to context1. Now I want to switch back to Minikube. I'm going to do that. And it says switch to context Minikube. That's great. You can also check out the list of contexts using the get context commands, and you can see that we have two, that is Minikube and context1, and the current one is where the star has been placed to. Okay, that is Minikube. Now, if you want to delete a particular context, we can do that. Okay, we will use the sudo kubectl config delete context and the context name. So we'll just name it context1. Okay. Now it says deleted context1 from the particular location. We can also view the contexts that are currently present, and we have only one, that's Minikube. So that's great. This is for contexts. So I'm going to repeat this again. A context in Kubernetes is an object that contains a set of access parameters for your cluster. I hope that's clear. Now let's go and check out namespaces. Okay, is basically again an abstraction that allows you to subdivide your cluster into multiple virtual clusters. Now, by using these namespaces, you can divide cluster resources among multiple teams and scope objects properly. Now, for example, if you have a development namespace for development and test workloads and a production namespace for production workloads, so you can really divide the cluster resources among these, two teams that we have. I'm going to clear the screen. So what now we're going to do is we're going to fetch and print a list of all the namespaces in your cluster. And we are going to use the get namespace command. So sudo kubectl get namespace. So you can see the output as default, kube node lease, kube public, and kube system. Okay, now if you want to set a namespace for your current context, our current context is Minikube, you can use the set -context space -- current command. I'm just going to show that. And you can see the context Minikube has been modified. Okay. Now, if you want to create a namespace, you can just simply use the create namespace command. So I'm going to use the command sudo kubectl create namespace 2. That is, namespace 2 is the namespace name that you would like. You want it to be 3, you want it to be 4. That's all up to you. I'm just going to name this namespace 2. And you can see that namespace 2 has been created. Okay. Now we'll just list out all the current namespaces. And you can see that the namespace 2 has been created and it is active and it has been created 11 seconds ago. Now you can also delete a namespace by using the delete namespace command. Deleting a namespace will delete everything in the namespace, including running deployments, pods, and other workloads. Only run this command if you're sure if you'd like to kill whatever's running in the namespace or if you're deleting an empty namespace. So you have to be aware of this. So what I'm going to do is I'm going to delete namespace and I'm going to delete namespace 2. Okay. You can see that namespace 2 has been deleted. That's great. And I'm just going to view the namespaces that are currently there using the get namespace command. And you can see that our namespace 2 has been deleted successfully. I'm going to clear the screen. Now, if you want to fetch all pods in a given namespace or to perform other operations on resources in a given namespace, make sure you have to include the -- namespace flag. Okay. So say that I want to get the pods of namespace default. And it says no resources are currently found in the default namespace, which is fair enough. So I'm just going to clear my screen now. And we will be talking about another command, the API-versions command. So what this does is it prints the supported API versions on the server in the form of grouper version. Okay. And for that, we're just going to type the command sudo kubectl API-versions. And this just gives the supported API versions on the server. Okay. So these are some of the most basic commands that are available. We used create, we used get, delete, we used describe, API versions, cluster info, and there are a lot more. But to just get started and to just understand how Kubernetes works, you will have to start off from the basics because this is a very vast topic. I think that you cannot go into detail that easily. You will need to have some experience over time with all of these commands that you use and their respective flags and their respective parameters that are involved here. Now let's move ahead to the next part of this session and talk about Minikube dashboard. Now the dashboard is a web-based Kubernetes user interface, and you can use it to deploy containerized applications to a Kubernetes cluster. You can also use it to troubleshoot your containerized application, manage cluster resources, get an entire overview of applications running on your cluster. You can also create or modify individual Kubernetes resources such as deployments, jobs, etc. For example, you can scale a deployment, initiate a rolling update, restart a pod, or deploy new applications using a deploy wizard. Now to access the dashboard, you simply use the command minikube dashboard, and this will enable the dashboard add-on and open the proxy in the default web browser. It is worth understanding and noting that web browsers generally do not run properly as a root user. So if you're in an environment where you're running as root, see the URL only option. To stop the proxy, abort the started process using Ctrl+C. So if you don't want to open a web browser, the dashboard command can also simply emit a URL, minikube dashboard -- URL. Now let's switch back to the VM and access the dashboard. So first what we're going to do is we're just going to type the command minikube dashboard. Now once the dashboard has been enabled, you will be automatically redirected to the dashboard page on your browser. So on top you can see there's an overview button, and here you can see the workload, service, config and storage, cluster, settings, about, custom resource definitions, all of that. You can also see the workload status where you have deployments, the pods, and also the replica sets. Now to create an application, you can just click the plus button in the top right corner, and which will give you three options that says create from input, create from file, and create from form. Here you can specify the application name and also specify the Docker image that you want to use. So after all of that is done, you can just click on the number of pods, the service, and then finally you can click the deploy button, which will be presented with a new view that shows deployments and replica sets. And after a bit of time, you will also see a pod. So these are some of the key API primitives. So I'm just going to create from form. I'm going to type Redis, and also the container image will be Redis. Okay, and then I'm going to click on the deploy option. If you want to view the pods, you can just click on the pod option. If you want to view the replica sets, you can click on the replica sets option, and you can see the replica sets that has been created. You can also view the deployments by clicking on the deployments option. So we can switch back to the terminal now, and we can view all of this using the command kubectl get pods, rs, that is replica sets and deployments. You can see that the Redis pod has been created, and the replica set Redis has been created, and also deployment has been created for Redis. Now your Redis pod will be running the Redis server. So you can see that using the logs command. And I'm just going to copy this. So here you can see all of the information, that is the version of Redis. You can also see the running mode and the port that it's currently activated on, and if it's ready to accept connections. So with this, we have discussed what is the dashboard and how to make the maximum use of the dashboard. Now let's switch back to our terminal and clear this. So what we're now going to do is we're going to learn how to manage your clusters. You can pause Kubernetes without impacting deployed application using the mini pause command. You can also stop the cluster by using the minikube stop command. As the same way we started the cluster using the minikube start option, you can also stop it. Okay. You can also increase the default memory limit by using the config set memory command. Okay. You can also browse the catalog of easily installed Kubernetes service. You can do this by using the command sudo minikube add-ons list. You can browse through the Kubernetes services. You can see that the dashboard has been enabled, the default storage class has been enabled, also the storage provisioner has been enabled, and the REST ingress and log viewer, ambassador, autopause, all of that has been disabled as of now. We aren't using it. If you want to delete all of the minikube clusters, you can use the command minikube delete -- all. I'm going to clear the screen. Now, if you want to view the various commands in minikube, you can just simply type the command minikube -- help, and this will list all of the commands that you can really use. You can see that there's the configuration and management commands like add-ons, config, profile. There are also advanced commands. You also have troubleshooting and debugging commands like describe, cp, authorization, which inspects authorization, and many other commands that you can use. We will now create a Kubernetes deployment named Hello Minikube using an existing image named Echo Server, which is a simple HTTP server with the port set to 8080 using the -- port flag in our command. So you can see that I have typed out the command sudo kubectl create deployment Hello Minikube image is equal to k8gcr.io/echo server 1.10. And it says that Hello Minikube has been created. Now to access the deployment, you will have to enter the command expose deployment. The -- type is equal to node port flag specifies the type of the service. So you can see that the service Hello Minikube has been exposed. Now to verify this expose, you just type in the command kubectl git deployments. You can see that it is ready and up to date and also available right now. Now that the deployment has been exposed, I'm just going to clear the screen. Now you can just use the kubectl get services command, and you can just check out all of the services that are currently running. Now, if you want to delete this service, you can just simply use the kubectl delete service Hello Minikube. And once that is done, you can see the services that are currently present and you do not have Minikube in it. And if you want to stop Minikube, you can simply type in the command sudo minikube stop. Once that is stopped, you can also delete Minikube by using the minikube delete command. So once you have Minikube up and running, the following tips can really help you get the most from the environment. First one is to sharing your Docker daemon. A Docker daemon is included with Minikube. This is the same daemon you use for Docker-only deployments and can be shared between Minikube and Docker. Now, if you share, you can speed up your local tests and make any Docker builds you create available to Minikube. The second one is using add-ons. Now, add-ons we already saw in the demo session. They're just the extensions of Minikube that you can enable or disable to provide access to advanced features. Add-ons can enable features like the dashboard, registry, credentials, or ingress. You can also use add-ons that are already available, or you can use customizable add-ons by modifying the associated YAML file. The last tip is to gain access to host files. Now, if you want to make files on your host system available to containers running inside Minikube, you have a couple of options. First, you can use Minikube's mount command, which uses a 9p file system implementation under the covers to expose host files to the Minikube VM. Now, the Minikube 9p mounts have some performance impacts compared to hypervisor native mounts and work best for directories with just a few files. As an alternative, some hypervisors automatically mount a host system directory and make it available for use inside the Minikube virtual machine. Now, these special mount points that we're talking about provide superior performance to the user-definable Minikube 9p mount points. So these are a good option if you need to expose a large collection of files to the containers you're testing inside Minikube. Unfortunately, the hypervisor guest mount points differ depending on the host system OS and hypervisor you are using. So these are some tips that you will have to really remember when you're using Minikube or when you're starting to use Minikube. Now we'll go ahead and check out a case study of how Kubernetes has helped Booking.com achieve their business goals. So the problem in 2016 was Booking.com migrated to an OpenShift platform, which really gave product developers very fast access to infrastructure. Now, because Kubernetes was abstracted away from the developers, the infrastructure team became a knowledge bottleneck when challenges arose. So they were trying to scale that support that wasn't sustainable. So after almost a year of operating with OpenShift, the platform team decided to build its own vanilla Kubernetes platform and really asked developers to learn some Kubernetes in order to use it. They believe that it is not a magical platform and they're not claiming that you can just use it with your eyes closed. Here, developers really need to do some learning and they're going to do everything to make sure that they have access to that particular knowledge. That was the solution that came up with Booking.com. Now, despite the learning curve, there has been a great uptick in the adoption of the new Kubernetes platform. Before containers, creating a new service could take a couple of days if the developers understood Puppet, or weeks if they didn't. So Puppet is the tool here which they used. On the new platform, on the other hand, it could really just take as few as 10 minutes. About 500 new services were built on the platform in the first 8 months. Booking.com has a long history with Kubernetes. In 2015, a team at the travel platform prototyped a container platform based on Mesos and Marathon. Impressed by what the technology offered, but in need of enterprise features at its scale, the site handles more than 1.5 million room night reservations a day on average. The team decided to adopt an OpenShift platform.
Let's take up another question. What is Minikube primarily used for? And the options are running a Kubernetes cluster locally, deploying Kubernetes on the cloud, managing container image, or scaling Kubernetes cluster. And if you know the answer, please leave it in the comment section below. Next, we will cover Kubernetes YAML to learn how to write and use YAML files for Kubernetes configuration.
What is YAML? YAML's official definition is a human-friendly data serialization standard for all programming languages. YAML's main advantage over other similar formats like JSON or XML is its human readability. That is, it was specifically designed to be easily readable and editable by humans. This makes it very ideal for dual human-machine use cases such as log files, configuration files, inter-process messages, and in this case also for Kubernetes config and definition files. Now let us discuss some of the most common use cases as to why YAML files were really created. Firstly, YAML files are used as configuration files, log files, inter-process messaging, cross-language data sharing, object persistence, and even to work on complex data structures. These are the very few common use cases as to where YAML files can be used. Now that we know why YAML was really created and some of its common use cases, let's move ahead and talk about why should you use YAML. Firstly, YAML files are extremely readable by humans. They're very expressive and extensible. Even a small child going to school, if you show him or her a YAML file, they could identify few things and how the structure is completely laid out. It's really that easy. And the second reason as to why you should use YAML files are because they're very easy to implement and use. The third benefit is that they're easily portable between programming languages. So if you want to switch from one language to another, if you want to create these YAML files in Java, for instance, you can easily port this YAML file to Python. Okay, so it's very portable, and that's the biggest advantage of YAML files. The next advantage is they match the native data structures of agile languages. So that's another advantage. That is why porting between programming languages is also possible, because it matches the native data structures. The fifth important benefit is that you can perform maintenance. You can really, maintainability among these files are extremely easy. The last advantage is that they are flexible. Now let's move ahead and talk about the structure of a YAML file. There are three building blocks of a YAML file. The first one is a key value pair. The second one is arrays and lists. And the third one is dictionary or map. The basic type of entry in a YAML file is of a key value pair. After the key and colon, there is a space and then the value. List, on the other hand, would have a number of items listed under the name of the list. The elements of the list would basically start with a dash. They can be a number of lists. However, the indentation of various elements of the array matters a lot. Dictionary or map, on the other hand, is a much more complex type of YAML file, which is a much more complex type of YAML file that would be a dictionary and a map. Now let me explain this with an example. Key value pair could be fruit colon apple, vegetable colon radish, liquid colon water, meat colon goat. Arrays would be a group of similar items, like fruits would be orange, banana, mango, vegetables would be potato, tomato, carrot. Dictionary or map would be how these items within an array or list are classified. So banana can have three features that are calories of 200, fat of 0.5 grams, carbs of 30 grams. Grapes, on the other hand, could have calories of 100, fat of 0.4 grams, and carbs of 20 grams. So once the structure of a YAML file is clear, let's move ahead and talk about some of the basics of YAML. So as you can see, it is difficult to escape YAML if you're really doing anything related to many software fields, particularly Kubernetes, SDN, and OpenStack. YAML stands for yet another markup language, which is a human-readable text-based format for specifying configuration type information. So usually when you're learning anything about Kubernetes or anything related to deployment, you would first learn how to create a pod and then a deployment, right? So when you're defining a Kubernetes manifest, YAML gives you a number of advantages that includes convenience and flexibility. Firstly, you will no longer have to add all your parameters to the command line. When defining a Kubernetes manifest, YAML gives you a number of advantages, including convenience, maintenance, and flexibility. So in terms of convenience, you'll no longer have to add all your parameters to the command line. And when you talk about maintenance, YAML files can be added to source control, such as a GitHub repository, so you can track your changes. In terms of flexibility, you'll be able to create much more complex structures using YAML than you can on the command line. YAML is basically a superset of JSON, which means that any valid JSON file is also a valid YAML file. So on one hand, if you know JSON and you are only ever going to write your own YAML, you're all set. On the other hand, that's not very unlikely, unfortunately. Even if you're only trying to find examples on the web, they are most likely non-JSON, that is YAML, so we might as well get used to it. Still, there are many situations where the JSON format is much more convenient, so it is good to know that it is available to you. Fortunately, YAML is relatively easier to learn, and there are only two types of structures you need to know about it. The first one is lists, the second one is map. That's it. You might have maps of lists and lists of maps and so on. But if you've got those two structures down, you're literally all set. That's not to say that there aren't more complex things to do, but in general, this is all you need to get started. So let's move ahead and talk about YAML maps. Let's start looking at these. Maps really let you associate name-value pairs that we've already discussed, which of course is convenient when you're trying to set up configuration information. For example, you might have config file that starts like API version v1, kind as pod. The first line is basically a separator and is optional unless you're trying to define multiple structures in a single file. From there, as you can see, we have two values, v1 and pod, mapped to two keys, API version and kind. This kind of thing is pretty simple, of course, and you can think of it as in terms of JSON equivalent API version as to 1 and kind as pod. So in the YAML version, the quotation marks are optional. So in the YAML version, you don't really have to add the quotation, it's optional. The processor can tell that you're looking at a string based on the formatting. You can also specify more complicated structures by really creating a key that maps to another map rather than a string. In this case, we have a key, metadata, that has as its value a map with two more keys, names and labels. Okay, the labels key you can see itself as a map as its value. You can nest these as far as you'd like to. The YAML processor knows how all of these pieces relate to each other because we have intended the lines. In this example, we've used two spaces for readability, but the number of spaces doesn't really matter as long as it's at least one and as long as you're consistent. For example, names and labels are at the same indentation level, so the processor knows they are both part of the same map. It knows that an application is a value for labels because it's indented further. One thing you'll have to know is never use tabs in a YAML file. So you could imagine the JSON file of this, right? So I hope maps are clear. So now that we've understood about maps, let's talk about YAML lists. YAML lists are literally a sequence of objects. You can see this example. We have arguments sleep, 1000, message, bring back Firefly. You can have virtually any number of items in a list, which is defined as items that start with a dash indented from the parent. And of course, members of the list can also be maps. So in the JSON file, this would be arguments sleep with quotation, 1000 with quotation, message with quotation, bring back Firefly with quotation. And of course, members of this list can also be maps. So you can have list of container objects, each of which really consists of a name, an image, and a list of ports. Each list item under ports is itself a map that lists the container port and its value. So now that we know maps and lists quite in detail, let's move ahead and talk about YAML usage in Kubernetes. So having seen the advantage and basic building blocks of a YAML file, let us understand how YAML is used in Kubernetes. The Kubernetes resources are created in a declarative way, thus making use of YAML files. Kubernetes resources such as pods, services, and deployments are really created by using the YAML files. The example here contains both basic and advanced specifications. Firstly, let us talk about the various fields that are available. The first one is replicas. This tells Kubernetes how many pods to create during a deployment. Modifying this field is a very easy way to scale a containerized application. The second one is in spec strategy type. So suppose there is another version of the application that needs to be deployed, and during the deployment phase, you need to update without facilitating an outage. The rolling update strategy allows Kubernetes to update a service without facilitating an outage by proceeding to update pods one at a time. Again, under spec, under strategy, you can see max unavailable. This is the maximum number of pods that can be unavailable during the rolling update. Also, the max surge option gives you the maximum number of pods that can be scheduled above the desired number of pods. Now, again, in specification, you can see minute ready seconds is an optional integer that really describes the minimum number of seconds for which a new pod should be ready without any of its containers crashing for it to be considered available. Revision history limit is an optional integer attribute that you can use to tell Kubernetes explicitly how many old replica sets to retain at any given time. Under metadata labels, you can add labels to a deployment specification, whereas the selector under spec is an optional object that tells the Kubernetes deployment controller to only target pods that match the specified labels. Thus, to only target pods with the labels of application and deployer, you can make the following modification to our deployment YAML. You can see from the explanation of the various fields that YAML files can really help you maintain and control Kubernetes resources in a very declarative way. YAML is on its way to be considered as a de facto standard for configuration files. So in the next part of the session, let us learn how to create a pod using YAML. Okay, so now what we're going to do is we're going to be creating a Kubernetes pod using the YAML file. There are some prerequisites. You will have to have kubectl and Minikube installed on your VM. Okay, so currently I'm working on my Linux virtual machine and I already have my kubectl and Minikube installed successfully. To check if kubectl has been successfully installed, I'm just going to execute the command kubectl version -- client. This will just give me an idea if the kubectl client version has been installed successfully, and you can see that there is the version info, the git version, git commit, go version, etc. So we know that kubectl is installed in my VM. Now, if you want to start the default Minikube cluster, all you have to do is execute the Minikube start command. For this, I'm just going to type Minikube start. This command will automatically start the Minikube cluster for me in less than a minute. Now that we have successfully configured our Minikube cluster, so what we can do is we can just clear the screen and let's move ahead and create our YAML file. So the first thing that we're going to do is we're going to learn how to create a Kubernetes pod using the YAML file. Now, to create a Kubernetes pod with this file, you first need to create an empty file and assign it the necessary access permission, and then you define the necessary key value pairs, that is lists. The important lists are the API version, the kind that is basically the pod, its name, and the containers that are present within the pod. So now what we're going to do is we're going to create a file that is named pod1.yml, okay? So now what we're going to do is we're going to code the YAML to create a pod that has been named new pod. So first I'm going to specify the version. The API version is v1 and the kind will be pod. The metadata will specify the metadata. Its name will be new pod. Labels. The labels will be app and environment, and this will be test. Once that is done, we're going to execute the specification. Here we have containers, and here the name will be test container and image will be nginx. I'm just going to specify a dash. I'm just going to save this file, and once I've saved, I'm just going to use the kubectl apply command pod.yml. So you can see that there's a new pod that has been created, and once that is successfully executed, you're going to get new pod has been created. So now to see the state of the pod, if it is up and running, we're just going to execute the kubectl get pods command, and you can see that there are many pods that have been created in the past. So you can see that the new pod has been created 27 seconds ago, and its status is container creating. Okay. After some time, if you execute the same command, you can see that the new pod is in the running state. So basically, this file is really important. Taking it apart one piece at a time, we can start with the API version. Here it's just V1. When we need to get to deployments, we will have to specify different version because deployments do not really exist in V1. Next, we are specifying that we want to create a pod to hold our application or cloud service. We might specify instead a deployment, job, service, and so on, depending on what you're trying to achieve. Moving on, we specify the metadata. Here we're specifying the name of the pod as well as the label we'll use to identify the pod in Kubernetes. Okay, then we will finally configure the actual objects that really make up the pod. Okay, the spec property includes any containers, memory requirements, storage volumes, network, or other details that Kubernetes needs to know about, as well as properties such as whether to restart the container if it fails, etc. All of that specifications can be mentioned here. So we have a fairly minimal definition here, that is a name, that is the front end, and the image on which it's based on, that is NGINX. And if you want to mention one port on which the container will listen internally, you can also mention that. You can also move ahead and specify more complex properties such as a command to run when the container starts, arguments it should use, a working directory, or whether to pull a new copy of the image every time it's instantiated. You can also specify when deeper information such as the container's exit log, all of that can be specified here. So now that we have finished the first part and created our first pod using the YAML file, let's move ahead to the next part of the session. Okay, so now what we're going to do is we're going to be creating a deployment using the YAML file. So let's quickly switch back to our terminal and get started. So now what we're going to do is we are going to run an application by creating a Kubernetes deployment object, and you can describe a deployment in a YAML file. For example, a YAML file can describe a deployment that runs the NGINX 1.14.2 Docker image, right? So that's what we're going to do. We're going to create a deployment. So I'm just going to clear my screen. So what I'm going to do is I'm going to name this as deployment.yml. Okay. And once I create this, I'm going to just add all of its fields, right? So firstly, I'm going to add the API version, that is apps/v1. Then the kind will obviously be a deployment. Then I will specify the metadata field. Here I'm going to specify its name as NGINX deployment. Once that is done, I'm just going to mention the spec. So here I have the field selectors and then match labels under it. And the app here is going to be NGINX, right? Okay. After this, I will set the replicas to 2. So what this really does is it tells deployment to run 2 pods matching the template. And now I'm going to specify the template field. Under this, I'm going to specify the metadata field, followed by labels. And here we're going to specify the app again, that's NGINX. I'm going to give specifications to the containers. And here the name NGINX, image is going to be NGINX 1.14.2, and the ports. And then under the ports field, we're just going to specify the container port, which is 80. Once we've completed writing the code in the YAML file, what we're going to do is we are quickly going to save this file and we are going to create a deployment based on the YAML file, right? So for this, I'm simply going to use the kubectl apply command. With the help of the F flag, I'm just going to create this deployment, right? So let's do it. You can see that the deployment has been successfully created. You can also, really describe this information, right? You can display the information about the deployment by using the kubectl describe command. So I'm just going to describe the deployment, Nginx deployment. And you can see that the output is available. You can see its name, that is the Nginx deployment. You can see the namespace, it's been created in the default namespace, the labels, if there are any annotations, the selector, the replicas, there are 2 right now, and the strategy type is rolling update. All of the detailed information about this deployment has been given or described after this command has been executed. So once that is done, what we can do is we can also scale the application by increasing the replica count. For this, you can also create a scale YAML file and then apply the new YAML file, then verify that it has pods. So if you want to check out the number of pods that are currently present in the deployment, what you can do is you can use the kubectl get pods command. Okay. And you can specify the L flag, assign app to Nginx. So you can see that I've created 2 pods, right? That is 2 minutes ago, 2 minutes 30 seconds ago, and the status is running. That's great. So this is up and running, we know that. So now what you can do is we will clear the screen and we will check our pods IPs. Okay. So now what we're going to do is we're going to use the kubectl expose command, and we are going to be exposing the deployment that we've just created. And the deployment name is Nginx deployment. So that's what I'm going to mention. And you can see that the Nginx deployment, that is the service that we've created, has been exposed successfully. Now, what I'm going to do is I'm going to open the service file, the service.yml file, using the vim command. So I'm just going to write the code. So firstly, we're going to specify the API version, that is v1. Then I'm just going to mention the kind, that is service. So this is a service file, so that's the kind. And in the metadata field, so I'm just going to mention the various tags that's associated. First, we will write the name. The name will be Nginx deployment. Then we have the labels, and under this, we have to specify the run tag. Here, we're going to specify Nginx. Then in the specifications field, we are going to mention the ports. And under this, you can see that the port we're going to specify is 8080, followed by the protocol, which is going to be TCP. And in the selector field, we're going to specify the run tag. And this also will be Nginx. I'm going to save the service file. So once it's done and saved successfully, so using the kubectl get command, so we're just going to see the list of supported fields in the service definition. And my name is Nginx deployment. So that's what I'm going to really work on. So you can see that you have the type, that is cluster IP, the IP address is given, the port is 80 TCP, the age is 9 minutes 28 seconds. So you must be aware that a service is backed by a group of pods, and these pods are exposed through endpoints. The services selector will be evaluated continuously, and the results will be posted to an endpoint object, which is also named as Nginx. When a pod dies, it is automatically removed from the endpoints, and new pods matching the services selector will automatically get added to the endpoints. And if you want to check the endpoints and note that the IPs are the same as the pods created in the first step, we can just use the describe svc command and check it out. And you can see that the name is Nginx here, namespace is default, the app is equal to Nginx. You have the selector, all of the information is given here. And the endpoints is 172.17 and so on. Now we're just going to execute the get command. You can see that both of these endpoints are the absolutely same, right? The Nginx and the service that we've created. Now we should be able to curl the Nginx service on the cluster IP's port from any node in your cluster. So now I'm just going to clear my screen. So this is all you have to know to get started with the Kubernetes YAML tutorial. Okay, so now what we're going to do is we are going to be deploying a service in an application. So for this, firstly, what we have to do is we'll have to create a YAML file, and I'm just going to create a deploy.yml file. And as you can see, the file opens. So here I'm just going to type out the entire code. So you can run an application by creating a Kubernetes deployment object, and you can describe a deployment in a YAML file. So now let me explain this code, okay? We start with the API version. Here it is apps/v1. So next we are specifying that we want to create a deployment to hold your application or service. We might specify instead a job, pod, service, and so on that we already know depending on what we're trying to achieve. Next, we specify the metadata. Here we'll be specifying the name of the pod as well as the label we'll use to identify the pod to Kubernetes. And then we will configure the actual objects that make up the pod. The spec property includes any containers, memories, replicas, all of that. So here we have a simple, fairly minimal definition and name for the spec container. In the spec property, we have containers. That is a name and an image and different ports. You can also specify more complex properties such as a command to run when the container starts, arguments it should use, a working directory, all of that. Okay, and then moving on to the next part, we add 3 dashes, and then in the next part, we'll mention the service. So you can see that the API version is v1, the kind is service. We're creating a metadata where the name of the metadata is Nginx. And using the spec property, we're going to specify the type, which is node port, a selector where the app is named node port, and ports by default and for convenience, the target port is set to the same value as the port field. So the port is set to 80, the target port is also set to 80. And we also have an optional field. For convenience, the Kubernetes control plane will allocate a port from a default range. So the node port here is specified as 3007. We're quickly going to save the file. Now that we've talked about the YAML file in detail, let's go ahead and save this. Now, once the file has been saved, let's use the kubectl apply command. You can see that the deployment and the service has been created. And what we're going to do is we're going to use the kubectl get server. And you can see that Nginx on port with cluster IP 10.99.84.28 has been successfully created, and it's been deployed on port 30007. So what I'm going to do now is I'm going to open a web browser. I'm just going to add the external IP on which my instance is running on 30007, and you can see that the application has been successfully created. You can see that there's welcome Nginx and there's some more details that has been given. So just by creating one YAML file, we can add the application and the service and deploy it all together. So this is how easy it is to work with Kubernetes using YAML files.
Now let's take up a quiz question. In Kubernetes, what is YAML primarily used for? And the options are writing configuration files, running command line tools, creating container image, or monitoring applications. If you know the answer, please leave it in the comment section below. Having learned YAML, we will explore Kubernetes networking to understand how network setup and service discovery work.
Anybody working with Kubernetes must also have an understanding of Kubernetes cluster, as that gives the basics for networking. So let me tell you what exactly Kubernetes cluster is. Now, the basic fundamental behind Kubernetes is that we can enforce what's called a desired state management, and really what that means is that I'm going to feed a cluster service in a specific configuration, and then it will be up to the cluster services to go out and run that configuration in my infrastructure, right? So one of the main components of the Kubernetes clusters is the API that sits in front of all of these services. So this is like the building block of a system, and the second building block of a system is a worker. So what is a worker? Well, a worker is just like a container host. So one unique thing about the worker or a container host in Kubernetes environment is that it does have a kubelet process, and that is responsible for communicating with the Kubernetes cluster services, and this whole setup with the workers and APIs and the pods is known as Kubernetes cluster. Now, let me explain you with an example here. So you can see this deployment file, right? So this deployment file has all the configuration that is required to feed into the cluster services. So it has pods, it has replicas, each pod has various container images which are going to be fed to the cluster services, and then it will be up to the cluster services to divide the pod and replicas into the worker nodes. So in this example over here, we have two pods, with the first pod having 2 container images and 3 replicas, and the second pod having only 1 container image and 2 replicas. Now, once this configuration is fed to the Kubernetes cluster services, it will be up to the cluster services to schedule these pods and the workers. So as you can see over here, the worker 1 has pod 1 replica 1 and pod 2 replica 2. The worker 2 has only 1 pod with 1 replica, and the third worker again has 2 pods with 2 replicas. So this can depend on the cluster services completely. Now, the main aim of cluster services is to make sure that the configuration is running across all of the containers or the workers. Now, you must be knowing about Docker, right? When Docker was there, why did Kubernetes come up? Because this has an approach of networking in a different way. So there are mainly 4 distinct networking problems to solve with Kubernetes that we have to deal with. The first one is the container-to-container communication. The second one is the pod-to-pod communication. The third one is pod-to-service communication. And the fourth one is external-to-service communication. So don't worry guys, I'll discuss each one of these communications in this session. So let me brief you about each one of them one by one. Now, container-to-container communication is basically the communication between 2 container images. The pod-to-pod communication is the communication between 2 different pods having various images and the replicas. The pod-to-service communication is how a service enables a pod to communicate with any other pod. And external-to-service communication is how an external-to-service communication is how something out of the cluster can communicate something which is inside the cluster. Now, before I get into the depth of all these, let me tell you the fundamental requirements of any network implementation in Kubernetes. So all the containers can communicate with containers without NAT. All the nodes can communicate with all the containers without NAT, and it's also vice versa. Not only this, but the IP that the container sees itself is the same IP that others see. So these are some fundamental requirements that you need to understand before you start with Kubernetes networking. So now, as I was talking so much about Kubernetes networking, let me tell you what Kubernetes networking is all about. So Kubernetes networking mainly deals with the communications between pods, services, and external services to the one in clusters. So it's all about communications. So for your better understanding, I've divided the networking concepts into containers and pods, services, and ingress networks. So first, let's start with containers and pods. Now, what do you think pods are? Well, pods are nothing but the basic units of Kubernetes applications that are built from. So a pod consists of one or more containers that are allocated on the same host and are configured to share a same network stack or other resources as volumes. In simple terms, we can just say that the containers in a pod can reach each other on the local host. So for example, if a pod has 5 container images, all the container images can interact with each other on the local host. Now let's consider an example here. So starting from the top, we have a physical network and a Docker bridge connected to it. So attached to that, we have 2 containers, one working at virtual Ethernet 0 and the other one working at virtual Ethernet 1. Now both these containers are on the same logical network as the bridge, and both the containers can communicate the bridge as long as they can discover the other container's IP address somehow. But this doesn't get the concept of shared network pod.
So since namespaces are very flexible, Docker can start a container, and rather than creating a new virtual interface for it, it shares the existing interface. So both the containers have the same virtual interface and both are addressable and can hit ports opened by the other in the local host. So that's how two containers communicate between each other. But this can cause one problem. The problem is that this set of processes can take full advantage of decoupling and isolation of services while at the same time collaborating the simplest possible networking environment. So to implement this, Kubernetes implements this pattern by creating a special container for each pod whose only purpose is to provide a network interface for the other containers. So when you use the pause command, it suspends the current process until a signal is required. So it's basically like the heart of the pod, providing all the virtual network interfaces that all the containers will communicate to use with each other and outside the world. Now you must have understood how two containers communicate with each other. But how will two different pods communicate with each other? So will two pods communicate with each other with the intranode network or the internode network? Now, before I talk about the two types of communication within the pods, let me introduce you to the components of pod network. So on every Kubernetes node, there is a root network namespace, a pod network namespace, and a Linux network bridge. Now, each pod has its own network with a virtual Ethernet pair connecting it to the root network. So this is basically like a pipe pair with one end in the root network and the other end in the pod network. Now this is done for all the pods on the node, and to enable pods to talk with each other, the Linux Ethernet bridge is used. So now that you have understood the pod network components, let me start with the two types of communication, and let me start with intranode pod network. So intranode pod network is basically the communication between two different pods on the same node. So suppose we have two pods over here, pod 1 network and the pod 2 network, who have their own root network with the virtual Ethernet pair, right? So suppose just assume that a packet is going from pod 1 to pod 2. The packet leaves pod 1 network at Ethernet 0 and enters the root network at virtual Ethernet 0. Then it is passed on to the Linux bridge, which discovers the destination by using an ARP request, and then it finds out that the destination is on pod 2. So the virtual Ethernet 1 says that it has the destination IP, and the bridge now knows where to forward the packet. So once the bridge knows where to forward the packet reaches the virtual Ethernet 1 and crosses the pipe pair and reaches the pod 2 network. So that's how two pods communicate within each other on the same node. They just have to pass through the Linux bridge to know where is the destination IP, and then automatically the virtual Ethernet, which has the destination IP, takes the packet and forwards it to the pod network. So guys, that's how two pods communicate on the same node. Now, if you have two pods on two different nodes, how will they communicate with each other? So this is enabled by routing, and this is also known as the internode pod network. So as we all know that every node is assigned a unique CIDR block for the pod IPs, each pod has its unique IP, and that does not conflict with the pods on the other node. So as the same way that the cloud provider routes tables and makes sure that the packet reached a correct destination, the same thing can be accomplished here by using the network plugins. So over here we have two different nodes having their own virtual Ethernet pairs, network interfaces, and Linux bridge. Now we want two pods to communicate which are present on two different nodes. So suppose we want the packet to be transferred from pod 1 to pod 4. How is that possible? So let me show you how that's possible. So the packet leaves from the pod 1 network and enters the root network of node 1 at virtual Ethernet 0. Then it is passed on to the Linux bridge, which makes the ARP request to find the destination. After the Linux bridge finds out the destination, then the packet leaves the Linux bridge to the main network interface at Ethernet 0, since it finds out that nobody on this network have the destination IP address. So it leaves the machine node 1 and it enters the routing table to find out its destination. So the routing table has a route setup for each of the node CIDR blocks, and it routes the packet to the node whose CIDR block contains the pod 4 IP. So now the packet comes to know that its destination is on node 2. So with this, the packet arrives at the node 2 at the main network interface at Ethernet 0. Now, even though the pod 4 is in the IP of Ethernet 0, the packet is still forwarded to the Linux bridge since the nodes are configured with the IP forwarding enabled. So the nodes routing table is looked upon for any routes matching to the port 4 IP, and then the Linux bridge finds out that the destination for this node is at CIDR block. So the bridge takes the packet and makes the ARP request, and then it finally finds out that the IP belongs to virtual Ethernet 1. So virtual Ethernet 1 takes the packet, and finally the packet crosses the pipe pair and reaches the port 4 network. So that's how, guys, two pods on two different nodes communicate. They are just helped with the routing table, which helps them to find out the destination IP which is present on any different node, right? So that was all about container to container communication and pod to pod communication. Now let's move on and talk about the second topic, that is services. Now how do you think these services help in the communication of pods? So when clients connect to the proxy and the proxy is responsible for maintaining a list of healthy servers to forward its requests, there are few requirements to the proxy. It must be self-durable and resistant to failure. It must have a list of servers that it can forward to, and it must also have some way of knowing if a particular server is healthy and able to respond to requests. So the Kubernetes designers solved this problem in an elegant way by building all the basic capabilities of a platform to deliver all of these three requirements, and then they developed a resource type known as service. So we can define service as a type of Kubernetes resource that causes a proxy to be configured to forward requests to the set of pods. The set of pods that will receive a traffic is determined by the selectors which match the labels assigned to the pods when they were created. Once the service is created, we can see that it has the assigned IP address and will accept the request on the port. Now, there are four types of services that you have to understand so that you understand the option for exposing a service onto the external IP address. The cluster IP, the node port, the load balancer, and the external name. Now, the cluster IP is the default service type, and by choosing this type of service, we expose the service on a cluster internal IP. So basically with this type of service, the service is only reachable within the cluster. After cluster IP, we have the node port. So this type of services exposes the node's IP at a static port that is nothing but the node port. A cluster IP service to which the node port service will route is automatically created, and you'll be able to contact the node port services even from outside the clusters. After the node port, we have load balancers. So the load balancer exposes the service externally by using a cloud provider's load balancer. Node port and cluster IP services to which the external load balancer will route are automatically created. And finally, we have the external name. So basically this service will map the service to the contents of the external name field by returning a CNAME record with its value. There's no proxying of any kind in the setup, and it requires a 1.7 or a higher version of Kubedns. So guys, these were the four types of services that you need to understand. So now that you've understood the pod-to-pod communication, the container-to-container communication, and the services-to-pod communication, let's deep dive into the external-to-service communication. And this comes with none other than the Ingress network. So Ingress network is a collection of rules that allow inbound connections which can be configured to give services externally through reachable URLs, load balanced traffic, or by offering name-based virtual hostings. So Ingress is the most powerful way of exposing services. The services and pods have IPs only routable within the clusters. It acts like an entry point to the Kubernetes cluster. Ingress is also an API object that manages the external access to the services in a cluster with the HTTP request. And then, finally, it also sits in front of the multiple services and acts as a smart router, right? So now that I've told you about Ingress networks, let me tell you how does it work. So over here, let me explain you with an example. So we have two nodes having the pod and the root network namespaces with a Linux bridge. In addition to this, we also have the virtual Ethernet device called the Flannel 0, which is a network plugin. Now what the network plugin does is that it basically helps to route the packet to the desired destination. So over here, we want to route the packet from pod 1 to pod 4, which are on two different nodes. So the packet leaves pod 1 network at Ethernet 0 and enters the root network at the virtual Ethernet 0. Then it is passed on to the Linux bridge, which makes the ARP request to find the destination, and then when it sends the ARP request, it finds out that nobody on this pod has the destination IP address. So the Linux bridge sends the packet to the flannel 0 as the node's routing table is configured with flannel 0 for IP forwarding. Now, the flannel daemon talks to the API server of Kubernetes to know all the pod IPs and their respective nodes to create mappings to the node IPs. The network plugin then wraps this packet in a UDP packet with extra headers changing the source and the destination IPs to their respective nodes, and then it sends the packet out via Ethernet 0. Now, since the routing table already knows how to route the traffic between the nodes, it sends the packet to the destination node 2, and then the packet arrives at Ethernet 0 of node 2 and goes back to the flannel 0 to decapsulate and emit it back into the root network namespace. So the packet is again forwarded to the Linux bridge by making an ARP request to find out the IP that belongs to the virtual Ethernet 1, and finally the packet crosses the root network and reaches the destination port 4. So guys, that's how external services are connected with the help of Ingress network. So as I was talking about network plugins, let me introduce you to the top network plugins available in the market. So we have the Google Compute Engine, OpenContrail, Cilium, Project Calio, Flannel, Amazon Web Services, Romana, Weaveworks, OpenWeaveSwitch, and many others. So these are just few. We have many more in the list that you can refer from the Kubernetes official documents, right? So guys, that was all about the theory part of Kubernetes networking. Now, let me show you a real-life case study about Kubernetes networking and how a company benefited by using Kubernetes. So Wealth Wizards is an online financial planning platform that combines the financial planning and smart software technologies to deliver expert advices at an affordable cost. Now, it was extremely important for the company to quickly discover and eliminate code vulnerabilities with full visibility of their cloud environment, but they also wanted to control the traffic through access restrictions. So, they used Kubernetes infrastructure to manage the provisioning and rollout of clusters with the help of tools to manage the deployment and configuration of microservices across the kube clusters. They also used network policy features of Kubernetes to allow them to control traffic across restrictions. Now, the problem was these policies are application oriented and can only evolve with applications, but there was no component to enforce these policies. So, the only solution the company could find out for this was to use a network plugin, and hence they started using the network plugin WeaveNet. So the network plugin created a virtual network that has a network policy controller manager to manage and enforce the rules in Kubernetes. Not only this, but it also connected the Docker containers across multiple hosts and enabled their automatic discovery. So suppose you had a workload in the cluster and you wanted to stop any other workload in the cluster talking to it, you can achieve this by creating a network policy, and that restricts the access and only allows ingress to it via the ingress controller on a specific port. Now, with this deployment on each Kubernetes node, the plugin manages the interpod routing and has access to manipulate the IP tables. In simple terms, you can just understand that each policy is converted to a collection of IP table routes coordinated and configured across each machine to translate the Kubernetes tags. So guys, that was how Wealth Wizards benefited by using Kubernetes network with the help of network plugins. Now, as I was talking so much about network plugins, let me show you practically how it is done. So we're going to deploy a multi-tier application over Kubernetes networks which are present on 2 different pods and have a container image. So suppose you want to store the product name and product ID. So you'll need a web application and a database. So those are the 2 applications that we're going to use, and each of these applications will have their own container images and pods. And then we're going to form a communication line between them with the help of services. So let's get started with the hands-on part. So the first step is to make a working directory for your project. So we'll make a working directory. So let me type in the command mkdir, and let's say I create a directory saying demo. and then I'll change my working directory to that directory. So I'll type in demo. So we are in a working directory. Now you have to create a deployment YAML file for both of your applications. So to create that, you just have to open a new file and then mention the specifications required. So let me create the file. Let's create a deployment file for the web application first. Let me open a file. Alright. So I've created my deployment file for the web application. So we have the API version, basically defining the API version for it. Then in the metadata, I've given my deployment name as web app 1 with the labels for web app SQL, tied to be front end because this is the front end application, and then we are mentioning the specifications for the containers and also for the port. So in the same way you have to create for the MySQL application. So let me again open a new file. Alright, so I've created my deployment file for the MySQL application. So again, the API version is defining our API version and the kind to be deployments because it's a deployment file. And then we are giving the name for this deployment file to be SQL database and the type to be backend since it is a backend application. And then we'll also mention the specifications for the containers. So in the specifications of the containers, we are mentioning the port where we want it to run and also the image from where we are pulling it. So once all this is mentioned, you just have to close your application file. And then you'll have to check for your deployment. So for that, you have to type in the command kubectl apply -f and the name of your deployments. So over here, I have my deployment files. So you can see that first deployment has been created with the command kubectl apply -f and the name of the deployment file. So similarly, you have to do it for the MySQL application. So you just have to again type in the command kubectl apply -f and the name of file, right? So you can see that both the deployments have been created. Now, if you want to check if your deployments have been created or not, so you just have to type in the command kubectl get deployment. So you can see that both your deployments have been created with their respective names that we had given them. Now, what you have to do is you have to create services. So to create services, you again have to open a file and then mention the specifications required. So let's open a file. So let's say, suppose I open a file, web service. So we have mentioned the API version to be v1, which we had mentioned in the deployment file. The kind to be service because it's a service that we are creating, the name of the service, and then the app name, and the type to be front end because we're creating the service for the front end applications, and the port. So the type of service that we're choosing is the node port. So I'll save this file and then I'll close this. Similarly, I'll do it for the MySQL service. Let me create a new file, MySQL service, and mention the specifications. Alright, so again, we have mentioned the API version to be v1, the type to be service, because with service that we're creating, the name, the type to be backend because it's a backend application that we're dealing with, the port, and the type of service is cluster IP. So once it is done, I'll save this file and then I'll close this. Once your services are created, you have to again deploy your services. So for that, you'll use in the command kubectl apply -f and the name of the services, right? So I'll type in the name of the service. And you can see that the web service has been created. Similarly, we'll create for the MySQL service. So I'll again mention the command kubectl apply -f and the name of that file. So that's MySQL service. Now, once both of your services are created, just to check if your services are done or not, you just type in the command kubectl get services. So you can see that apart from your Kubernetes cluster service, you also have the web app service and the SQL services. So now you have to check the configuration of pods after you're done creating with the services. So for that, you'll type in the command kubectl get pods. So you can see that the web application and the SQL are running on two different pods and have their own container images. So now to create a communication line between the web app application and the database, you have to go inside each container image and you have to configure some stuff. So let's first go inside the web app container. So for that, I'll type in the command kubectl exec -it the container ID of the web app application, and end the command with a bash. So once you're inside this container, what you have to do is you have to open the index.php file, which is basically the configuration file for your web app application. So for that, I'll type in the command nano and then I'll mention the directory. So once your configuration file has been opened up, you have to change the server name, password, and the database details that you want. So let's mention the server name to be web app SQL1 that we mentioned for the MySQL container. The password to be Edureka since it's my user ID password. The database name to be, let's say, product details. So once you're done mentioning all the details, you just have to save this file. Once you're done saving this file, come out of this container. So for that, type in the command exit and you'll be out of this container. So now once you're out of the web app container, you'll come inside the MySQL container. So for that, you'll type in the command kubectl exec-it, the container ID, and bash. Then you'll have to get the access to the MySQL container. So type in the command mysql-u root-p and your password. So now once you've got the access to the MySQL container, you have to create the database and the table that you mentioned in the web app containers configurations. So for that, you'll type in the command create database product details. And then you'll use the database. For that, you'll type in use product details. Then you'll create a table that you mentioned. So you'll type in the command create table products, product name, and varchar, let's say 10 characters, product ID, and let's say 15 characters. Once it is done, you can see that a table has been created. Now just exit this MySQL container and come out of it. Alright, so now once you're done with this, you'll check the port on which the services are working. So for that, you'll type in the command kubectl get services. Alright, so you have to open your web browser and then open the web application. So you can see that our web application has been opened up. Now let's input some values. So let's say I input headphones with some ID and then I'll submit query. So you can see that a new record has been created successfully. So let me type in some input so that I can show you in the database whether they are stored or not. So I've entered few products. So now let me go back to my MySQL container and let me use the database. Once the database is used, let me show you the tables inside it. So we just have one table, that is products. So we'll select all the tuples from products. So for that, I'll type in the command select staff from products. Alright, so as you can see that we have got the output of all the products that we have given as input. So there was one product that I did not give an ID and rest all stored with the product name and the product ID.
Here's another question for you guys. Which Kubernetes object is used to manage external access to services, typically HTTP? And the options are pod, service, node, or ingress. And if you know the answer, please leave it in the comment section below. With networking covered, we will dive into Kubernetes deployment to see how to deploy and manage applications on Kubernetes.
When you start talking about Kubernetes, you should understand the basic unit of Kubernetes, that is a pod. So a pod in Kubernetes is the basic unit of this container orchestration tool. So it basically represents a unit of deployment in Kubernetes cluster and is very easy to horizontally scale a pod. Did you guys know that a group of whales is a pod which gives the whole logic behind the Docker's logo? You didn't, right? So as you guys know that the Docker's logo is a whale and a group of whales forms a pod. So with this understanding, a group of containers can be placed inside a pod. So a pod can have a single container or it can have many containers.
Now, a single container pod is used when a container runs on a physical machine on top of an operating system. And the multi-container pod is used for the applications which are dependent on the other applications or the services for which they are functioning. So guys, that's the difference between a single container pod and a multi-container pod. Alright, so now that you've understood in brief what is Kubernetes and what is a pod in it, let me tell you what is a replication controller, because these are few concepts that you need to understand before you deep dive into deployments. So starting with replication controller, the replication controller helps to achieve the desired state by making sure that the desired number of pods always exist. So just in case if a pod crashes, the replication controller creates a new one. Not only this, but it can update and delete multiple pods with just a single command, and it also helps to create, scale, and maintain multiple pods as part of its desired state. So as you can see on the screen, we have two pods. So we want the first pod to have two replicas with the label selector to be V1 and the second pod to have only one replica with the label selector V2. So this replication controller will make sure that these replicas are made, and then it will make sure that the desired number of pods always exists. So guys, that was all about replication controller. Now let me tell you about replica sets. Replica sets do almost everything same as that of the replication controller. It ensures that the specified number of pod replicas are running at any given point of time. But you might be wondering, right, what is the key difference between replica set and replication controller if they have the same job to do? Well, the main difference comes from the support of selectors. So replica set supports the set-based selectors, whereas the replication controller supports only the equity-based selectors. Now, what is the difference between these two selectors? Well, let's start with the equity-based selectors. So the equity-based selectors matches the same exact word or phrase. So for example, if you say that the label selector app should be Nginx, then it will only look for the pods which have a label app equal to Nginx and nothing else. So it will not look into anything else with any other name. It will only look for the pods which have the name Nginx. So similarly, the set-based selectors is where you can define a proper set. So suppose that we define a set having the name Nginx, NPS, Hello. Now if the app is equal to any of the Nginx, NPS or Hello, then the selector will take this as a true result. So that's the difference, guys. In the equity-based selectors, the selector matches only to the exact word, and in the set-based selectors, the selector matches to a proper set. Alright, so now that you've understood both these terms, let's jump into our main topic, that is deployment. So what do you think these deployment controllers are? As the name suggests, it's all about deploying a file, right? It's all about deploying something in action. So deployments are basically upgraded and higher version of replication controllers. So they manage the deployment of replica sets, which is also an upgraded version of the replication controller. And then they have the capability to update the replica set and are also capable of rolling back to the previous version. So deployment controllers are declarative in nature to provide the required informations or updates to the pods and replica sets. Not only this, but they can also change the actual state of the defined controller object to the desired state. So as you can see on the screen, you will have replica sets of the pods which will be automatically created when you create a deployment. Then all these pods will be connected with each other via nodes, and if you delete a deployment, then obviously you will lose your replicas, right? So in short, if you describe a desired state in a deployment object, then the deployment controller can change the actual state to the desired state at a control rate. Not only this, but you can also define deployments to create new replica sets or to move from the existing deployments, and can also adopt their resources with the new deployments. So is it clear to you guys? Alright, so that's great. So now let me tell you the various activities that you can perform on deployments. Well, you can create a deployment, you can also update a deployment, you can roll back a deployment, you can scale a deployment, and you can also pause a deployment. Now, when I'm talking about creating a deployment, you can create a deployment in a very simple manner and see how the replica sets are automatically created. Then, by updating the deployment, I mean that whenever you update a deployment, the new replica sets created by the deployment represent the deployment version. Coming to the rollback of deployments, by this, I mean that you can roll back to any deployment versions that you want. But let me tell you here that the replicas do not get replaced, only the container image versions gets updated. Next, if you have to scale your deployment, then you can either scale up or descale the deployment based on the resources requirements. Not only this, but you can also use the auto scale by which you can limit the usage of resources and can also limit the number to which we can upscale or descale the deployments. And finally, You can also pause the working pods, make the changes required, and then resume back the pods. So guys, these are few use cases of deployments. Don't worry, I'm going to show you each one of them. So starting with the creating of deployments, let me tell you that we're going to just create a simple deployment and then I'll show you how the replica sets run in the background. Alright guys, so let's get started. So first we want to create a deployment. So to create a deployment, you have to open a file, right? So for that, I'll type in the command gedit and let's say I mentioned demo.yaml. So this will open a simple file for me. Now what I have to do is I have to create my deployment file. So for that, you have to mention some specifications, okay? So let's start mentioning the specifications. So first I have to mention the API version. So for that, let me type in my API version to be, let's say, apps/v1. Then let's say kind to be deployment because it's a deployment file that we are creating. In metadata section, I'll mention the name of my deployment to be Nginx deployment because I'm trying to deploy an Nginx container. So let me type in Nginx deployment. In the labels section, let's say app to be Nginx because as I said, we are deploying an Nginx container. So let me mention that. In the spec section, let's say I'll mention the replicas to be 3. In the selector section, which is an optional section that you can choose to, let's say I mention the match labels to be again app for Nginx so that I want it to get matched. Then in the template section, I'll again mention the metadata and the labels. So let's say the metadata and labels to be again app.nginx. Then I'll again create a spec section where I'll mention my container port. So that's basically the port where it's going to run. So let's type in the spec section. Name to be Nginx. Let's say I choose the image version to be 1.7.9. So I'll type in the version and then I'll mention the ports. So let's say it runs on the port 80. So I'll mention that. Alright. Now once I've mentioned this, let me just give you a summary of it. So I've created a deployment named Nginx deployment indicated in the metadata name field. Then this deployment will create 3 replica pods which are indicated in this replica field. Now the selector field defines how the deployment will find which pods to manage. In this case, I've just simply selected one label defining in the pod template. However, it can be done in a more sophisticated way as per your requirement. So the template field basically indicates the pods that run in one container. So it has the metadata labels apps, right? So basically the pods are labeled with app::nginx. It will create one container and then it will name it Nginx. So the Nginx image is at version 1.7.9 and it will open at a port 80 so that the container can send and accept the traffic. Guys, that was our deployment file. So just now save this file and now close this file. Alright. Now once your deployment file has been created, you have to deploy that deployment file. So there are basically 2 ways to do that. Either you create and deploy that file in just one go or you just apply the previous deployment to it. So since we have already created a deployment, we're just going to apply the deployment. So for that, you have to type in the command kubectl apply -f and the deployment file name. So that is demo.yaml. So you can see the output that our deployment has been created. Now, if you want to create your deployment file, you have to type in the command kubectl create -f and the deployment file name. So once you put in this command, it will open a blank file for you. You again have to create your deployment file, and once you save that file, it will automatically get deployed. So now that you can see that our deployment has been created, let's just check our deployment. So for that, you have to type in the command kubectl get deployments. Now once you put in this command, you can see the output that our file has been deployed. Now you see these fields, right? The name, desired, current, up-to-date, available, and age. What do these fields signify? Well, the name lists the names of the deployments in the cluster. The desired displays the desired number of replicas of the application which you define when you create the deployment. So this is basically the desired state. As I showed you while creating the deployment file, I've mentioned 3 replicas. The current field displays how many replicas are currently running. The up-to-date displays the number of replicas that have been updated to achieve the desired state. The available field displays how many replicas of the application are available to your users. And the age displays the amount of time that the application has been running. So guys, these were the fields that you get when you type in this command kubectl get deployment. Now, if you want to check the number of replicas running and you want to check the replica set, For that, you have to type the command kubectl get rs. Now just observe the name of the deployment here. This has got a code that was not the same as the name of the deployment file. That's because the replica set is always formatted as the deployment name and the pod template hash value. So the hash value is automatically generated whenever the deployment is created. So it's basically generated by hashing the pod template of the replica set and uses the resulting hash as the label value that is being added to the replica set selector. So this is basically to check, that that particular replica set is not being overwritten or it does not override something else. Now, once that is done, if you want to see the description of your complete deployment file, you have to type in the command kubectl describe deployment and the name of the deployment file. So this is Nginx deployment here. So once you type in that command, you can see the complete description of your deployment file, like the number of replicas that we mentioned, that was 3 are running, 3 are updated, total number are 3, and 3 are available. The strategy type to be rolling update, the Nginx image version to be 1.7.9, it runs on the port 80, and various other conditions. So guys, that's how you can create your own deployments. Now moving on with the session, let's see how can we update the deployments. So let me switch back to my terminal. Now to update your deployment, you basically have to change some parameters. Let's change the number of replicas and the container image to 1.9.1. So for that, I'll just open my YAML file. And then let's say I change the number of replicas to 6 and the version to be 1.9.1. Once this is done, let me just save this file and close this file. Now, let's just apply this deployment. So for that, you'll type in the command kubectl apply -f demo.yaml. So you can see that, our deployment has been updated. Now let's check our deployment. So for that, I'll type in the command kubectl get deployments. And you can see that the desired is 6, current is 8, up to date is 5, and available is also 5. Now let's type in the command again. You can see that all are 6 and the available number is 5. And let's do it again to check the number of available. So you can now see that all our replicas are available, right? So that's how you can update your number of replicas. So now let's see if our version has been updated or not. So for that, I'll open the description. So I'll type in the command kubectl describe deployment and the name of the deployment. All right. Now, once this deployment description opens up, you can see that we have 6 replicas that I just mentioned, and the version has been changed to 1.9.1. All right. Now, once you're done with updating the deployment, let's look into how can we roll back to a particular deployment. For that, you have to type in the command kubectl rollout status deployment and the name of the deployment. So I'll just type in the name of the deployment. And it gives us an output that the deployment has been successfully rolled out. So after the rollout succeeds, you may want to get the deployments, right? So let's just check the deployments again. So for that, you'll type in the command kubectl get deployments. And yes, you can see that our deployment has 6 replicas ready. Now, once you're done with this, if you want to check your rollout history, so you type in the command kubectl rollout history deployment and the name of the deployment. Now this rollout history will basically give you the number of revisions. So we have 2 revisions over here. Now if you want to roll back to a particular revision, you have to type in the command kubectl rollout undo deployment, name of the deployment, and then space -2 revision, and then mention the revision's name. So let's say I put 3. So you can see that, it has been rolled out. So now let's just check the description again. So for that, you'll again use the command kubectl describe deployment. And you can see that, our image has been, changed to 1.7.9. But yes, the number of replicas do not change. Now, if you do not mention the revision number here, then it will be rolled back to the most recent deployment. So since I've mentioned the revision number, I've just rolled back to that particular revision. So guys, that's how, you can roll back to a particular deployment. Now let's look into the next one, that is how to scale a deployment. Either you can upscale a deployment or you can descale a deployment. But how do you do that? So for that, let me just switch back to my terminal. So if you have to scale a deployment, you have to type in the command kubectl scale deployment nginx deployment -- replicas equal to 4. So basically, I'm descaling the deployment. Now, once that is done, you can see the output that the deployment has been scaled. So let's just type in the command kubectl get deployments to see the number of replicas running. So you can now see that, instead of 6, we have 4 running. So that's how you can upscale or descale your deployments. Apart from this, we have something more. That is the auto scaling concept. Now by auto scaling, you can choose the minimum and the maximum number of pods that you want to run based on the CPU utilization of your existing resources. So if you want to just auto scale, you have to type in the command kubectl auto scale deployment and the name of the deployment space hyphen minimum. Let's say I mentioned 5 and hyphen maximum. Let's say I mentioned 9, right? And then I'll mention the CPU percent to be 80. That is 80% of the CPU would be used. Now, once this is done, you can see an output, right? That the horizontal autoscaler has been autoscaled. So with this command, you'll have minimum 5 number of replicas always running and maximum of 9 number of replicas. Suppose you scale your deployment to 10 replicas, it will be automatically descaled to 9 replicas. And if you suppose have scaled down to around 2 replicas, then it will be automatically upscaled to 5 replicas. So this is the minimum and the maximum number of replicas that will be all the time running. Now let me again scale and show you what happens. If I type in the command kubectl scale deployment and the name of the deployment file, and let's say I type in the replicas to be 2. So you can see that, it has been scaled. Now let's just get the deployments and you can see that we have 2 running. Now if you want to get the information of the horizontal autoscaler, you have to type in the command kubectl get HPA. So you can see that, there are 5 minimum pods, 9 maximum pods, 5 replicas, and 80% of the CPU can be used, right? Now, if you want to know the description of it, you just have to type in the command kubectl describe HPA Nginx deployment. That is basically the deployment file. And you can see the description of the horizontal scaler. So you can see over here the minimum replicas, the maximum replicas, the deployment pods, what it's able to scale, how much it is using, when is it used, what is the age that they're starting from and all, right? So you'll get all the information. All right. Now, if we just delete this deployment, let's see what happens. So let's say I delete the autoscaler. So for that, I'll type in the command kubectl delete HPA Nginx deployment. So you can see that, our horizontal pod autoscaler has been successfully deleted. Now let's scale the deployments again. So for that, let me type in the command kubectl scale deployment, the name of the deployment file. And let's say I mentioned the replicas to be 10. So you can see the output that deployment has been scaled. So let's get the deployment. So for that, I'll type in the command kubectl get deployments. So you can see that the number of replicas has been changed. But yes, before when we were trying to scale it with the help of the scaling command and we had the autoscaler enabled, we were not able to scale it. So once the autoscaler has been deleted, you can again scale up or scale down based on your requirement. So guys, that was about the scaling up and scaling down a deployment. Now, how do you think that you can pause a deployment? Well, you can pause a deployment before triggering one or more updates and then resume it. So this will basically allow you to apply multiple fixes in between pausing and resuming without triggering unnecessary rollouts. So let's say I want to pause this deployment. So for that, I'll type in the command kubectl rollout pause deployment and the name of the deployment. You can see that, our deployment has been paused. Now, let's say we want to update back the image and let's say we'll resume it. So if you want to update the image of the deployment, you can just type in the command kubectl set image deploy and the name of the deployment file. So let me just type in the name. And you can see that, our image has been updated. Now you can make as many updates as you want and then you can resume back your deployment. So let's say I want to update the resources as well. So for that, I'll type in the command kubectl set resources deployment nginx deployment -c is equal to nginx limits is equal to CPU is equal to, let's say, 200. And let's say it's taking a memory of 512, right? So let's say I type in 512. And once that is done, I'll just press on enter. And you can see that, our deployment resources have also got updated. Now, the initial state of deployment prior to pausing it will continue as its function, but new updates to the deployment will not have any effect as long as the deployment is paused. So when you resume a deployment, you'll observe a replica set coming up with all the new updates. So with the note of that, let's just see how to resume the deployment. So for that, you'll type in the command kubectl rollout resume deploy nginx deployment. So you can see that our deployment has been resumed. So let's just open the description again. So for that, I'll type in the command kubectl describe deployment and the name of the deployment. So for that, let me just type in the name of the deployment. So you can see that our image has been updated to 1.9.1. The CPU and the memory that we're using are 200 and 512 respectively, and that's what we updated there. So that's how you can do.
After learning about deployments, we will discuss Kubernetes controllers and services to understand how they manage application states and enable communications.
Let us now understand what is Kubernetes controllers in general. Okay, but before we move ahead to controllers in Kubernetes, let's see what does this controllers actually mean in a common sense term. So this controllers, right? Controllers are basically an infinitely running loop that keeps on executing as long as we have that application running. Okay, and the responsibility of these controllers is to monitor everything that is happening in the system. So to give you a real-time example, let's take something like a room temperature controller. Okay, so we basically have this thermostat installed in majority of the rooms, right? So whatever the current state of the room is, whatever is your desired state of the room, that is monitored by a thermostat. And thermostat continuously monitors if the room temperature is dropping or increasing. And if the room temperature is changed, right? So it brings it according to whatever the difference amount is there. So coming back to Kubernetes, right? Well, controllers in Kubernetes are basically like this control loop that watches the entire state of your cluster and then make or do request changes needed to be done. Each controller tries to move the current state that is closer to the desired state over here. So let us now move ahead and discuss some of the popular controllers that is available to us in Kubernetes. First off, we have something called as replica set. You see, replica set's purpose is to maintain a stable state of a replica pod running at any given time. As such, it is often used to guarantee the availability of a specified number of identical pods. You see, replica set ensure that a specific number of pod replicas are running at any given time. However, a deployment of a container is a high-level concept that manages the replica sets and provides directive updates to pods along with a lot of other useful features. Therefore, we recommend using deployment rather than just using replica set at once. So what I'm trying to say here is that you may never need to manipulate replica set object. Instead, you can just use a deployment instance over here. Alright, so speaking about deployments, right? So deployment basically provides a declarative updates for pods and replica sets. You describe a desired state in a deployment and the deployment controller changes the actual state to the desired state at a controlled rate. You can define deployment to a creative new replica set or to remove the existing deployment and adopt all the resources with a new deployment. So moving ahead to the next type, that is Statefulset. You see, Statefulset is a workload API object used to manage stateful application. This manages the deployment, scaling of the pod and provides guarantee that ordering the uniqueness of these pods. Like deployment, a Statefulset manages the pod that are based on identical container specs. Unlike deployment, a Statefulset maintains a sticky identity of each pod. These pods are created for the same spec, but are not interchangeable as they are referred to by unique identity. So moving ahead to the daemon set. You see, a daemon set ensures that all the nodes run a copy of a pod. As nodes are added to the cluster, pods are added to them. As nodes are removed from the cluster, then those pods are removed and sent to a garbage collector. Deleting a daemon set will clear out all the pods that it has created. Some of the typical use cases of daemon sets are running a cluster stored daemon set on every node. Okay, running a logs collection on a daemon on every node. In a simple case, right, a daemon set covers all the nodes and would be used for each type of daemon. A more complex setup might use multiple daemon sets for a single type of a daemon, but the different flags or different memory and a CPU request for different hardware types are used here. So let us now move ahead and see what are Kubernetes services, right? So what do you understand when someone says what exactly is a service, right? Well, a Kubernetes service is a logic abstraction for a deployment group of pods in a cluster. Since pods are ephemeral, a service enables a group of pods which provides a specific function such as web services or image processing or whatever it is, to assign a name and a unique IP address. As long as the service is running that particular IP address, it will not change. Services are defined like with different policies that goes there. Majority of the time we get asked what is the difference between service and a deployment. Well, you see, in Kubernetes, a deployment is a method of launching a pod with a containerized application and ensuring that this necessary number of replica is always running on the cluster. On the other hand, a service is responsible for exposing an interface to those pods which enable network access from either within or from outside the cluster. Alright, so now that we know a brief about what exactly is services, let us now move ahead and see what are the different types of clusters that are available. Starting off with cluster IP service. So the cluster IP service is a default type of service which is used to expose service on IP address internet to the cluster. This access is permitted only from within the cluster. Moving on to the next one, we have headless service. Services that do not need load balancing and only expose a single IP can create headless service by specifying none as the cluster IP. Headless service can be defined as a selectors, in which cases endpoint records are created at the API that modify the DNS to return address that point to the pods that are exposing the service. Headless services without selectors don't create an endpoint records. The DNS ecosystem configures either the CNAME record or the record of the endpoint with the same name as the service. Moving on to the next type, that is node port service. You see, node port are opening ports at every cluster nodes. Kubernetes will route traffic that come into the node port to the service, even if the service is not running on that particular node. You see, node port is intended as a foundation of high-level method of ingress such as load balancing and are useful in deployment. Moving on to the next type, we have external name service. External name services are similar to other Kubernetes services. However, instead of being accessed by a cluster IP address, it returns a CNAME record with a value that defines in the external name. Alright, so moving on to the last type, we have load balancer service. For those clusters that are running on a public cloud providers like AWS or Azure, creating a load balancer service provides an equivalent to a cluster IP service extending to a load balancing service that is specific to that particular cloud provider. You see, Kubernetes over here will automatically create a load balancer and provide a firewall rules if needed, and then populate the service with an external IP address assigned by the cloud provider. So now that we know Kubernetes services, let us now understand how can you access these services, right? So how do you access these services? Well, you see, services simply point to the pods using labels. Since services are not node specific, a service can point to a pod regardless of if they run in a clustered environment or not. Here, by exposing the service IP address as well as the DNS service name, the application can be reached to either methods. So how do you access these Kubernetes services is a question over here, right? Well, you see here there are two basic ways. First off, we have DNS, which is actually the most common way, and the other one is env variable. Talking about DNS, right? The DNS method is recommended method for discovering the services. To use this method, a DNS server must first be installed to the cluster. The DNS server monitors the Kubernetes API, and when new service is created, its name becomes available for easy routing and for requesting of an application. Next, as I mentioned earlier, we have env variable. This method relies on something called as kubelet adding environment variable for each active service for every node that is running at any given point. So to conclude over here, we can access Kubernetes services by two ways. One is by DNS and the other one is by env variable.
Now moving on to another question. Which Kubernetes controller is responsible for managing stateless application? Options are given on the screen, and if you know the answer, please leave it in the comment section below. Next, we will explore Kubernetes ConfigMap to learn how to manage configuration data within your applications.
What is ConfigMap? In Kubernetes, according to the definition, a config map is an API object used for storing non-sensitive data. This data is stored in the key value pairs. These config maps are consumed by pods as environment variables or as configuration files in a volume. The benefit of this is that config map decouples environment-specific configuration from container images. This means that your applications can become more portable. Let's understand this a bit further. In Kubernetes, you can think of volume as a file system. Volumes are provisioned to the pods and owned by that pod. The contents of that volume can be mounted into any file system path we like in the pods container. So, the config map contains the actual content that you are going to be using to populate a pod's volume or environment variable. They contain key value pairs describing file contents, environment variable, or some arguments. Now, let's look at the use of config map and its purpose. First, let's understand that when you create a pod, you use several environment variables. These values are tightly coupled with the pod. These values are normally typed in the pod's definition. For example, when you use a specific location, that is statically defined in the pod definition. Now, if you have multiple pods using the same variable, you will have to edit the pod definition one by one. So, you have to change variable, file location, definition, and so on. Kubernetes offers config map as a solution to this boring task, where you can define location as a key value pair, and that value will be injected into the pod. Now, if you ever want to change the values, all you need to do is edit the config map, and that's it. No more tedious work of changing variables and configuration one by one. This saves time and makes things simpler. So, let's talk about the similarities and differences of config map and secrets. First, in Kubernetes, these config map and secret might appear virtually similar, but the intended usage for both is a bit different. First, config map is strictly intended for storing non-sensitive information such as configuration data and environment variables. On the other hand, secrets is used for storing sensitive data such as passwords, tokens, and keys. Unlike config map, which has no encryption available, with secrets, you can enable encryption in order to use it safely. Talking about the similarities, both objects are meant to be injected to the pods, but secrets is very specific and is intended to hold confidential data. Now, let's talk about how you can create config maps. Well, there are two ways you can create them. First is called the imperative approach and the other declarative. Let's look at imperative first. With the imperative approach, you can use the kubectl command followed by config map and the name of the config map and the key value pair with the literal parameter. The literal means that you are passing the key value directly during the creation process. These key values pair can be something like first name as a key and the first name like John as a value. With the declarative approach, you can use the file structure of config map and define key value pairs inside it. Then you save the file with an extension of YAML. Afterwards, all you need to do is run the kubectl apply command and provide it the file that you just saved. We will look into this shortly in the demo. So let's dive right into the demo and look at how to create config maps and use them in pods. Here I have my GCP master and worker node setup. First, I'll SSH into this session. Now, for this demo, you can go to the official documentation of Kubernetes. I have this page opened up. In my opinion, all you need to do is experiment with these commands. With a little bit of patience, you would be able to understand most of the documentation without any help. So, under this section that says create a config map, the first thing that we are going to be looking at these commands. So, as you can see, with this command, it first creates a directory of config map which is located inside configure pod containers. Next, it downloads two files from the Kubernetes website, which are game.properties and UI properties, and then pushes that into the directory that we just created. Afterwards, what it does is it creates the config map using this command with the config map name being game-config, and it passes it the file which are located in this directory. Therefore, in this manner, it is essentially creating config maps from directory because the directory will be holding two files. Let's do this. So first, I'll copy this command and essentially copy paste most of the code. Next, I'll download these two files and then we'll again be looking into this. Now, what I first want to do is I'll open these files. So as you can see, we have the UI properties with the key value pairs being listed like this. And the same goes for game.properties. So game.properties has these values, which is enemies equal to aliens, lives equal to 3, etc. etc. Now, we are not much interested in that, but what we are interested in is creating the config map using this directory. So if we look at my directory here, it has configure pod container, and if we go inside it, we should see the files that we downloaded. So it has the files downloaded here. Now we'll create the config map. This is done by using the kubectl command followed by create and then passing it the config map argument. Then we provided the name of our config map and follow it with the file argument. And then we provided our directory. In this case, it's configure pods, container, and config map. So we hit enter and we should have created our config map. So it says here, we have created a config map and we can view this by typing kubectl get config maps. As you can see, we have created the game-config. Now, to view what's inside this, all you have to do is type in kubectl get config map followed by the name of your config map and then using -o YAML. So it has the game.properties values key value pair here and the UI properties key value pairs here. Now again, let's go back to the documentation. So we have created config maps from directory. Now let's look at how you can create config maps from just a file. So here, unlike last time when we passed the directory, we are just passing one single file and we are giving it the config map name as game-config-2. So let's create this config map. And in this case, our config map name is game-config-2. So because this time a directory was not passed, we should have only game.properties data in the config map that we just created. So let's verify this. As you can see, we have just the game.properties key value pairs here. And this was created using just one single file. Now, let's look at how you can use imperative approach to create a config map. What we did till this point was use a declarative approach in which files were already there and we just passed it to the kubectl create command. With this command, we use the from literal argument and we pass it a key value pair. Here we are providing this key value pair of special how, which equals very, and special type, which equals charm. So let's create this config map. This time let's check how many config maps we have available. So now we have a new special config. Let's see what we have inside it. So as you can see, values that we provided, which were special.how equal to very and special.time equal to charm, are available here. And now let's see how you can actually inject values into pods using keys and config map references. So let's go through the documentation and see what we have. So under this section, we can see that we are defining an environment variable here, which is from literal equal to special or how equal to very, which we just did, as you can see here. Next, what we are doing is we are assigning the special.how variable to our config map, and we are doing this for this specific variable. So if you look at this, you can see that it has the name of the pod, which will be this. Next, it has a container, test container, and under the environment, it has a variable name called special level key, and it gets this value by referencing to the config map, which is named special config, and it references to the key of special.how, and then it creates this pod. So here, Kubectl will be downloading the YAML file and creating it right away. But what I'll be doing is I'll be copying this and then create it on my system. And now we have created our pod, which is named dapi test pod. Now, if we look at our documentation, it says here that we referenced special config and we have referenced the special.how key. Now, this should be reflected in the environment variable called special key inside the pod that we just created, which is named dapi test pod. So to check this, what we are going to do is we'll type in one command, which is called kubectl log, followed by the pod name. And as you can see here, we have the special level key defined as very. And this is what we wanted to see. And with that, I hope you have a better understanding of what config maps is. This session was by no means a very comprehensive session on this topic, but at least with this knowledge, you can understand how config maps is used to inject values into the pods. So do experiment and keep learning.
Let's take up a quiz question. Which command is used to create a config map from a file in Kubernetes? Options are given on the screen, and if you know the answer, please leave it in the comment section below. With config maps understood, we will move on to the Kubernetes operators to see how they automate complex application management.
Now, before we understand what is operators, let's talk about site reliability engineering. So operators are basically software site reliability engineering. So what does it really mean? Site reliability engineering is a set of patterns and principles for running large systems. Originating at Google, SRE has had a pronounced influence on industry practice. Practitioners must interpret and apply SRE philosophy to particular circumstances, but a key tenet is automating systems administration by writing software to run your software. Teams freed from rote maintenance work have more time to create new features, fix bugs, and generally improve their products. Now let's talk about operators. It is like an automated site reliability engineer for its application. It encodes in software the skills of an expert administrator. An operator can really manage a cluster of database servers, for example. It knows the details of configuring and managing its applications, and it can install a database cluster of a declared software version and number of members. An operator continues to monitor its application as it runs and can back up data, recover from failures, and upgrade the application over time automatically. Cluster users employ kubectl and other standard tools to work with operators and the applications they manage because operators extend Kubernetes. You must be wondering, what is kubectl? So kubectl is basically a command line tool for Kubernetes. You can really play around and operate Kubernetes with the help of kubectl command line. Now that we know what is operators, let us understand what are custom resources. So custom resources, in short, are used for small in-house configuration objects without any corresponding controller logic. That is, it is purely declaratively defined. But custom resources also play a central role for many serious development projects on top of a Kubernetes that want to offer a Kubernetes native API experiences. Custom resources are available in every Kubernetes cluster since version 1.7. They're stored in the same etcd instance as the main Kubernetes API resources and served by the same Kubernetes API server. At its core, a custom resource would look very similar to the image that you can see on the screen. Custom resources or CRs as extensions of the Kubernetes API contain one or more fields like a native resource, but are not part of a default Kubernetes deployment. CRs hold structured data, and the API server provides a mechanism for reading and setting the fields as you would those in a native resource by using kubectl or another API client. Users define a custom resource on a running cluster by providing a custom resource definition. A CRD is akin to a schema for a CR, defining the CR's fields and the types of values those fields contain. Now, Kubernetes provides custom resources to represent new collection of objects in the API. Custom resources are created and accessed by standard Kubernetes clients like kubectl, and they obey Kubernetes conventions like the resources.spec and .status. At their most useful, custom resources are watched by custom controller code that in turn creates, updates, or deletes other cluster objects or even arbitrary resources outside of the cluster. With this, let's move ahead and understand what are custom controllers. Custom resources are entries in the Kubernetes API database. They can be created, accessed, updated, and deleted with the common kubectl commands, but a custom resource alone is merely a collection of data. Now, to provide a declarative API for a specific application running on a cluster, you also need active code that captures the processes of managing that application. So the Kubernetes has a standard Kubernetes controller, which is called as the replica set controller, which we'll not be talking about as of now. But to make an operator providing an application programming interface for the active management of an application, you build an instance of the controller pattern to control your application. This custom control that you create checks and maintains the application's desired state represented in the custom resource. So every operator has one or more custom controllers implementing its application-specific management logic. So now that we know what is custom controller and how it is related to custom resources, let's move ahead and talk about how operators work. So operators work by extending the Kubernetes control plane and API. In its simplest form, an operator adds an endpoint to the Kubernetes API called a custom resource, which we just talked about, along with a control plane component that monitors and maintains resources of the new type. This operator can then take action based on the resource's state, which is illustrated in the figure on the screen. Here on the screen, you can see that operators are custom controllers watching a custom resource. As I've already mentioned, custom resources are the API extension mechanism in Kubernetes. A custom resource definition, that is a CRD, defines a custom resource. It's analogous to a schema for the CR data. Unlike members of the official API, a given CRD doesn't exist on every Kubernetes cluster. CRDs extend the API of the particular cluster where they are defined. They, meaning CRs, provide endpoints for reading and writing structured data. A cluster user can interact with CRs with kubectl or another Kubernetes client, just like any other API resource. Now let's move ahead and talk about how operators are made. So the first thing what Kubernetes does is it compares a set of resources to reality, that is the running state of the cluster. Then it takes actions to make reality match the desired state described by those resources. Operators then extend that pattern to specific applications on specific clusters. So an operator is basically a custom Kubernetes controller watching a custom resource type and taking application-specific actions to make reality match the spec in that resource. Now, making an operator means creating a custom resource definition and providing a program that runs in a loop watching CRs of that kind. What the operator does in response to changes in the custom resource is specific to the application the operator manages. The actions an operator performs can include almost anything, that is scaling a complex application, application version upgrades, or even managing kernel modes for nodes in a computational cluster with specialized hardware. Now, for example, the etcd operator knows how to perform particular tasks. An operator knows about its application's internal state and takes regular actions to align that state with the desired state expressed in the specific of one or more custom resources. Now that we know how operators are made to, let's talk about who are operators for. Now, the operator pattern arose in response to infrastructure engineers and developers wanting to extend Kubernetes to provide features specific to their sites and software. Operators make it easier for cluster administrators to enable and developers to use foundation software pieces like databases and storage systems with less management overhead. Now, if the killer new DB database server that's perfect for your application's backend has an operator to manage it, you can deploy killer new DB without needing to become an expert killer new DB DBA. Application developers build operators to really manage the applications they are delivering, simplifying the deployment and management experience on their customers' Kubernetes cluster. Infrastructure engineers create operators to control deployed services and systems. Now that we've discussed the major topics and terms in Kubernetes operators, let's move ahead and build our own operator. Okay guys, so now I am currently on Ubuntu. So what we're going to do now is we're going to build operators. For this, you'll need Minikube and kubectl already installed in your local machine. And you will also need cluster admin access to a cluster running Kubernetes version 1.11.0 or later. If you met these requirements, then you're good to go. So I'm just going to use the command sudo minikube version to check the version that I currently have on my Ubuntu, and it is version v1.20.0. Okay, and we are also going to check the kubectl version with the command sudo kubectl version space -- client. Okay, and this will give you the client version, it will give you the git version, git commit, go version, all of that information is here. Now that we have both Minikube and kubectl set up in our Linux machine, I am just going to start Minikube using the command minikube start. Now you can see that kubectl has configured to use Minikube cluster and default namespace by default. This is good. Now I'm just going to clear my screen. So before we move ahead, we are going to ask the Kubernetes API about the cluster admin role to see if it exists on the cluster. So you must be wondering, what is cluster admin role, right? Since operators extend Kubernetes itself, you will need privileged cluster-wide access to a Kubernetes cluster to deploy them. One such common cluster role is the cluster admin. Okay, so I'm just going to type this command to get a summary of the role with the kubectl's describe subcommand. Okay, now you can see that the RBAC cluster admin cluster role has been displayed. That is, the name is cluster admin, and also the labels, annotations, and policy rules have been mentioned. So now once you verify that you have privileged access to a Kubernetes cluster of a compatible version, you're ready to deploy an operator and see what operators can really do. A common starting point would definitely be the etcd, which is a distributed key value store with roots at core operating system, now under the auspices of the Cloud Native Computing Foundation. It is basically an underlying data store at the core of Kubernetes, and it is definitely a key piece of several distributed applications. Now, etcd provides reliable storage by implementing a protocol which is called as Raft. Raft, what it does is it guarantees consensus among a quorum of members. Now, you can think of etcd operator as Hello World, example of the value. Okay, so we use Hello World as a beginner's program, right? So definitely etcd operator is a great way to start off with Kubernetes operators. So to use etcd, you put keys and values in and get them back out by name. So we'll learn how to really work with etcd. So for this, what I'm going to do is I'm going to firstly clear my screen, and so we will be downloading a Git repository for the chapters example codes. What this does is it grabs the chapters repository and changes into the particular chapter that we'll mention. So I'm just going to download this book by using the command git clone. So you can see that it is going to clone and download these chapters onto my system. And once that is done, I'm just going to change directory to chapters chapter 3. So as with nearly everything in Kubernetes, a YAML manifest describes a CRD. We've already talked about CRD in the theory part. A CR, that is a custom resource, is a named endpoint in the Kubernetes API. A CRD named etcd clusters.etcd.database.coreos.com represents the new type of endpoint. So what we're going to do first is we're going to be creating a CRD. A CRD defines the types and values within an instance of a custom resource. And this example defines a new kind of resource, the etcd cluster. So what we're going to do is we are going to type the command sudo cat etcd-operator-crd.yml. So you'll see a tiny piece of, YAML file that specifies the etcd cluster CRD. The CRD defines how the Kubernetes API should reference this new resource. The shortened nicknames that help you do a little less typing in kubectl are defined here too. You can see that etcd class is given, etcd is given. Those are the short names that have been described. Now what you can do is you can create the CRD on our cluster using the command sudo kubectl create -f etcd -operator -crd.yml. So you can quickly check if the new CRD has been created by using the command kubectl get CRD. You can see that the etcd clusters.etcd.database.coreos.com has been created. Now the CR's group, version, and kind together form the fully qualified name of a Kubernetes resource type. That canonical name must be unique across a cluster. The CRD you created represents a resource of version v1 beta 2 and kind etcd cluster. Now that we've created our CRD, let us clear the screen. So for now, what we're going to do is we just want to take a first look at the basic declarations for a service account and the capabilities that account needs to run the etcd operator. So we're just going to check out the file etcd-operator-sa.yml. Okay. And you can see the API version, you can see the kind and the metadata with its name. So you can create the service account by using the kubectl create command. Okay, and I'm just going to enter. Okay, my bad. And as you can see that the etcd operator SA has been created. Now, if you check the list of cluster service accounts, you'll see that the etcd operator SA also has been added. And you can check that by using the command kubectl get service accounts. And you can see that we have two clusters. The first one is the default one, which we saw when we started the Minikube. So when we started the Minikube by using the Minikube start command, we saw that a default cluster had been created. You can also see that the cluster service accounts have been added. So the role governing the service account is defined in a file named etcd operator role.yml. So now what we're going to do is we give the role a name that we'll use to reference it from other places. I'm quickly going to type in the command sudo cat etcd operator-role.yml. And you can see that the YAML file goes on to list the kinds of resources the role may use and what it can really do with them, that is, what verbs it can say. So you basically have verbs, you have API groups, you have resources, etc. Now, as with the service account, we're also going to be creating the role with kubectl. I'm just going to be using the command kubectl create -f etcd operator-role.yml. And you can see that the role also has been created. I'm just going to quickly clear the screen. Now, the last bit of the RBAC configuration is the role binding, which assigns the role to the service account for the etcd operator. And this has been declared in the role binding YAML file. We're going to check that out. Again, we're going to use the cat command. So if you notice the last line, and if you're on a brand new OpenShift cluster, like that provided by code-ready containers, By default, your kubectl or OC commands will run in the namespace my project. Now, if you're on a similarly unconfigured Kubernetes cluster, your context default will usually be the namespace default that you can see on the screen. So wherever you are, the namespace value in the role binding must always match the namespace on the cluster where you're working. So now what we're going to do is we're going to create the binding. The role binding has also been created successfully. Now I'm quickly going to clear the screen and we will be deploying the etcd operator. Now the operator is a custom controller running in a pod and it watches the etcd cluster CR which we defined earlier. So the manifest file etcd operator deployment YAML lays out the operator pod specification, including the container image for the operator you're deploying. We're quickly going to see how that looks. See, if you notice that it does not define the spec for the etcd cluster, you will describe the desired etcd cluster to the deployed etcd operator in a CR once the operator is up and running. Now the deployment provides labels and a name for your operator. So some items that you will have to note are the container image to run in the deployments pods and the service account the deployments resources should use to access the cluster's Kubernetes API. So the etcd operator deployment uses the service account created for it. As usual, you can create this resource on the cluster from the manifest kubectl create-f command. I'm going to just clear the screen. So I'm just going to create the deployment YAML file. And once that is done, you can use the kubectl get deployments to check out the deployment. And you can see that the etcd operator deployment is ready. Now the etcd operator is itself a pod running in the deployment and you can see that starting up by using the get pods command. I'm going to clear the screen. So now that we have created a CRD defining a new kind of resource that is an etcd cluster. And finally, now that we have an operator watching the etcd cluster resources, you can declare an etcd cluster with your desired state. To do so, provide the two spec elements the operator recognizes, that is size, the number of etcd cluster members, and the version of etcd each of those members should run. You can see the spec stanza in the CR file. So I'm just going to check out the etcd cluster -cr.yml file. So this brief manifest declares the desired state of 3 cluster members, each running their own version of the etcd server. Now you can create this etcd cluster using the kubectl command that we did before, that we used before. So this will be etcd cluster cr.yml. Okay, and you can see that it has been created. And we're just going to check out the pods using the flag -w. This example etcd cluster is a first-class citizen, an etcd cluster in your cluster's API. And you can see that it is initializing and the pod is also initializing and now it's going to run. So you can see that the status of the cluster is up and running. With this, we come to the end of the session. So now let's move ahead and talk about the operators and how they've been adopted in various companies. A wide variety of developers and companies have adopted the operator pattern, and there were already many operators available that make it easier to use key services as components of your applications. Crunchy Data has developed an operator that manages PostgRE SQL database clusters. There are popular operators for MongoDB and Redis. Rook manages Ceph storage on Kubernetes clusters, while other operators provide on-cluster management of external storage services like Amazon S3. Moreover, Kubernetes-based distributions like Red Hat's OpenShift use operators to build features atop a Kubernetes core, keeping the OpenShift web console available and up-to-date.
After operators, we will cover Kubernetes Statefulset to manage stateful applications and ensure reliable storage.
So firstly, we will understand why do we need Statefulset in Kubernetes. So as I've already mentioned in the introduction, Statefulset is used to manage stateful applications. What it really does in Kubernetes is that it manages the deployment and scaling of a set of pods. So the pods that you create in Kubernetes is simply a collection of one or more containers and is the smallest unit of a Kubernetes application. So stateful set really manages the deployment and scaling of a set of pods. Okay. The second reason as to why stateful set is required in Kubernetes is that it provides guarantees about the ordering and uniqueness of these pods. Also, unlike a deployment, a stateful set maintains a sticky identity for each of their pods. Replica pods of MySQL, for example, are not identical. These pods are created from the same spec but are not interchangeable. Each has a persistent identifier that it maintains across any rescheduling. The persistent identifiers are predictable pod name like mypod0, mypod1 instead of hash fixed endpoint or individual DNS name. So when a pod restarts, while the IP address changes, the name and endpoint stay the same. Stateful sets currently require a headless service to be responsible for the network identity of the pods. That is, we are responsible for creating this particular service. And stateful sets do not provide any guarantee on the termination of pods when a stateful set is deleted. To achieve ordered and graceful termination of the pods in stateful set, it is possible to scale the stateful set down to 0 prior to deletion. The storage for a given pod must either be provisioned by a persistent volume provisioner based on the requested storage class or pre-provisioned by an admin. Now that we know why stateful set in Kubernetes is really important, let's move ahead and talk about what is Kubernetes stateful set. As I've already mentioned before, stateful set is the workload API object used to manage stateful applications. It basically manages the deployment and scaling of a set of pods and provides guarantees about the ordering and uniqueness of these pods. Like a deployment, a stateful set manages pods that are based on an identical container spec. Unlike a deployment, a stateful set maintains a sticky identity for each of their pods, and these pods are created from the same spec but are definitely not interchangeable. Each of them have a persistent identifier that it maintains across any rescheduling. We've already discussed these points in the previous part. Now, if you want to use storage volumes to provide persistence for your workload, you can use a stateful set as a part of the solution. Although individual pods in a stateful set are susceptible to failure, the persistent pod identifiers make it much easier to match existing volumes to the new pods that replace any that have failed. So in short, a stateful set is a Kubernetes controller that is used to manage and maintain one or more pods. However, so do other controllers like replica sets and the more robust deployments do. So what does Kubernetes use stateful sets for? A stateless application is one that does not care which network it is using, and it does not need permanent storage. Some of the examples of stateless applications may include web servers like Apache, Tomcat, etc. On the other hand, we have stateful applications. Now, if you deploy such applications on Kubernetes, you'll need to ensure that pods can reach each other through a unique identity that definitely doesn't change. Some examples of stateful applications include MySQL clusters, Redis, Kafka, MongoDB, and others. Now that we understand what is stateful set, let's move ahead and talk about the differences between stateful set and deployment. So at the heart of any Kubernetes deployment strategy lies the pod, the workhouse of distributed container solutions. The Kubernetes pod glues together a bunch of containers to a single networking stack and process namespace. Pod processes can communicate with one another over loopback and signal each other using signal mechanics. Deployments and stateful sets allow you to scale up your pods, roll out new images and configurations, and much more. But how do you pick which one to use for a given situation? It all depends on what you want out of your pods. So when your pods are interchangeable, you can use deployment. If scaling up means just run more of these, then you want a deployment. These are by far the most common in the wild, and they fit very nicely with application workloads and other 12-factor applications that share no state and have no need for identity. Let's say you have a deployment of a Rust-based web application. The load balancer out front routes traffic to the single application instance. The application itself keeps all state in the relational database behind it. So if you want to scale it, You have to just ask for more copies, as you can see in figure 2. Kubernetes Deployment Controller immediately springs into action, creating all of the new pods at once. Now, these new pods boot with the same environment variables set and the same config maps mounted in, presumably allowing them to talk to the database just like the first pod. The best use cases for deployments is when you want to use stateless application workloads and when you just want a single pod. Now we'll understand when to use Statefulset. The 12-factor never be responsible for the data approach is a great one for commodity computation, like the kind of workloads that make up API services, backend service brokers, etc. Eventually, somebody has to actually handle data in order to make the whole thing worthwhile. Now, to scale stateful systems, you need a stateful set. Now, let's consider the relational database system behind the applications. Ideally, we'd like to be able to scale it up and build some sort of consensus-based leader or follower topology. We can't really discuss the details of how this would work, but suffice it to say that one cannot hold elections without identity. When we scale the stateful set from 1 replica to 3, the stateful set controller starts to incrementally deploy a new missing pods one at a time. First, the pod 1 comes up initialized and then settles into a ready state. Then the second pod does likewise. One of the more powerful features of a stateful set is the use of persistent volume claim templates, a means to provide each pod in a stateful set with its own persistent volume. Now, if you're trying to replicate database contents, this is a critical capability. The best use cases for stateful sets are when you're working with data services like databases, key value stores, etc. Or if you're working with identity-sensitive systems like consensus systems, leader election clustering, etc., or anything that really needs a slow rollout. Now that we know the difference between when to use deployments and when to use stateful set, let's go ahead and check out a stateful set example. So now currently I'm working on my Linux virtual machine. So if you want to try this on Ubuntu, you can follow this procedure. So before we begin, there are some prerequisites. Firstly, you will have to download kubectl, you have to download Minikube, you will have to download Docker. All of the procedure you can find in their official website. So install all of that and then we can get started. So the first thing that we're going to do is I'm just going to start my Minikube using the command sudo minikube start. Okay, so once that is done, you can see that kubectl is now configured to use the Minikube cluster and default namespace by default. I'm going to clear the screen. So sometimes running Minikube with the default resource configuration results in inefficient resource errors. So to avoid those errors, you can also start Minikube with start -- memory 2048 -- CPUs is equal to 2. Or you could just use the Minikube start command. I've already mentioned that stateful sets require a headless service to be responsible for the network identity of the pods. And we are responsible for creating the service. Stateful sets are intended to be used with stateful applications and distributed systems. However, in order to demonstrate the basic features of a stateful set, what we're going to do now is we will deploy a simple web application using a stateful set. So we're going to use a web.yml file which creates a headless service called the JenkinsX service to publish the IP addresses of pods in the stateful set. So what we're going to do is I'm just quickly going to open my web browser. So I'm just going to copy this web.yml file and I'm going to paste it on my web browser so we can view the entire file, the YAML file. So I'm just going to explain this YAML file really quickly. So firstly, there is a headless service which is named JenkinsX that is used to control the network domain. The headless service is created by explicitly specifying none for the cluster IP. So for the headless services, a cluster IP is not allocated. This is what we'll have to remember. So the stateful set, which is named web, has a spec that indicates that has 2 replicas of the JenkinsX container, which will be launched in unique pods. We must also set the .spec.selector field of a stateful set to match the label of its spec template metadata lab. And the volume claim templates will provide stable storage using persistent volumes. So I know we haven't learned what is persistent volume, but it is simply a piece of storage in the cluster that has been provisioned by an administrator. So that's what a persistent volume is. Kubernetes creates one persistent volume for each volume claim templates. In our case, each pod will receive a single persistent volume with the default storage class and one GIB of provisioned storage. Now, when a pod is rescheduled or scheduled onto a node, its volume mounts mount the persistent volumes associated with its persistent volume claims. However, the persistent volumes associated with the pod's persistent volume claims are not deleted when the pods or stateful set are deleted. This must be done manually. When the Statefulset controller creates a pod, it adds a label statefulset.kubernetes.io/pod name that is set to the name of the pod. And this label allows you to attach a service to a specific pod in the stateful set. So I'm going to switch back to my terminal. First, what we're going to do is we are going to start with creating the stateful app. That is the stateful set along with the persistent volumes and the headless server. And we're going to do this using the kubectl apply command. So after the -f flag, I'm just going to paste the YAML link. So you can see that we have created the headless server and stateful set successfully, which is defined in the web.yml file. And I'm going to open another terminal. And here we are going to use the kubectl get command to watch the creation of the stateful sets pods with selector flag. So I'm just going to use the kubectl get command. And you can see an output that is very similar to this. So you can see the status, you can see if it's ready, the age of it, how it restarts, etc. All of that you can see here. Now the pods I've already mentioned in a stateful set have a sticky unique identity. This identity is based on a unique ordinal index that is assigned to each pod by the stateful set controller. Now the pods names take the form stateful set name ordinal index. Since the web stateful set have two replicas, it creates two pods, that is web0 and web1. You can see that on the screen, right? Now each of these pods have a stable host name based on its ordinal index. So as you can see that each pod has a stable host name based on its ordinal index. And we can also use the kubectl execution command to execute the host name command in each pod. Now when the pods restarted, the pods ordinals, host names, SRV records, and A record names have not changed, but the IP addresses associated with the pods may change. You can use the delete command to delete all the pods in a stateful set and wait for the stateful set to restart them and for both pods to transition to running and ready. And we can do this using the delete command. So I'm just going to first clear my screen. And I'm just going to use the kubectl delete command. So it says the pods have been deleted. Now what I'm going to do is I am going to use the get pod command. Now the status is currently terminating. That means it is deleting. Now again, if I execute the command, it says the status is container creating. So there's a lot of things that you can really do in stateful set. You can write to stable storage using the persistent volume claims for all of the pods. You can also scale up via stateful set using the kubectl scale stateful set. So this is all to begin with stateful set. Let's move ahead and check out its limitations. So the storage for a given pod must either be provisioned by a persistent volume provisioner based on the requested storage class or pre-provisioned by an admin. Also, deleting and or scaling a stateful set down will not delete the volumes associated with the stateful set. This is done to ensure data safety, which is generally more valuable than an automatic purge of all related stateful set resources. Stateful sets currently require a headless service to be responsible for the network identity of the pods, and you are responsible for creating the service, which can be sometimes a limitation. Stateful sets also do not provide any guarantees on the termination of pods when a stateful set is deleted. To achieve ordered and graceful termination of the pods in the stateful set, it is possible to scale the stateful set down to 0 prior to deletion. And when you're using rolling updates with the default pod management policy, it's possible to get into a broken state that requires a manual intervention to repair. So these are some of the disadvantages of stateful set.
Having learned about stateful sets, we will set up a multi-master cluster using Kubeadm to enhance cluster reliability.
Let's do a quick introduction to what is Kubeadm. Kubeadm provides you with a utility, or Kubernetes provides you with a utility called as Kubeadm to initialize and join your cluster. So in a way, it is a bootstrapping utility, and it helps you create a single master cluster, a multi-master cluster, and it takes care of making sure that the cluster that you create, it passes all the conformance tests that are given to us by Kubernetes. So if we take a look at this GitHub repository over here that we'll use to create a cluster, and I believe now we can start off with the actual demo on how to use Kubeadm to create a multi-master cluster. First of all, let's talk about prerequisites. As a part of prerequisites, we will talk about what sort of virtual machines do we need and what should be the corresponding sizing, OS version, and so on. First of all, we need 2 virtual machines for the master. The machines needs to be at least Ubuntu version 16.04. We'll be using Ubuntu as a primary OS. It needs to have 2 CPU, 2 GB RAM, and 10 GB storage. The second machine that we need 2 additional machines for the worker nodes. Once again, similar configuration, Ubuntu 16.04 plus, 1 CPU, 2 GB RAM, and 10 GB storage. So the master needs to have at least 2 CPU, and the worker can work with a single CPU. The load balancer machine will have exactly the same configuration as the worker nodes. So once again, Ubuntu 16.04 plus, 1 CPU, 2 GB RAM, and 10 GB storage. Apart from that, all the machines need to be in the same network. That means the machines need to be accessible from each other. In case if you're using any sort of cloud provider, just make sure that they are within the same VPC. The machines, or you also need to set up SSH connectivity between at least one machine, and for our demo we'll use load balancer. So the load balancer will have the actual private key, and the public key can be distributed across all the corresponding master and the worker nodes along with the load balancer node itself. We are not really going to have a demo on how to create SSH keys. I'm assuming that you already know how to set up SSH keys either on the virtual machines or on top of your cloud provider. You also need to have sudo privileges. That means you should be able to log in as root. And you need to set up SSH connectivity between the load balancer node and the master and the worker nodes. Something that is not a prerequisite, but it's good if you have it, because you will need to copy over certain files at the end of the demo. So rather than downloading the file from a virtual machine and then uploading it to the load balancer node, might as well set up SSH key beforehand. It will help you a lot in case you want to set up your own certificates. Once again, certificates are not something we won't cover over here. We'll only use a certificate given to us by Kubeadm. So now that we have talked about the prerequisites, let's take a look at how my cluster looks like. So I have 1 load balancer node and 2 master nodes and 2 worker nodes. As you can see, load balancer and the worker node, they have the same configuration, that is 1 CPU, 2 GB RAM, 10 GB storage. The master node over here has configuration of 2 CPU and 2 GB of RAM. The OS that I'm using is Ubuntu version 18.04, and I already have SSH setup between the load balancer node and the master and the worker nodes. So if I quickly go to my load balancer node over here, as a part of my load balancer node, I can do a quick SSH test by just running a simple script. So for I in master 1, master 2, worker 1, worker 2, and load balancer node itself, do ssh$i hostname to just verify if I can connect to all the machines using the DNS name. And that would also prove that I have network connectivity between my load balancer node and all the other master and the worker nodes itself. So all the nodes, they are within the exact same network of US West 1. So now that we have established the fact that I have my clusters, I have my machine set up, and I do have SSH connectivity, we can start off by setting up the load balancer. First and foremost, why do you need the load balancer node? The load balancer node is required to load balance between both the masters, which means that now that you have 2 masters, if you as an end user ever wanted to fetch some data from Kubernetes, for example, you just wanted to run a simple command like kubectl get pods, how do you exactly execute it? Are you going to execute it on the master, or are you going to tell Kubernetes that I want my output from, let's say, master 1? That's not really going to be the case, because your server right now, your cluster right now is highly available since you have multiple masters. The load balancer helps you in load balancing your request, or not just your requests, even the requests coming from your kubelet, and will distribute it across both the masters. And that's the primary reason why you would need to have a load balancer node. Now, the other question is, what sort of load balancer should you use? If you're working on top of a cloud provider, feel free to use your TCP load balancer. You can create a simple TCP load balancer on your cloud provider, and you can still use the same load balancer as a part of this demo. If not, if you want to create your entire cluster on premise, then you would need to leverage certain tools, certain load balancing tools like a F5 load balancer, HA proxy. Even a simple proxy pass using Nginx or Apache should also be fine for this demo. So as long as you have any utility that you can use to create a load balancer, that utility should be completely acceptable. As long as you have a front-end configuration and a back-end configuration, that's the only thing that you need. For this demo, we will be working with HA proxy as our primary load balancer. However, there are multiple demos available on the internet where they use Nginx, someone uses F5, and some other people also use the cloud-based TCP load balancers. So let's now start off by configuring our load balancer server, and we'll now install HA proxy. So first of all, let's log into our load balancer server, and we'll switch to root first of all, because we'll be performing the entire demo as root. So once we have switched to root, we'll then run an apt-get update and apt-get upgrade. Now this usually takes some time, so I'll pause my screen in between till the time the entire upgrade has taken place. So let me just log into my load balancer server first of all. I'm at my load balancer VM. I'll clear my screen so it is visible to everyone. And now I can start off by running my first few set of commands. I'm already logged in as root, so sudo -i I have already run using my own ID. And now I can run the second command, that is apt-get update and apt-get upgrade with the -y flag, so that I don't have to type yes after every whenever I'm prompted to. So I'll go to my load balancer node and just paste this command. And this will take a couple of minutes, so I'll pause my screen right now and I'll start as soon as the upgrade has taken place. As you can see, I got my prompt back and the upgrade is now complete. So that means I can just clear my screen over here so that everybody can see the next set of commands that we'll run. We'll go back to our GitHub repository and we'll run the next set of commands. So now that we have run the upgrade, we'll now start off by installing HA proxy, and then we'll configure the HA proxy to set up our front-end and the back-end configuration. To install HA proxy, we'll just run the command apt-get install HA proxy with the -y flag. We'll take this command over here and we'll go back to our load balancer node. And we'll paste the command so that HA proxy gets installed on our server. HA proxy is now installed. I've got my prompt back and I can just clear my screen over here so that we can run the next set of commands. So now that we have installed HA proxy, it's now time to tell HA proxy that what should be load balanced. So now we'll edit one configuration file, that is etc HA proxy haproxy.cfg. I'll just run this vi command. If you're not familiar with vi, you can use any other utility of your choice like gedit, nano, and so on. And I'll go right at the end of the file so that I can start adding my configurations. So I'm right at the end of the file over here. And we'll go back to my GitHub repository to understand what configuration are we actually going to put. As a part of load balancer or any load balancer, even if you're using load balancers on top of cloud providers, you always have two configuration. The first configuration is called as a front-end configuration, where you tell your system that where will the incoming request come to. So the incoming request can come from anywhere, to my system, that is 0.0.0.0 at the port 666443. Sorry. So the bind configuration is 0.0.0.0. That means my own system, my machine, that is my load balancer server, at the port 6443. Now why 6443? Because 6443 is the default port for API server. As part of architecture, we know that only the API server is the primary front end for the entire master control plane, which means that the only component that we need to load balance is the API server. And API server, the default port is set as 6443. The mode we are going to keep it as TCP. Now the default backend is a location that tells the front end server that where to route the request to. The default backend, we are giving it a name called as BE-API server, that is backend-API server. And the backend API server configuration is written right below the front-end configuration, that is the backend server BE API server. The mode once again is TCP. Then we have certain more additional flags that is required by our HA proxy configuration. The algorithm that we'll use is round robin. So it is going to use round robin algorithm to load balance between both the masters. And then we have the details about what are the servers that we are going to use. So server is master1, master2, that is the DNS name for my server. And then I have the corresponding internal IP address. So typically true when people are using cloud provider, you already usually have a combination of internal IP and an external IP. That is a private IP and a public IP. Always use the private IP address. It is much more secure. We don't really want to use a public IP address and let your connections flow through the internet. Once again, the port will be 6443 because master and master 2 are the location where your API server will actually run. Unless you want to configure a different port for your API server, I would suggest use a default port, that is 6443, and it will also perform a check at the corresponding port and the IP address. So these are the front end and the back end configuration on how you would set up your load balancer. So we can take the front end configuration from here, and we'll go to my load balancer server, and I'll just paste the configuration at the end of the file. And then for the backend configuration, I'll once again go back to the GitHub repository, take the backend configuration, and I will paste the configuration right below the front end config, right over here. Just one small note over here is that in case if the name of your servers are different, make sure you're using the DNS name or the host name of your server itself. In my scenario, the name of my server is master1, master2. Probably the name of your servers would be slightly different. So whatever server name that you have and whatever IP address that you have, make sure you change the configuration for backend and ensure that you're writing the correct configuration. That means the correct host name and the correct IP address. Make sure that you are making the corresponding changes and changing the value to fit your configuration. So now that we have added the front end and the back end configuration, I can go ahead and I can save this particular file. I'll save this file over here. And that's about it. I do not have to do any other changes at this point of time. So now that I've edited my configuration, I can just go ahead and I'll restart HA proxy so that it takes in all the configurations, all the latest configurations that we have added. So to restart HA proxy, we'll run the command systemctl restart HA proxy so that the HA proxy gets restarted. I'll take this command and I'm just going to paste it on my load balancer node. And this restarts HA proxy. And the next command is to just view the status of the HA proxy node so that it gives us either a running or a failed status. And as you can see, HA proxy over here is in active status at this point of time. So it's active, it's running, and it has started all the front end and the back end API server configuration that we have actually wrote in the HA proxy CFG file. So we can just just enter Q to quit from this attachment that happens after you run the systemctl status command, and I'll clear my screen so that everybody can see the next step of commands that we'll write. We'll go back to our GitHub repository page, and we'll just run one more command with the nc command, the netcat command, to see whether or not we're successfully able to attach to a server or not. So we can take this command nc-v to localhost, that means the host on load balancer node itself, at the port 6443. We'll go back to the load balancer server, and you should ideally get an output stating that the connection to the localhost at the port 6443 has succeeded, which means 6443 at this point of time is now active, is now serving incoming requests. So now that we have installed the load balancer, it's now time to configure the master and the worker nodes. For the master and the worker nodes, there are certain components that you have to install. And these components are Kubeadm, the executable itself, kubelet, and Docker. So the kubelet, Kubeadm, and the Docker binaries have to be installed on all the nodes. That means it needs to be installed on master 1, master 2, worker 1, and worker 2, not on load balancer. Load balancer configuration is almost complete. We'll keep the load balancer node aside, and now we'll start installing the remaining components on master and the worker nodes. Once again, whatever steps that we run as a part of this demo should be run on all the nodes. I will be running the demo on one of the master, either master 1 or master 2, and then you can replicate the exact steps across all the 4 nodes. So I'll be showing you how to run these steps on one of the masters, and then you can replicate the exact same steps, exact same commands on all the remaining nodes. So let's start off by logging into one of the master, and I'll be taking in over here master 2 as the primary master that I'll be working with. In master 2, you just have to log in as root. And after logging in as root, you have to run some sets of command. So first of all, we'll start off by running a simple apt-get update to update the current repository. So I'll take the command, run it on master 2. I got my prompt back. That means apt-get update has completed successfully. I'll clear my screen. I'll go back to my GitHub repository, and next step is to turn off swap. Turning off swap is one of a prerequisite for Kubernetes itself. That means kubelet configuration requires swap to be turned off. So we'll turn off swap on master 2. Then we'll start installing Kubeadm and kubelet. There are certain steps of command that we have to follow. First of all, we have to install certain OS-based dependency. That means we have to install certain packages like apt transport HTTPS and curl utility. So we'll take the first line of command. We'll just run it on our master 2 system. And it should install both the utilities, that is apt transport HTTPS and curl. I'll clear my screen over here. And we'll go back and now we'll start installing the two components, that is Kubeadm and kubelet. To install Kubeadm and kubelet, we first have to download a GPG key required for authentication, and we'll run the curl command to install the GPG key on our system. You should get an output called as OK. OK means that the GPG key that you have downloaded is now successfully registered in your system. The next step is to add the repository detail for the location from where you'll download the Kubernetes binaries or Kubernetes packages in your etc apt sources.list. So we can take the next set of commands, that is 3 lines over here from cat till eof, and we'll paste it on our system. This basically creates a single file, and the name of the file is at the first line itself, that is etc apt sources.list.d, and inside this directory you will create a file called as kubernetes.list. Run a simple cat command to see that the output is nothing but the second line that you have entered. That means this is the location from where you're going to download the packages required to install Kubeadm and kubelet. We'll go back to the repository and we'll run a simple apt-get update to update the latest repository detail that we have given. And the update command will add the latest repository from the new file that you have created, and will update its cache with all the new repositories that it must have found from the etc apt sources.list.d. And finally, we'll run the command apt-get install for kubelet and kubeadm. This usually takes more than a couple of minutes, so I'll pause my screen and I'll just start my screen back once the installation is completed. So I'll run this command on my system. I've got my prompt back, which means Kubeadm and kubelet are now successfully installed. I'm just going to clear my screen. And now we can run one last command that is apt-mark to hold the kubelet and the kubeadm binaries. So we'll run this command and this will hold a kubelet and kubeadm. Now that we have installed Kubeadm and kubelet, it's now time to move to the next set of instructions, that is to install the Docker component. We have taken the Docker installations directly from the docker.io website, directly from the installation steps. So something that you can actually refer to in case if you want to install any specific version of Docker. So we'll install the latest version of Docker, that is 19.x, whichever will be the latest minor version. We'll start off by running a simple apt-get command so it can install any prerequisite packages. So we'll take the apt-get install command for all the prerequisite package. As you can see, a couple of packages are already pre-installed when we wanted to install Kubeadm and kubelet. However, it's completely fine. We can rerun the package. It won't do anything to the already installed packages. So we'll take the apt-get install command till the software properties common, and we'll run it on the master 2 that we have been working on. And as you can see, everything is now installed. I can clear my screen once again. Go back to the repository, and similar to how we installed Kubeadm and kubelet, we'll follow almost similar steps, that is adding the GPG key, adding a repository, running an update, and then installing the corresponding Docker packages. So we can start off by step number 3, sorry, that is to add the GPG key. We got OK as an output. Next step is to add the repository details. We'll take this, we'll just paste it. This adds the repository details. Next step is to run an update. This will update the current repository with the latest repository of Docker. And then finally, we'll execute the command apt-get install for Docker CE, that is a community edition, along with the CLI and container D. So we'll take this, we'll execute it on our system itself, which installs almost all the packages required for Docker. Now, once again, this takes around a minute or two to complete, but I'll pause my screen in between. However, once again, guys, all these steps, they have to be performed on all the nodes. That means on master 1, master 2, worker 1, and worker 2. I'm showing you only on master 2. However, these commands need to be run on all the nodes itself. As you can see, my installation is almost complete. It's actually complete. I got my prompt back and I have successfully completed installation of Kubeadm, Kubelet, and Docker on master 2. Now we'll start off by installing them on master 1, worker 1, and worker 2 nodes. So I have now completed the installation on all the 4 machines. That means I've completed installing Kubeadm, Kubelet, and Docker on master 1, master 2, and my worker 1 and worker 2 nodes. So now that we have all the components installed, it's now time to bootstrap the cluster. And to bootstrap the cluster, we first have to start off with any one of the master, any master of your choice. You can either choose master 2 or you can either choose master 1. I'll be starting off with master 1 as my primary master. I'll first initialize my cluster on master 1. And to initialize the cluster, you have to run a command called as kubeadm init. The kubeadm init command is used to initialize a cluster. It basically takes in certain flags. And the flag it takes is called as a control plane endpoint flag. The control plane endpoint flag needs to be the value of your load balancer server DNS. So I'll be using the host name load balancer. In case if you do not have access to the load balancer using the host name, feel free to use the internal IP address. As long as the load balancer is able to connect to master 1 and master 2 both, a DNS name, host name, or even IP addresses should be completely fine. Along with the IP address or the DNS name, you also have to add the port of the load balancer that you have specified in the front end configuration. So in my scenario, I had specified the port 6443 because that is a default port of the API server. So in my case, the entire value of the control plane endpoint flag would be load balancer :6443. However, you can also use the IP address in case a host name is not directly accessible to you. So once again, we'll be using the Kubeadm generated certificate. So we will use the flag called as upload certs. And then the third flag that we'll provide is the pod network CIDR flag, which tells Kubernetes that what will be the pod network CIDR. That means what will be the IP address or what will be the CIDR or the subnet on top of which the IP addresses will be assigned to the pods. The reason why we are using 192.168.0.0/16 is because I want to use Calico as my primary CNI. And if you're not aware, then Calico's default configuration for pod network CIDR is 192.168.0.0/16, something that can be configured. But if you want to configure the Calico CNI to a different range of IP address, you will have to make the changes in this location. That means you have to make the change while initialization itself, and then you can make the change in the corresponding calico.yaml file. But for now, for the sake of this demo, we are going to use the default CIDR provided by Calico, that is 192.168.0.0/16. So once again, we'll be running this command only on one master. Now, please note that this command will generate a series of outputs, and these outputs are something you have to preserve because they will contain commands that you will have to run on worker nodes on the master 2 node, as well as the command that you need to run on your load balancer node. So it is going to generate a series of outputs. So make sure you preserve the output. Once you run this command, do not clear your screen. Preserve the output on master 1 because that will become a reference to what is to be executed on master 2, worker 1, and worker 2. So we can start off with this demo, and I'll pull up my master 1 node. So my master 1 node is right over here, and everything is once again installed on master 1, master 2, worker 1, and worker 2. That is Kubeadm, Kubelet, and Docker. I can take this command over here, that is kubeadm init control plane endpoint, and the value in my case will be load balancer :6443. Upload cert and the pod network CIDR will be 192.168.0.0/16. I can take this and I'll run this command over here so that it initializes my cluster. So I got my prompt back, which means that my initialization is now complete. As a part of my output, I get three major scenarios. The first thing it gives me is how to configure my kube config, which is pretty similar to how the kube config would be configured even on a single master cluster. The second thing that it provides me is the way to bootstrap other master, that means other control planes, as a part of my cluster, which means that I can run the Kubeadm join command on master number 2. The third thing that it provides us is with one another command that is going to bootstrap your worker nodes to the master 1 and the master 2 control plane. So if you take a closer look at what is really happening, is that step number 1 is something that I have to run on the load balancer node. The step number 2 is to join the master number 2. However, the bootstrap node will be the load balancer at the port 6443, which means that the join command is not for master 1, it is for the load balancer node. And the second join command that you see over here is once again joining to the load balancer node. That means all connectivity, all communication that will always happen through the load balancer node at the port 6443. We'll start off with step number 2. We won't start off with step number 1 right now. We'll create the kube config right at the end. However, I'm going to keep my screen as it is because this particular data is important for me because I have to take it and paste it on my master 2 and my worker 1 and worker 2 nodes. So I can start off by joining my master 2 as a part of the same control plane. I can take the command that is kubeadm join load balancer 6443 along with the discovery token and the control plane token. So that means all of you guys, whoever has completed this demo, can use their master 1 node as a reference, and you can take this command and you can paste it on master 2. So I'll go to my master 2 once again, logged it as root. I'm going to paste it over here so that it starts off with the prerequisite check and will then bootstrap the master 2 as a part of the same control plane. So as you can see, the master to join command is now complete, and the output that I get over here is that a node has joined a cluster and a new control plane instance has been created, which means that this master 2 has now joined my cluster as a separate control plane, which is communicated through using the load balancer and the port 6443 that we have configured on HA proxy. So I can go back to my master 1 once again, and I'll take the command to join the nodes. That means I'll take the last command, that will be the exact last command on your screen, kubeadm join load balancer 6443, and the corresponding token and the discovery token CAssert. I can take this command, I'll go to my worker 1, and I'll execute this command on worker 1. Similarly, I'll go to worker 2, and I will execute the exact same command on worker 2. I'll go back to my worker 1 to see what is happening, and as you can see, my worker 1 has now joined my master, and my worker 2 once again should give you a similar output saying that the worker 2 once again has now joined the master. The node has joined the cluster and some information about the certificates and what the kubelet and how the connection to the kubelet happened. And it gives you output saying that run the kubectl get nodes command on the control plane to see if the node has joined a cluster or not. So just for the time being, just to verify if everything worked correctly or not, I'm going to take these three lines. That's mkdir-p, that is to create a .kube directory, copying the admin.conf as config file inside the .kube directory, and changing the ownership. I'll just execute this on my master one itself. So I'll take these three commands and I will just execute it on the master over here so that I have my master setup to just run a couple of commands for verification. Now I can run a command called as kubectl get nodes to see what is really happening. So kubectl get nodes to quickly verify whether or not all the servers, that is master 1, master 2 and worker 1, worker 2 are bootstrapped or not. And as you can see the output over here, I see that all the 4 nodes, that is 2 masters and 2 workers, are now combined as a part of the same cluster. Even though the status is not ready, it will become ready once we install Calico on our system. So now that we have initialized the master, joined the master 2 as a part of the control plane, and joined the worker as a part of the entire cluster itself to work as worker nodes, we can now start off by basically configuring the load balancer node. To configure the load balancer node, we'll use the exact same commands or similar commands to what we did to configure master 1. We'll go back to the load balancer server once again, logged in as root, and now we'll start off by running the first command, that is to create a .kube directory at the home location. We'll run this. That's it. This creates a .kube directory on my home. So now that I have the .kube directory set up, the next thing that I need is basically to copy over the admin.conf file. I'll copy over the admin.conf file from master1 and I'll save it as a file called as config inside the .kube directory, which means that since I already have SSH set up, I can basically run the command scp from master1 and I'll give the path of etc kubernetes admin.conf and I'll store it at my current home location, that is $home/.kube/config. So basically, I'm just replacing cp-i with the scp command. In case you do not have SSH setup, you can just download the admin.conf file and you can upload it to the load balancer node, and you can basically rename it with the name as config inside the .kube directory. And this should copy over the file, so I can go inside cd.kube. Inside cd.kube, I should find the admin.conf file renamed as config. And finally, I can give the corresponding ownership. That is, I'll change the ownership to root, which is ideally already there. But however, if you're really not using a root user, you'd probably want to change the ownership in case you're using a non-root user. That means your own account. And I now have config setup on my load balancer node. So let's go back to our GitHub repository, and we have almost configured the entire cluster. We can scroll down to the steps that we have actually completed. We'll scroll down to configuring the kube config on load balancer node. We have completed these commands, that is creating the .kube, copying over the admin.conf to the corresponding location on the load balancer node. And now that we have also changed the ownership, it's now time to install the kubectl CLI. Kubectl CLI is the primary CLI that you will use to interact with Kubernetes. There are multiple ways to install CLI. We will use snap over here in order to install CLI, which is a pretty fast way to install any binary. So we'll use snap install kubectl --- classic to install the kubectl binary on the load balancer node. So I'll clear my screen and I will run snap install kubectl --- classic. It gets the latest version of kubectl and it installs it. Now we can run the same command that we ran on the master as well as and the worker nodes. We'll run kubectl get nodes to see if whether or not we are getting the corresponding output or not. This means that since we are getting the output, that means load balancer is functioning fine. It is load balancing between both the masters and giving us the corresponding output. And the final step over here will be to install the CNI, and the CNI that we'll install is Calico. So over here, we're installing the version 3.8 of Calico. However, you can install any CNI of your choice. Since we have already kept our pod network CIDR as 192.168.0.0/16, which is the default pod network CIDR defined in the Calico YAML, we don't have to make any updates. But in case if you have already made any update to the pod network CIDR, you can just download this calico.yaml file on your local system using a simple wget command. Edit this file, change the pod network CIDR, and then run the same command kubectl apply with the location on your system where your calico.yaml was downloaded. I don't want to make any changes, so I'll just run the same command kubectl apply -f and the network location of the calico.yaml file. It creates a bunch of entities in your system, some custom resource definition, and it creates your cluster role bindings, and deploys the actual Calico pod. It actually runs as a daemon set. However, you will have at least 4 pods running in the system. So I'm going to clear my screen. We'll just quickly run a command kubectl get pods -n kube-system to see what is happening in our system right now. I see that a lot of pods are running. Some are getting created, some are getting initialized. I'll just wait for a couple of more seconds to see if everything is running or not. Almost everything is running right now. One pod to go. And that's about it. I'll clear my screen. I'll run the command once again, kubectl get nodes, to see whether or not all the master and the worker nodes are in ready status or not. And at this point of time, our installation is now complete, which means that we have successfully configured a multi-master configuration, a multi-master cluster using Kubeadm. One final thing that we'll do is we'll just run one simple pod nginx, and we'll see how we'll be able to interact with the nginx pod. So kubectl run nginx --image equals nginx should download the latest nginx image from Docker Hub repository and should create an nginx deployment for us. So kubectl get deploy should show that you have one deployment of nginx running in a system, and kubectl get pods -ovide should show that you have one pod running, that is worker 2, and the corresponding IP address assigned is 192.168.189.65, which means that it is basically conforming to the pod network CIDR that we had set of 192.168.0.0/16. You can now run a curl command to this 192.168.189.65 from a node within your cluster. That means you can go to either master 1, master 2, worker 1, worker 2 nodes and run a curl command. So I can just go to my master 1, master 2, any node of my choice. I'll run a curl over here to this IP address to see whether or not I'm able to connect, and I'm able to get the entire output from the nginx pod. One thing to note over here is that you cannot run a curl command from the load balancer node, because ideally the load balancer node is not a part of your cluster. It just holds your load balancer. That means whatever Calico CNI that you have installed has only created a private subnet between master 1, master 2, worker 1, worker 2. That means you cannot run a curl command to the internal IP addresses which are local to only the nodes inside your cluster. Load balancer node will always be a node outside your cluster. So just to show you once again, a curl command over here will always get hung because this IP address block does not belong to the load balancer node. Just something to note, especially if you are using cloud providers, you might have to open up certain firewall rules even to access these ports, access these IP addresses from the machines in your cluster. So just a side note on that. And guys, I believe we have completed this installation.
With a multi-master setup, we will explore Kubernetes Storage to understand how to manage data persistence.
Challenges of data. Now, containers have changed the way we build, ship, and run applications. This transformative technology affords great velocity and application portability, but has also brought new challenges to technology teams. The challenge of persisting data in a transient system. As I've already mentioned in the introduction, Kubernetes is the leading orchestrator for container workloads. So let's discuss a particular scenario. What if a container stops for one reason or another? Kubernetes is definitely able to start a new instance almost immediately, making availability and recoverability something that happens in seconds as opposed to minutes or even hours. But this new instance of the application may not have access to the file system from the old instance, especially in the case of local file systems, so additional orchestration is required to ensure that the stateful component of the application is bound to the instance at restart. This focus on stateless applications and epithermal systems have prevented certain stateful and complex applications from being a good fit for this revolutionary technology. As companies look to bring applications into Kubernetes, the inability to persist data through a container's lifecycle is undesirable. People need a way of dealing with stateful applications and persisting data, all without inhibiting the positive aspects of the self-healing capabilities of the Kubernetes platform. Now, to get a better sense of how to address challenges in Kubernetes, we'll take a look at one of the earliest challenges that have been successfully addressed, that is handling log data. The Kubernetes community found a successful way to address log data by sending it to an external system. Now, by using solutions such as the Elasticsearch, Logstash, and Kibana stack, you have a pattern of leveraging an agent in a container alongside different applications. Now, the process enables developers to send logs to a standardized endpoint, which makes it portable and flexible. In the enterprise, moving storage into external system isn't something new or unique. The use of a storage area network, that is SAN, has been a staple practice of enterprises for a large number of years, but typically it has been implemented by delivering a pre-configured, dedicated volume to a virtual or physical machine. So now the next question that arises is, how do you provide a stable storage solution for any type of content with an equally composable and portable convention as the EKL pattern? Firstly, you do not want to inhibit your IT team's abilities to back up, recover, or secure the data either. Fortunately, this is where Kubernetes enters the picture. Its features and capabilities address this challenge as they are rapidly growing and maturing. Kubernetes began with the storage features as part of the pod API and soon expanded these into standalone interfaces, which include volumes, persistent volumes, storage classes, and container storage interface. In the previous sentence, if you noticed, I mentioned the word pod. You must be wondering what pod is, right? A pod is simply the smallest schedulable resource in Kubernetes. It is a logical collection of containers which ensures the encapsulated containers share resources and are hosted on the same node in your cluster. So typically a pod really contains of a single container and is an instance of an application. Now let's move on to the next topic of this session and discuss volumes in Kubernetes. The Kubernetes volume in its simplest form is a directory that's attached to a pod and mounted to one or more containers in the pod. Such coupling is tight and is a foundational construct for how data can be presented to a container. Now, because of this relationship with the pod, Kubernetes volumes are designed to have the same life cycle as the pod. If an epithermal volume is defined by the pod, for example, its contents do not survive a container restart. Now, when a pod is removed from Kubernetes, any volume relationships are broken and epithermal volumes will be destroyed. Kubernetes volumes are typed, which is how you define the storage mechanism backing the volume. Volume characteristics may be defined via volume type specific parameters. This may be a physical disk or path on the Kubernetes node, a SAN, a network attached storage, or even a storage service from a cloud provider, to name a few. So what really volumes do is it really allows applications to have a very defined storage part that stays consistent through the redeployment of a container. Okay, so this layer of abstraction really helps, but on its own does not solve all persistent storage concerns. There are many special volumes available for use like the empty directory, ConfigMap, secret. So all of these have their own advantages and can be used in many ways. When a pod is scheduled to run on a node, a volume is created on that node and will remain there until the pod is deleted or moved to another node. This volume is an empty directory volume that begins empty and is backed by the storage of the host itself. The other two types of ConfigMap and secret are volumes whose content is actually stored by Kubernetes. This mechanism is often used to pass configuration information, such as credentials, into a container and ensure they are available wherever the pod is scheduled to run. Now that we understand volumes just allow applications to have a defined storage path that stays completely consistent and same throughout the redeployment of a container, let's move ahead and talk about persistent volumes in Kubernetes. Now, as the relevance and utility of local storage options are literally exhausted, the need arises to leverage external storage. Individual nodes may have storage provided by a SAN, but that's not the same as being able to orchestrate the external storage along with the rest of the instructions for managing an application. Kubernetes here provides a persistent volume claim, which is a request for storage. So the request made by the persistent volume claim defines characteristics of the storage that are desired by your application, such as access and volume modes, size of volume, selectors, storage cache, all of that. In conjunction with PVCs, that is persistent volume claim, Kubernetes also provides a persistent volume resource. Okay, so a persistent volume has historically been a pre-provisioned storage volume, but more commonly is provisioned from a storage class dynamically and made available to the cluster for use by a pod. So persistent volume is simply a piece of storage in the cluster that has been provisioned by an administrator. And it also provides a persistent volume claim, which is basically a request for the storage. And you can see all of this represented in the diagram on the screen. In a Kubernetes cluster, when you create a storage class, you define provisioners, parameters, and reclaim policy. Provisioners are the utility or component responsible for interacting within the backend storage system, whereas parameters helps in the setting or values that you can pass to the provisioner. The reclaim policy instructs Kubernetes to either retain or delete the volume when it's released. If your volume is retained, you may need to perform your own volume cleanup and maintenance. To make storage systems support more extensible, plugin-based storage driver mechanisms are really important and necessary. So instead of only developing and shipping storage drivers as part of Kubernetes itself, storage vendors and users wanted a way to provide and use the drivers they need and to omit the ones they do not. So along came CSI and Flex Volume, which are the out-of-tree extension points for storage drivers. Both of these plugin types allow for administrators to deploy storage drivers that can be loaded dynamically by Kubernetes nodes, and both provide the ability to provision volumes of any number of storage types. Flex Volume was introduced first, but CSI is emerging as a more dynamic and comprehensive specification. Flex Volume is included for completeness. However, the convention is being only deprecated. Only use it if you must. On the other hand, the CSI specification outlines a number of storage operations in a way that can extend to additional container orchestration platforms. Now that we understood what are volumes and persistent volumes in Kubernetes, let's move ahead and talk about why do containers need storage. Okay, so when you think of adopting a new application architecture, such as, cloud native, it seems really logical to do with a new application. More times than not, however, you do not find yourself only developing new applications. If you're like most folks, you have to blend the traditional needs of applications and the functions they serve while applying emerging application architectures to improve speed, adaptability, and costs. Now, at this point, Kubernetes and the real world collide, and storage is a big part of this transformation. So I'm sure most of you are aware that you build business applications in containers. They implement business logic, automate decisions, and really set out to make our lives much easier. Your applications also produce a lot of data. It may be in the form of files, data tables, reports, and much more. Building small functional bits of logic into containers is a very good decision, but what would you do with so much data? Now, without storing data in a persistent volume, the file system of a container is also epithermal. Now, when a container restarts, the file system is reset to whatever the file system state is in the container's image, and files not stored in a persistent volume do not survive the restart. You really need a sustainable and supportable way to store data and objects in flight or as output from your applications while taking advantage of the portability, scalability, and recoverability of containers. Now, instead of fighting the natural tendency of containers to be stateless and lightweight, the pattern looks to augment Kubernetes to facilitate the behaviors we want. If your Kubernetes cluster has access to or is in public cloud providers such as AWS, you have the platform services that can provide block devices, file system as a service like Elastic File System, databases as a service like Relational Database Service, and object storage like Simple Storage Service. Now, each of these offerings have individual performance characteristics, that is, they have their own pros and cons, and you must align your application and workload with the proper type of storage for its needs. This alignment requires multiple unique methods and processes for orchestrating the various storage mechanisms, and not all are aligned with the way the application is orchestrated by Kubernetes. GCP, AWS, and Azure all have storage drivers in Kubernetes that help offload the concerns of managing and provisioning the platform storage services and provide a common interface in PVCs and storage classes. But how do you achieve parity for clusters running inside corporate data centers or for storage services you wish to use when a consistent experience in Kubernetes doesn't exist yet? There's one solution, which is to host your own storage system. So let's move ahead to the next part of the session and check out the storage solutions in Kubernetes. Hyper-converged infrastructure is the combination of compute, networking, and storage, all implemented as software and all deployed on the same nodes. Now, this software-defined approach introduces immense flexibility in the underlying hardware, eliminating dependency on specific vendors and specialized components. It also affords IT teams the ability to achieve portability and consistency of management and configuration. Rook is a storage orchestration for Kubernetes. It uses the declarative nature of Kubernetes to make storage services self-healing, self-scaling, and managed with similar conventions as your containerized applications. Rook uses a plugin extensible architecture to help you automate storage administrative tasks such as deployment, bootstrapping, configuring, scaling, provisioning, and monitoring. So what does this really mean? Rook allows you to use a declarative style of management that really empowers you to achieve as code capabilities for a multitude and various types of storage types. It implements the new necessary Kubernetes objects, so you have a common interface to provision storage software that provides object, block, and file system storage types. That is, Rook goes way beyond primitive storage types and also really enables you to orchestrate databases and other storage types in a claims-based fashion. This common way of dealing with volumes and now other storage types in Kubernetes is one way it is growing to orchestrate all of the storage types. So Rook on its own isn't a storage system. It must be coupled or collaborated with a portable storage subsystem or service. So Rook has operators to support the following storage backends, and one of it is Ceph. Ceph is a high-performance distributed storage platform designed to bring similar capabilities found in GCP and AWS to any cloud platform such as Kubernetes. It provides object storage, block storage, and distributed file systems backed by a single reliable storage cluster, which is running on commodity server hardware. Ceph is designed to be extremely scalable. It is based on the reliable autonomic distributed object store that is a self-healing system that distributes and replicates data safely across storage nodes. It then layers a distributed file system, block storage service, and S3 compatible object storage service on top of RADOS, that is the reliable autonomic distributed object store. So there's a huge advantage of using Ceph, that is, it is open source and purely software. It can really provide its rich set of storage capabilities and features when deployed across almost any server hardware and either hard drives, SSDs, or any combination of the two. It is widely used in a range of environments, especially private cloud deployments, but it can be complicated to properly provision and connect a Ceph system to Kubernetes. Rook simplifies the deployment and management of Ceph itself and also provides an extremely simple and Kubernetes native way to provision storage services. So some of the storage best practices are with the persistent volume settings, limiting the storage resource consumption, and definitely making requests and limits on the resources. So the persistent volume life cycle is independent of any particular container in the cluster. Persistent volume claims are a request made by a container user or application for a specific type of storage. So when you're creating a persistent volume, you will have to follow its rules. Okay. The next best practice is to limit the storage resource consumption. It is definitely advisable to place limits on the container usage of storage to really reflect the amount of storage actually available in the local data center or even the budget available for cloud storage resources. There are two main ways to limit storage, that is resource quotas and storage classes. The next best practice is to implement resource requests and limits. Kubernetes provides resource requests and resource limits that really help you to manage resource consumption allowed for individual containers in Kubernetes. So a resource limit can be specified for some temporary storage. Okay. So setting storage requests and limits can help prevent containers from being constrained by resource scarcity on container hosts or taking up too many resources unexpectedly. With this, let's move on to the case study. So the case study that we'll be talking about today is by using a cloud provider storage service to externalize data from the container. As you can see in the figure, you can see the implementation of the application and storage patterns in a progressive fashion. You can use each of these application and storage patterns in the HCI system. Okay. You can also see an application that consumes storage via a persistent volume. And if you move from AWS to a different provider such as Google, you can provision the application in the exact same way. However, if you're running Kubernetes on premises, there is no pre-existing storage service to consume. So here in the figure, an application is attached to a persistent volume backed by Amazon EBS. So now what the application can do is they can use a storage provided by Rook, Ceph, or another software-defined storage solution, which is in turn consuming compute and storage resources from any cloud provider. Okay, so it shows your application deployed to a hyper-converged cluster, and the diagram really illustrates your ability to make your applications portable across similar HCI clusters hosted in two different providers. It is really critical to point out that this is accomplished with only one set of orchestrations to manage applications and storage, thanks to the common interfaces and consistency provided by Kubernetes plus the Rook and Ceph combination. You can now move your applications as is between providers now. So the diagram that you see has an application that consumes persistent volumes that are provided by Rook Ceph in any environment.
After storage, we will discuss Kubernetes Ingress to learn how to manage external access to your services.
Firstly, we will understand why do we need Ingress. So when you're creating pods in Kubernetes, you assign selector labels to them. You can see these labels in this snippet of a deployment manifest on the screen. So this deployment.yml file, what it does is it creates 3 replicas that run the Docker image my app and assigns the app that is equal to the FOO label to them. Rather than assigning the pods directly, it is typical to group them under a service which makes them available at a single cluster IP address, although only from within the same cluster. The service also acts as a layer of abstraction that hides the epithermal nature of the pods, which can be scaled up and down or replaced at any time. It performs rudimentary round-robin load balancing. So, for example, on the screen, you can see the following service definition, which collects all the pods that have a selector label app is equal to FOO and routes traffic evenly among them. However, the service is accessible from inside the cluster only by other pods that are usually running nearby. So Kubernetes operator grappled with how to give clients outside the cluster access. The problem was pretty apparent early on, and 2 mechanisms were integrated directly into the service specification to deal with it. So when you're writing this service manifest, you can include a field that is named type, which takes a value of either node port or load balancer. So the example snippet that you can see on the screen sets the type to node port. So let's firstly talk about services with a node port. So this type are typically very easy. They essentially announce that they'd like the Kubernetes API to assign to them a random TCP port and expose it outside of the cluster. What makes this more convenient is that a client can target any node in the cluster using that particular port, and their messages will be relayed to the right place. For example, it's like saying you can call any phone in India and whoever picks up will make sure you get forwarded to the right person. The only downside is that the port's value must fall between the range 30,000 and 32,767, a range safely out of the way of well-known ports, but also conspicuously non-standard compared to the familiar ports 80 for HTTP and 443 for HTTPS. The randomness itself is also a hurdle, since it means that you do not know what the value will be beforehand, which makes configuring NAT, firewall rules, etc. just a bit more challenging, especially when a different random port is set for every service. So the other type of option that is available to set type is to load balancer. However, this comes with some prerequisites. It only works if you're operating in a cloud-hosted environment like Google's GKE or Amazon's EKS, and if you're okay with using that cloud vendor's load balancer technology, since it is chosen and configured automatically. The most costly disadvantage is that a hosted load balancer is spun up for every service with this type, along with a new public IP address, which has additional costs. So allocating a random port or external load balancer is easy to set in motion, but comes with various unique challenges. Defining many node port services creates a tangle of random ports. Defining many load balancer services leads to paying for more cloud resources than desired. It is definitely not possible to avoid completely, but perhaps it could be reduced, contained, so that you would only need to allocate one random port or one load balancer to expose many internal services. The platform needed a new layer of abstraction, one that could consolidate many services behind a single entry point. It was then that Kubernetes API introduced a new type of manifest called an ingress, which offered a fresh take on the routing problem. So it works like this. You write an ingress manifest that declares how you would like clients to be routed to a service. So the manifest here doesn't actually do anything on its own. You must deploy an ingress controller into your cluster to watch for these declarations and act upon them. Ingress controllers are just pods, just like any other application, so they're a part of the cluster and can see other pods. They're built using reverse proxies that have been active in the market for many, many years now. So you have your choice of an HA proxy ingress controller, an NJX ingress controller, and much more. The underlying proxy gives it layer 7 routing and load balancing capabilities. Different proxies bring their own set of features to the table. For example, the HA proxy ingress controller doesn't really need to reload itself as often as the NJX ingress controller because it allocates slots for servers and fills them in it at runtime using its runtime API. That can eventually lead to better performance. Being inside the cluster themselves, ingress controllers are susceptible to the same vault in jail as other Kubernetes pods. You need to expose them to the outside via a service with a type of either node port or a load balancer. However, now you have a single entry point that all traffic goes through, one service connected to one ingress controller, which in turn is connected to many internal pods. The controller, having the ability to inspect HTTP requests, directs a client to the correct pod based on characteristics it finds, such as the URL path or the domain name. So in short, Ingress is an API object that manages external access to the services in a cluster that is typically HTTP. Ingress may provide load balancing, SSL termination, and name-based virtual hosting. There are definitely some terms that you'll have to be familiarized with, such as node, which is basically a worker machine in Kubernetes, which is a part of the cluster. Also the meaning of cluster, which is a set of nodes that run containerized applications that are managed by Kubernetes. And edge router, which is a router that enforces the firewall policy for your cluster. This could be a gateway managed by a cloud provider or a physical piece of hardware. And I'm sure you know what a service means. A service is simply a Kubernetes service that identifies a set of pods using label selectors that we've already discussed in the previous part of the session. Cluster network is simply a set of links, logical or physical, that facilitate communication within a cluster according to the Kubernetes networking model. So what Ingress really does is it exposes HTTP and HTTPS routes from outside the cluster to services within the cluster. Traffic routing is controlled by rules defined on the ingress resource. So let's take a simple example where an ingress sends all of its traffics to one service. An ingress may be configured to give services externally reachable URLs, load balance traffic, terminate SSL or TLS, and offer name-based virtual hosting. An ingress controller is responsible for fulfilling the ingress, usually with a load balancer, though it may also configure your edge router or additional front ends to help handle the traffic. An ingress does not expose arbitrary ports or protocols. Exposing services other than HTTP and HTTPS to the internet typically uses a service of type service.type is equal to node port or service.type is equal to load balancer. So firstly, you must have an ingress controller to satisfy an ingress. Only creating an ingress resource has no effect whatsoever. You need to deploy an ingress controller such as Ingress NGX, or you can choose from a number of ingress controllers. Ideally, all ingress controllers should fit the reference specification. In reality, the various ingress controllers operate slightly different. So firstly, we will look at how a minimal ingress resource looks like. So as with all the other Kubernetes resources, And Ingress, as you can see, needs API version, kind, and metadata fields. The name of an Ingress object must be a valid DNS subdomain name. Also, Ingress frequently uses annotations to configure some options depending on the Ingress controller, an example of which is the rewrite target annotation. Different Ingress controllers support different annotations. The Ingress spec that you can see, that is the specifications, has all the information needed to configure a load balancer or proxy server. Most importantly, it contains a list of rules matched against all the incoming requests. Ingress resource only supports rules for directing HTTP or HTTPS traffic. So let's move ahead and talk about Ingress rules. Firstly, you'll need an optional host. Now in this example, no host is specified. So the rule applies to all inbound HTTP traffic through the IP address specified. If a host is provided, for example, foo.bar.com, the rules apply to that particular host. Secondly, a list of paths, for example, front/test path is required, each of which has an associated backend defined with a service.name and a service.port.name or service.port.number. Both the host and path must match the content of an incoming request before the load balancer directs traffic to the reference service. And finally, you'll need a backend, which is a combination of service and port names. HTTP and HTTP requests to the ingress that matches the host and path of the rule are sent to the listed backend. A default backend is often configured in an ingress controller to service any requests that do not match a path in the specification. With this, let's move ahead and set up Ingress on the default Kubernetes cluster, that is Minikube. So now what we're going to do is we are going to set up Ingress on Minikube. So before we move on, there are some prerequisites. Firstly, you will have to have Docker installed. You have to have an hypervisor installed. You will also have to have Minikube. You'll also have to have kubectl, that is the command line interface for Kubernetes installed along with Minikube. Okay, so if you want to install all of these tools, firstly, you will have to install Docker. And for this, you can just go to the official website of Docker and you can check out the version that you want to install. Now, currently, I'm working in the Linux virtual machine, so I'll want to install Docker for that. So I'm going to go to the official website of Docker. I'm going to click on Get Started button, which is present on the right-hand side. And if I just scroll down, you can see several options. You can play with Docker. You can sign up for Docker Hub, which is basically a website or a cloud-based application registry for collaboration purposes. So now what I'm going to do is I'm just going to scroll down and I'm just going to click on Docker Desktop. There are various options you can download for Windows. You can view for Linux engine. You can download for map. And I'm just going to click on for Linux. And this will redirect me to a page where I can just install the Docker engine, right? I have to install the Docker engine for the Ubuntu community, and I can just do that. So I'm just going to click on this. So this will redirect me to a page where I can install Docker. So if I scroll down and click on this link, I can install Docker engine on Ubuntu. Okay, if you want to uninstall the older versions, you can simply execute this command. If I scroll down, you can see that there are various ways you can install Docker into your Linux machine. The most convenient way to install Docker would be by using the repository. So there are some steps that you can follow, and you can update the app package index and then install packages to allow the apt to use a repository over HTTPS. Then you can add the Docker's official GPG key using this command. And then finally, you can execute this command based on your architecture, your system's architecture. And then finally, you can move on and install the Docker engine. If you want to install a specific version, you can just mention that too. You can select any of the versions that you'd like to install and then execute the command accordingly. Okay, once that is done, you can just verify that Docker engine is installed correctly by running the hello world image. And I'm just going to copy that. And since I've already installed Docker in my virtual machine, I'm just going to execute this command and check if Docker is up and running. you can see a message that says hello from Docker, and you can see that this message shows that your installation appears to be working correctly. That's great. So we have Docker installed in our virtual machine. Okay, now what I'm going to do is I'm going to open a new tab and I am going to install Minikube. Okay, so I'm just going to look for Minikube and kubectl. If I scroll down, you can see that there is a web page that says install tools, and I'm just going to click on that. So it redirects me to a page where you can choose the tools, the Kubernetes tools that you can install in your local machine. There's kubectl and there is Kind and there's Minikube. We don't really need to work on Kind and Kubeadm. So we're just going to be working on kubectl and Minikube. So that's what you will have to install first. So before you install Minikube, there are some prerequisites. Firstly, you'll need 2 CPUs or more. You'll need 2 GB of free memory. You need 20 GB of free disk space, internet connection. You'll need container or virtual machine manager such as Docker. That's the best thing. And also you will need Hyper-V or KVM or HyperKit, any of that, okay? And you'll also need a Hyper-V or KVM or VirtualBox or VMware, any of that installed successfully in your local machine. And once that is done, you can go ahead and install Minikube or you can install kubectl. So since I'm installing kubectl, which is simply a command line tool that will allow you to run commands against Kubernetes clusters, you can just click on the install Kubernetes option on Linux. And again, there are some prerequisites that you'll have to follow. And you can just scroll and you can see that there are 3 ways to install this into your local machine. The first one is you can install it by using the kubectl binary with curl on Linux. You can install using native package management, and you can also install using other package management. I would suggest or recommend you to install kubectl binary with curl on Linux. So there are a few steps. Firstly, you will have to download the latest version with the command. Then you have to validate the binary. And then finally, once the validation has been successfully done, you can install kubectl. Okay. And since I've already installed it in my VM, I'm just going to check the client version of kubectl. So you can see all the information of the client version, the Git version, the Go version, the platform that it is currently working on, the build date, all of that information is given here. That's great. So once you've successfully installed kubectl, we will go check out how to install Minikube. Okay, so first here you'll have to select your operating system. Okay, you have Linux, you have Mac OS, you have Windows, the architecture type, and there are 3 options. That is the binary download, the Debian package, and the RPM package. Again, I would suggest you to pick your choices according to what you're comfortable with, and then finally install Minikube on Linux. So as we all know, this is a cluster. Minikube is basically a cluster, right? So you can start your cluster by simply executing the Minikube start command, and then you can get on with the interaction. Okay, so what we're going to do is, since I've already again installed, I'm just going to execute the start command. Before that, I'll just clear my screen. So once I have cleared my screen, I'm just going to execute the Minikube start command. So as you can see that Minikube is up and running. It says kubectl is now configured to use Minikube cluster and default namespace by default. So that's great. We have a namespace that is created and that is named as default. We also have the Minikube cluster up and running. So I'm just going to clear my screen. And now what we're going to do is we are going to enable the NGX Ingress controller. As I've already mentioned in the previous part of this session, we will have to enable the Ingress controller. Then only we can move ahead and create our resource, right? So that's what I'm going to do. I'm just going to enable my NGX Ingress controller by using the command Minikube add-ons enable ingress. So for this command to execute, it's going to take you a minute or two. So I recommend you to be a little patient. And once that is done, you can see that the Ingress add-on has been successfully enabled. Okay. Once that is done, what we're going to do is we're going to verify that the NGX Ingress controller is up and running. For this, I'm just going to execute the command kubectl get pods -n kube system. So I've just opened the link and you can see that the output is hello world version 1.0.0 and also the host name has been specified. You can now access the sample application via the Minikube IP address and node port. Okay, so what we're going to do is we're going to access the application using the ingress resource. Okay, so firstly we will have to create an ingress resource, right? I'm just going to clear my screen. So there is a file which is an ingress resource that sends traffic to your service via helloworld.info. So first we are going to check out the file. So for that, I'm just going to go to my web browser. So I just have the link of the YAML file and you can see that the YAML file has the API version, the kind, the metadata, the specification, the rules. We discussed the rules, right? So all of that has been specified in this YAML file. Now what we're going to do is we're going to create this YAML file, right? So I'm going to switch back to my terminal and I'm just going to use the kubectl apply command. So I'm just going to type out the file that it has to fetch. I'm just going to cross check if it is right. And once that is done, I'm just going to execute it. So you can see that the example ingress has been created. Okay, so we're just going to verify the IP address is set. And for that, we're just going to use the command kubectl get ingress. So you can see that the example ingress has been created successfully and it hosts helloworld.info and there is an address, its ports, its age, all of that information has been given. Okay, so now what we're going to do is we're going to add the IP address to the bottom of the etc host file. So for that, what we're going to do is we are simply going to edit the file. I'm just going to execute the command vim host. Okay, so now that it is open, we can edit it. So once I get on the insert mode in this file, so I'm just going to add the IP address. So I'm just going to type in hello world info. So what this does is this sends requests from helloworld.info to Minikube. Okay, so I'm just going to click escape, save this file. So once that is done, what we're going to do is we are going to verify that the ingress controller is directing traffic. And we are going to do this using the curl command. You can see successfully the command has been executed. So if we shift to the browser, you can see that it's up and running. Okay, once that is done, I'm going to shift back to my terminal. So now what we're going to do is we are simply going to test our ingress. Okay, so in the next part of the session, we'll be testing our ingress. So testing is the absolute same way. You're simply going to be accessing using the curl command and it will just give you the output of what you are accessing. You can create many deployments and you can also add these deployments to your example ingress.yml file. And this will also be tested and it can also be applied.
Next, we will cover Helm charts in Kubernetes to simplify the deployment and management of applications.
Let's talk about what is Helm. You can think of these 3 points when trying to understand Helm. First, it is a package manager. Second, it deploys charts. And third, it reduces complexities. But what does that mean? Let's talk about these points one by one. First, Helm is like a package manager, but for Kubernetes. If you're familiar with installing via terminal in Linux, you can think of Helm as yum or snap, which helps you install packages. Helm does the same thing, but with Kubernetes. Second, it deploys charts. So, the charts or Helm charts are nothing more than a packaging format used by Helm. The chart is a file collection describing a set of Kubernetes resources. These Helm charts help you define, install, or upgrade your Kubernetes apps with ease. And lastly, Helm is meant to reduce complexities and chances of duplications. As the chart structure helps developer deploy apps faster without much coding, Helm provides structured way to manage Kubernetes applications with ease. Now, let's look at what is a Helm chart. To understand this, you must understand that Helm chart is a package. These packages contain YAML files that contain configuration and other necessary details for the application. These package, file, or chart are then used by Helm and then deployed on Kubernetes. This install or uninstall process is simplified using Helm. Thus, it makes deployments and management of applications easier. So, why is Helm used and when to use it? First, let's look at this key point. Even to make a simple deployment in Kubernetes, you need a minimum of 3 YAML files. Creating these files from scratch can be boring and time consuming. After you do this, you can make your deployment, and this is the same even if it is a very simple deployment. This is what Helm solves and why it is used to manage applications in Kubernetes. Once you install Helm and have it configured, you can install production-ready applications from software vendors such as MongoDB or MySQL with just one simple Helm install command. On top of it, if you ever need to remove installed applications, it is as easy as installing. Coming to the point about why Helm is used, it offers significant advantages. First, it simplifies deployments, and the process becomes seamless. It is easy using Helm charts to set override defaults in the values.yml file, allowing software vendors or admins of chart to define the base setting which is optimal for proper functioning. Second, it reduces complexity or duplication. Once the chart is built, it can be used over and over again. The fact that one can use the same chart for any environment reduces complexity of creating something for development, testing, and then for production. It boosts productivity. Software engineers are good at writing software, and the best use of their time is in writing software. Helm makes it possible to deploy softwares with single click and saves time and boosts productivity. And it smooths the Kubernetes learning curve. It is not a big surprise that learning for Kubernetes and containers is long. With Helm, this is simplified and allows developers to not require understanding every single aspect of Kubernetes objects. Now, let's talk about when to use Helm. Although from a high level, both Helm and Kubernetes operators do the same thing, you can think of using Helm for simpler deployments. The reason being is that as your team size grows and the project scales up, you might need direct control over your custom applications. Thus, many people agree to not using Helm for custom configurations. When working in an enterprise level, using Helm might make things more complex and hard to navigate through. But to make things clear, Helm can be used even with complex applications. It is just that sometimes it is preferred and sometimes it is not preferred. Now, let's look at the chart structure. You can create a chart in your terminal by writing Helm create followed by the name of your chart. After creating the chart, you will end up with a list of files in the directory of the chart name you provide. Here, we will be talking about three main things, which are the chart.yml file, the templates directory, and the values.yml file. So, let's look at these. The chart.yml file is a metadata file. This file contains information about the chart, including version and other such details. The values.yml is the default configuration file. This can be thought of as the heart of Helm, containing necessary configuration details for the chart that you create, and the template folder. This folder usually has a service.yml and deployment.yml. This folder contains the templates which are combined with values files and creates a valid Kubernetes manifest file. We will see all of this in the demo shortly. So let's dive right into the demo. And here we will install Helm first and then create our chart. After doing that, we will make a simple deployment using Helm install. So here I have my master and worker node set up, and all I'll do is SSH into my session. So here I have Kubernetes installed and configured. I can verify that using kubectl. As you can see, we are in the ready status and my worker node is connected and the master is the control plane. So here, the first step that we need to do is install Helm. You can find out the details by typing into your browser Helm install, and that will take you to the main page. As you can see, on this page, you can find how you can install Helm in your operating system. Since I am using Ubuntu, I can use either these commands, which are from here, or I can use the snap. Now, I'll be using this command because it's just one single command, and paste it into my master node. Now that Helm is installed, I can go ahead and create a chart. I do this by typing helm create followed by the name of my chart, which I'll say demo. And as you can see, we have created it. So as you can see here, this directory was created right about now. So now I'll just type in tree demo to see the directory. So it looks like I don't have the tree installed. So let's fix this. So now that I have tree installed, I'll go ahead and then type tree demo. So as you can see, this looks very familiar with the chart structure that we talked about before. Here we have the chart.yml file, we have the templates directory containing the deployment, service and other YML files, and then we have the values.yml file. So the objective of this demo is to create a very simple deployment, and what we are going to do is launch an NGINX service. So here what I'll do first is that I will edit the values.yml file, and to do that what I'll type is vi demo and then values.yml. So this is a basic configuration. Here what I'll do, as you can see here, I have my NGINX and all I need to do is configure it so that I can deploy it on my Kubernetes. So I'll make some basic configuration changes and later on I'll deploy it. To do that, I'll make some changes right here. And then I'll provide some override values. Next, I'll make it the type node port because I want this to be accessible. And now I'll go ahead and save all these changes. Now that it is done, all I need to do to launch this is type in helm install demo followed by the name of my chart, which I provided, and then I'll provide it with my directory, including the values.yml file. And with that, we get a confirmation saying it has been deployed. So what I need to do is type in these three commands to get the port number. So here I get the port number, that is 30563, and if I am able to curl this, it means that we should be successful. So as you can see, we get a response from our NGINX that we just deployed. We can again verify this by going to my browser and typing in my external IP address followed by the port name. And as you can see, our NGINX server was successfully deployed. In this way, you can launch applications using Helm in your Kubernetes clusters. This was just a simple demonstration, but even complex apps can be deployed using the same process. So feel free to experiment and do the same process, or maybe make some changes and try to figure out how things work in Kubernetes.
With Helm charts covered, we will look into JenkinsX CI/CD for Kubernetes to implement continuous integration and deployment.
What is JenkinsX?
So JenkinsX was created by James Strachan, who's also the creator of Groovy, Apache Camel, and was first announced in the year March 2018. It is designed from the ground up to be a cloud-native, Kubernetes-only application that not only supports CI/CD, but also makes working with Kubernetes as simple as possible. With one command, you can create a Kubernetes cluster, install all the tools you need to manage your application, create a build and deployment pipelines, and deploy your application to various environments. Jenkins is described as an extensible automation server that is configured via pipelines to be a continuous integration server, a continuous deployment hub, or a tool to automate just about any software task. JenkinsX provides a specific configuration of Jenkins, meaning you don't need to know which plugins are required to stand up a CI/CD pipeline. It also deploys numerous applications to Kubernetes to support building your Docker container, storing container in a Docker registry, and deploying it to Kubernetes. So this was the definition of JenkinsX. Now let us talk about the differences between Jenkins and JenkinsX. Unlike Jenkins, JenkinsX is a very opinionated and built to work better with technologies like Docker or Kubernetes. Having said that, both Jenkins and JenkinsX are deeply related, as everything that is done with JenkinsX can be done with Jenkins using several plugins and integrations. However, the best part of JenkinsX is that it simplifies everything. It lets you harness the power of Jenkins 2.0 using open source tools like Helm, Draft, Monocular, Chart Museum, Nexus, and Docker Registry to easily build cloud-native applications. In fact, it is this selection of tools and processes that makes JenkinsX unique and different from Jenkins and any other CI/CD solution. For example, JenkinsX defines the process, while Jenkins tends to adapt to which process that is needed. JenkinsX adopts to a CLI API first approach. It relies on configuration as a code and embraces external tools. And these tools are nothing but Helm, Monocular, etc. On the contrary, Jenkins has a UI first approach with the configuration via UI and drives everything heavily by internal plugins. Plus, the JenkinsX preview environments enables developers to collaboratively validate changes integrated into the code base by creating a running system per pull request. So these were the differences between Jenkins and JenkinsX. Now let us talk about the features of JenkinsX. The first feature is automated CI/CD. JenkinsX offers a sleek JX command line tool which allows JenkinsX to be installed inside an existing or a new Kubernetes cluster, import projects, and bootstrap new applications. Additionally, JenkinsX creates pipelines for the project automatically. The next feature is environment promotion via GitOps. JenkinsX allows for the creation of different virtual environments for the development, staging, and production using Kubernetes namespaces. Every environment gets a specific configuration list of version applications and configurations stored in the Git repository. You can automatically promote new versions of applications between these environments if you follow the GitOps practices. Moreover, you can also promote code from one environment to the another manually and change or configure new environments as needed. The third feature is the extensions. It is quite possible to create extensions to JenkinsX. An extension is nothing but a code that runs at a specific time in the CI/CD process. You can also provide code through an extension that runs when the extension is installed, uninstalled, as well as before and after each pipeline. The next feature is the serverless Jenkins. Instead of running the Jenkins web application, which continuously consumes a lot of CPU and memory resources, you can run Jenkins only when you need it. During the past year, Jenkins community has created a version of Jenkins that can run classic Jenkins pipelines via the command line with the configuration defined by the code instead of the usual HTML forms. And the last feature that we are going to discuss is the preview environments. Though the preview environment can be created manually, JenkinsX automatically creates preview environments for each pull request. This provides a chance to see the effect of changes before merging them. Also, JenkinsX adds a comment to the pull request with the link for the preview for the team members. So these were the features of JenkinsX. Now let us talk about the working of JenkinsX. So as you can see the diagram on the screen, so this is the overall architecture of Jenkins. what happens here is the developer commits and pushes the changes to the project's Git repository. JenkinsX is notified and runs the project's pipeline in a Docker image. This includes the project's language and the supporting frameworks. In the next step, the project pipeline builds, tests, and pushes the project's Helm chart to Chart Museum and its Docker image to the registry. Next, the project pipeline creates a PR with the changes needed to add the project to the staging environment. Then JenkinsX automatically merges the PR to the master. JenkinsX is notified and runs the staging pipeline. And in the final step, the staging pipeline runs Helm, which deploys the environment, pulling Helm charts from the chart museum and Docker images from the Docker registry. Kubernetes creates the project's resources, typically a pod, service, and ingress. So this was the overall working of JenkinsX. Now let us talk about the installation of JenkinsX. So in this session, I'm going to talk about installing JenkinsX on Windows as well as Linux platform. So if you talk about the installation on Windows, here the prerequisite is that you need Docker and Kubernetes installed on your system. So once you have the prerequisites completed, what you can do is you can right click on the menu and start the command prompt and run the following commands as an admin. So as you can see here, at the shell prompt, execute a PowerShell.exe command to download and install the Choco binary and set the installation path so that the binary can be executed. When you open the PowerShell, you have to execute this command here, as you can see. Once you run this command, you need to install JenkinsX using the Chocolate package, which is a third-party application. So the command for that is choco install JenkinsX. And you can update to the latest version of JenkinsX using the Chocolate by the command choco upgrade JenkinsX. So if you're using Scoop, then there's this command called scoop install JenkinsX or JX. And to upgrade the JX binary, you need to run the command scoop update JX. So these were the simple steps that you need to follow for installing JenkinsX on Windows. And if you talk about Linux operating system, these are the steps that you need to follow. So first, you need to download the JX binary archive using the command. This is the command. You need to run this command in the command prompt or the terminal of the Linux operating system. And if you don't have the JQ installed on your Linux OS, then you can run this command. As you can see here, this is the first step. In the second step, you install the JX binary by moving it to a location in your executable path using the command sudo mv jx user local bin. So this is the second step. And with this step, your JenkinsX installation is almost complete. And just to verify whether JenkinsX has been installed on your system, what you can do is you can run this command, which is the third step, jx space hyphen version. So if you run this command, you'll be able to see the latest version of Jenkins. So this was all about the installation of JenkinsX.
After JenkinsX, we will explore Kubernetes monitoring with Prometheus and Grafana to set up effective monitoring for your clusters.
Why use Prometheus? Before we answer this question, first let us understand what is Prometheus. Now, Prometheus is an open source systems monitoring and alerting toolkit that was originally built at SoundCloud. Since its inception in 2012, many companies and organizations have adopted Prometheus, and the project has a very active developer and user community. So if you have any queries, you can address them to the community, and I'm sure you'll have a very quick response. It is now a standalone, currently it is a standalone open source project and maintained independently of any company. To emphasize this and to clarify the project's governance structure, Prometheus joined the Cloud Native Computing Foundation in 2016 as the second hosted project after Kubernetes. Prometheus is free and an open source event monitoring tool for containers or even microservices. It collects numerical data based on the time series. So the Prometheus server works on the principle of scraping. This invokes the metric endpoint of the various nodes that have been configured to monitor. Now, these metrics are collected in regular timestamps and stored locally. The endpoint that was used to discard is exposed on the node. Prometheus works very well for recording any purely numeric time series. That is, it fits both machine-centric monitoring as well as monitoring of highly dynamic service-oriented architectures. Now, in a world of microservices, its support for multi-dimensional data collection and querying is a particular strength. It is designed for reliability to be the system you go to during an outage to allow you to quickly diagnose problems. Now, as we've already discussed, each Prometheus server is standalone, not depending on network storage or other remote services. You can rely on it when other parts of your infrastructure are broken, and you do not need to set up extensive infrastructure to use it. Prometheus is a pull-based tool. There are basically two kinds of tools that are currently present, that is a pull-based and a push-based tool. And Prometheus, as you can already see, is a pull-based tool. And as I've already mentioned in the previous slide, what the Prometheus server does is it works on the principle of scraping. That is, it invokes the metric endpoint of the various nodes that have been configured to monitor, and these metrics are collected in regular timestamps by pulling. Finally, the endpoint that was used to discard is exposed on the particular node. Now let's move ahead and understand the main reasons as to why one should use Kubernetes. Now, two technology shifts took place in the past few years that created a need for a new monitoring framework like Prometheus. The first shift that took was the DevOps culture. Now, prior to the emergence of DevOps, monitoring consisted of hosts, networks, and services. But now what developers need is the ability to easily integrate applications and business-related metrics as an organic part of the infrastructure. And this is because they are more involved in the CI/CD pipeline and can do a lot of more operations debugging on their own. Monitoring needed to be democratized, making them more accessible and cover additional layers of the stack. And the other technology shift that resulted in needing a new monitoring frame is containers and Kubernetes. Container-based infrastructures are radically changing how we do logging, debugging, high availability, etc. And monitoring is definitely not an exception. Now you have a huge number of volatile software entities, services, virtual network addresses, and exposed metrics that suddenly appear or vanish. Traditional monitoring tools are not designed to handle this. Now the question that arises is, why is Prometheus the right tool for containerized environments like Kubernetes? These four characteristics made Prometheus the de facto standard for Kubernetes monitoring. The first one is because of its multidimensional data model. The model is completely based on key value pairs, similar to how Kubernetes organizes infrastructure metadata using labels. It basically allows for flexible and accurate time series data, powering its Prometheus query language. The second reason is it has accessible format and protocols. Exposing Prometheus metrics is a pretty straightforward task. Metrics are human readable in a self-explanatory format that we'll see later on in this session and published using a standard HTTP transport. Later on in this session, we can check the metrics that are currently exposed by using our web browser. The third reason is it allows service discovery. Now, the Prometheus server is in charge of periodically scraping the targets so that applications and services do not need to worry about emitting data. That is, metrics are pulled, not pushed. These Prometheus servers have several methods to auto-discover scraped targets. Some of them can be configured to filter and match container metadata, making it an excellent fit for epithermal Kubernetes workloads. The last reason is because of its modular and high available components. Metric collection, alerting, graphical visualization, all of these are performed by different composable services in Prometheus itself. Now, all these services that I just mentioned are designed to support not only redundancy and also sharding. So now that we know what is Prometheus and why we need to use it, let's move ahead and understand what is Grafana. Grafana is a multi-platform open source solution for running data analytics, pulling up metrics that make sense of the massive amount of data, and to monitor our applications with the help of some cool customizable dashboards. What it really does is it helps you identify and tackle performance issues by giving you the tools you need to analyze and monitor your database. Not only does it help solve problems, but it also aids you in becoming proactive with your maintenance by using alert system management. Grafana is open source, compatible with a wide range of databases, and has a thriving community. It also supports a huge number of data sources, and since the application is open source, You can be sure that the moment a new data source has been released, someone out there is adding support for it. The most common use case of Grafana is displaying time series data such as memory or CPU over time alongside the current usage data. Now that we know that Grafana is simply a data visualization tool, let's move ahead and talk about some of its prominent features. The first one is visualize. From heat maps to histograms, graphs to geomaps, Grafana has a plethora of visualization options to help you understand your data very clearly. The second one is alert. Grafana seamlessly defines alerts where it makes sense while you're in the data. It defines thresholds visually, and it can also send you notifications via Slack, PagerDuty, and much more. The third feature is unify. You can bring your data together to get better context. That is, Grafana supports dozens of databases natively. You can also mix them together in the same dashboard. The fourth feature of Grafana is that it is open source. Grafana gives you options. It is completely open source and backed by a vibrant community. You can also use Grafana Crowd or easily install it on any platform. Moving ahead, let's discuss and talk about Kubernetes monitoring architecture. Now, as you can see, there is a Kubernetes API. There are Kubernetes nodes. In the middle, we have the Prometheus server. We have the Prometheus alert manager. And then finally, we have Grafana. Now, in the first step, the Prometheus servers need as much target auto discovery as possible. And there's several options to achieve this. That is via Prometheus Kubernetes Service Discovery, or the Prometheus operator and its custom resource definitions, or even Consul SD, Azure SD for Azure VM, GCE SD for GCP instances, EC2 SD for AWS VM, and also File SD. Apart from the application metrics, we also want Prometheus to collect metrics related to the Kubernetes services, nodes, and orchestration status. For example, node exporter for the classical host-related metrics like CPU, MEM, network, etc. And also kube state metrics for orchestration and cluster-level metrics for deployments, pod metrics, resource reservation, etc. And finally, Kubernetes control plane metrics like kubelet, etcd, DNS scheduler, etc. Prometheus can basically configure rules to trigger alerts using PromQL. Alert Manager will be in charge. Now moving on to step 4, Prometheus can configure rules to trigger alerts using PromQL. Alert Manager will be in charge of managing alert notifications, ping, inhibition, etc. Now the Alert Manager component configures the receivers and gateways to deliver alert notifications. Finally, Grafana can pull metrics from any number of Prometheus servers and display panels and dashboards, that is the visualizations of data. So this is the basic architecture that you see. As we've already discussed, Prometheus and Grafana are pull-based tools. So all of these metrics that they want to scrape are pulled from their respective targets, and then they're finally displayed based on visualizations or metrics, anything. Along with Prometheus and Grafana, we'll be making use of Helm, which helps you manage Kubernetes applications. Helm charts here help you define, install, and upgrade even the most complex Kubernetes applications, and this is exactly why we need to be working with it today. With this, we'll move ahead to the demo part of the session and install all of the tools that we'll be working with in this session. So now for the demonstration part, I'll be working on my Ubuntu virtual machine. So there are some prerequisites before we get on this demonstration. So the first thing is that you will need a Kubernetes cluster up and running. Kubernetes has a local cluster that is Minikube. So I have both Minikube and the command line interface tool that is kubectl installed on my virtual machine. So that is one thing. The second thing is you'll have to download Helm. As we've already discussed, Helm is basically a package manager for Kubernetes, where developers develop and manage Kubernetes using the Helm chart. Okay. So now what we're going to do is we already have Minikube and kubectl installed on the VM, but we do not have the Helm chart up and running. So firstly, I'm going to check out the Minikube version for you all to know which version I'm currently working on. You can see that I'm working on Minikube version v1.20.0. Okay, so now let's start Minikube. I'm going to use the command sudo minikube start for this. And as you can see that Minikube is up and running. We have configured to use the Minikube cluster, and we have one default namespace that is named default itself. Okay. Now that we have Minikube up and running, I'm just going to clear my screen. So now what we're going to do is we are going to view all the namespaces that are available in the Minikube cluster, and I'm going to do this by using the command kubectl get ns, that is namespace. So once that is done, you can see that there's a default namespace which is active and created 13 hours ago. You can also see some namespaces. You can also see kube node lease, kube public, and kube system namespaces. So now what we're going to do is we are going to go and download Helm tool in our VM. So I'm just going to quickly switch to my browser, and I'm just going to look for Helm. So this is the first result, and as you can see, you have Helm, the docs, charts using Helm, the architecture, and installing. So I'm just going to click on installing. This will redirect me to the official website of Helm, and this entire guide really shows how you can, download Helm into your OS. So there are various OSs that Helm can be installed within, that is Mac, Linux, or even Windows. So there are basically two ways to install Helm. The first one is the official methods to get the Helm releases, and the second one is through different package managers. Okay. So installation through these methods can be found on this page. So you can download Helm from the binary releases or from script or through package managers. Okay, so I'm just going to download it from the binary releases. And for this, there are 3 steps that can be followed. So the first step will allow you to download your desired version, and then you can unpack it and then find the Helm library in the unpacked directory and move it to the desired location, that is user local bin. So I'm just going to open this page, and this will take me to GitHub, where all of the Helm releases have been put into. So currently I need to download Helm Linux AMD 64. So I'm just going to click on that. This will download a tar file of the Helm package. I'm just going to say okay. I'm just going to click on this, and I'm going to click extract. And this will allow me to untar it right here. So I can extract the file. So I can extract or unpack my package right here. So I'm just going to click on the extract option. I'm okay with extracting my file in home. I'm just going to say show the files, and you can see that it's been extracted. Okay, that's great. I'm just going to close this window. Now that we have unpacked it too, we can skip this step, directly move the Helm binary into its desired location, that is user local bin Helm. Now I'm quickly going to switch back to my terminal, and I'm just going to paste this command. So we're using the move command, that is mv, to move the file into the desired location. Okay. So once that is done, we have our Helm binary in our user local bin location, our desired location. Okay. So now that we also have the Helm binary in our VM, so now we're going to get started with the next part of the session. So the first thing that we're going to do is we are going to check the status of Minikube using the Minikube status command and check if it's up and running. So you can see that it is all configured and running. So what we're going to do now is we are going to look at our namespaces that are available, which we have already. So these are the namespaces that we currently have. So what I'm going to do now is I'm going to create a new namespace. Okay. So for that, I'm just going to use the command kubectl create namespace Prometheus. So I'm just going to use the command kubectl create namespace to create a namespace that is named Prometheus. All right. I'm just going to enter, and it says a namespace Prometheus has been created. Okay. Now, if you want to view the namespaces, I'm just going to use the kubectl get ns command, and you can see that the Prometheus namespace has been created. It's active, and its age is 12 seconds. So once we have created our namespace, so now what we're going to do is we're going to install the Prometheus operator. Before that, we'll need to have the Prometheus Helm chart installed successfully in our VM. So we're going to do that. I'm just going to clear the screen. So for this, I'm going to use the sudo helm repo, that is repository add. We're going to add a new repository and name it whatever you want to. So we're going to add a repository that is named monitor. And I'm just going to use charts.helm.sh/stable. So I'm just going to use the Helm repository add command to add a new repository that is named monitor. And I'm just going to add the link to from where the charts can be installed from. Once that is done, I'm just going to click enter. So you can see that monitor has been added to your repositories. Now we're quickly going to update our repositories using the Helm repository update command. So just going to add all of the latest information into our repository. So once that has successfully completed, what we're going to do is, so finally we're going to install the Prometheus operator into our local machine. Okay. And now we need to make use of the Helm chart of the Prometheus operator to deploy Prometheus and Grafana and many other services, in fact, that have been used to monitor Kubernetes cluster. So for this, we're going to use the command helm install Prometheus monitor. This is the repository name, /Prometheus operator. So we're going to just specify the namespace that it has to be installed within. So you have the helm install command, and we are going to install Prometheus into the monitor repository, and I'm going to click enter. So now you can see that the Prometheus operator has been installed successfully, and you can check its status by running this command. So before we do that, what we're going to do is we are going to check the pods that have been installed in our namespace Prometheus. So for this, you can just use the command kubectl get pods -n Prometheus. So the flag that we specify here, that is -n, allows us to choose our namespace. So if you want to, find the pods of the default namespace, you can just specify this flag and then mention the name for it. So we're just going to check out the pods that are currently present in Prometheus. You can see that we have the alert manager that's running, we have Grafana, we have Kube state metrics, we have Prometheus node exporter, we have the operator, we also have Prometheus running. Okay, so this is great. So what we're going to do is we're going to activate the Prometheus server. And how do we do this? We're just going to simply use the command kubectl port forward, and we're going to specify the namespace. We're just going to copy this entire pod name, and I'm just going to paste it. So you have to specify the namespace that you're working on and repeat. So we're just going to use the kubectl port forward command. We're going to specify the namespace, specify the name of the pod, and then finally specify the port that it can run on. Okay, and I'm going to quickly switch to my web browser, and let's check out if Prometheus is up and running. This is how the Prometheus time series looks like. There's a navigation bar on the top. You can see alerts, you can see graph, you can see the status, you can see different rules, targets, the service discovery. You can also get help from the Prometheus community, and you can add an expression here. You can execute it and view it in graph or in the console. So if you click on the insert metric at cursor option, you get many queries that you can work with. Now, if I want to check the kubepod info, okay, I'm just going to execute this command, which shows the node count and the value is currently 1. If you want to check out the graph, you can just click on the graph option and it will execute the graph. Okay. And if you want to see the memory available, okay, the sum of the memory that is available, you can execute this command and you can see the value on the right hand side. There's several other queries that you can execute. and we're going to do that now. We will check out the namespaces that has been created. Okay, so you can see the instance, you can see the namespace. As we've already noticed and seen before, we had 4 namespaces initially. One is the default namespace that is created by Minikube. Then we had Kube System, then we had Kube Node Lease, and then we had Kube Public. But we created manually. So, and we created Prometheus. So we have 5 namespaces. That is great. Also, if you want to check out the node information, you can execute this command. And you can see the container runtime version, that is Docker, the endpoint. You can also see the job. All of that can really happen within the Prometheus. Now, if you want to create your own rules, you can create them henceforth from here onwards. You can see the alert manager rules. You can also see the etcd rule that is present in Kubernetes. You can see the K8 rules, that is the Kubernetes rules. All of that can be accessed via the status option. You can also see the targets. Currently, we have the alert manager up and running. We also have the API server, which is up. You can see that the kube controller manager is down. All of the statuses of each of these targets also can be viewed in this command. So this is a pretty important option in Prometheus itself. If I want to view the command line flags, I can just check them out here. You can see what port it is running on, the external URL, all of that can be viewed here. Then when I click on the runtime information, you can see that the working directory is Prometheus, and all of the information, the Go version is mentioned here, and the Prometheus version is also mentioned here. You can see the number of series in the alert managers. You can see the endpoint. All of that can be viewed here. Okay. Now I'm just going to click on Prometheus. So all of the monitoring part of the data can be done on Prometheus. Let's move ahead and talk about Grafana. So for this, what we're going to do is we're going to quickly switch back to this. Okay, I'm going to clear my screen. So what we're going to do is the Prometheus operator itself installs Grafana and Prometheus with other deployments, right? We saw that. Now with the installation of the Prometheus operator, Grafana is also installed with it. We can access the Grafana dashboard by the port forwarding the Grafana pod. So we're just quickly going to view the pods that are present in the Prometheus namespace. Once that is done, we're just going to use the kubectl port forward command. So we're just going to add the Grafana pod in this. I'm going to quickly copy paste this option. And I'm going to click on port 3000. Now what I'm going to do is go to my web browser and we will look for what's there in port 3000. Okay. You can see that there is a welcome page to Grafana, and also it will prompt you for a username and password. Now to find out this username or password, what we're going to do is we are going to switch to our terminal. And we are going to use the get secret command to, check out the password and the username. So I'm just going to type that out. Kubectl get secret. I'm going to specify the namespace. So you will get the admin password and also the admin user here. So as you can see that the secret data is encoded with base 64 and you can only decode it so by using a certain command. But before that, if you notice that the admin password has been decoded and also the admin user has been decoded. So what we're going to do now is we are going to get the username using the command OpenSSL base 64 -d. So this is taking a considerable amount of time to load. I'm just going to clear my screen. So now what we're going to do is we're going to just use another command. So we're going to execute the command and get our admin user and password. Once that has been executed, we are just going to check out the admin username. Okay, so we are just going to echo this and base64, and you can see that the admin username is admin. Okay, and the same thing we're going to do with the password. Okay, we're just going to type in echo and add in the password. and decode it using base64. You can see that the password is prom operator. So I'm just going to execute the command kubectl port forward, and I'm just going to execute this. So we'll quickly switch to our login page, and you can see that the username is password and password is prom operator. So once you're logged in, you're redirected to the Grafana page, and here you can see that this is the basic structure of Grafana UI. You have panels that you can really move around with and play. You can increase them in size, you can decrease them in size, most of it is made of panels. If you scroll down, you can see some, information from their blog and community. You can add your first data source, you can create your first dashboard, and you have some icons that are present on the side. You can search for any dashboards that you create. You can create dashboards, add folders, import data. Also, you can manage your dashboards and your playlists, your snapshots. You can explore, you can access alerting. In the configuration options, you can add data sources. You can search for data sources or add whatever you'd like to by clicking on the add data source option. You can check out the user. If you want to create teams, you can do that. You can check out the various plugins that are available, the preferences, and API keys. Okay. So this is the brief overview of how Grafana user interface looks and how it really works too. So now what we're going to do is I'm just going to click on dashboards and click on manage. So by default, Prometheus operators are deployed with some pre-configured Grafana dashboards. And to see this, you can click on manage on the dashboard options and you can see the default dashboards. So if I want to click on compute resources namespace, this will give me a complete overview of the CPU utilization, the memory utilization, and you can see the CPU usage in the form of a very colorful graph. And you can also see the CPU quota, you can see the memory quota, the network. You can really, see these panels if you want to. You can move these panels, you can arrange them however you'd like to. All of them can be done with these default dashboards that are available. Now, there are several dashboards that are available. Now, if I want to see the volumes, I can also click on this option. Okay, and you can also create your own dashboard. You can add your own data source via Prometheus, and then you can really make your own dashboard. So let's move on to the next part of this session.
With monitoring setup, we will explore Google Kubernetes engine to see how it is managed on Google Cloud.
What is Google Cloud Platform? Google Cloud Platform is a suite of cloud computing services and management tools offered by Google. GCP runs on the same cloud infrastructure that Google uses internally for its end-user products such as Google Search, Gmails, Google Photos, and YouTube. GCP is one of the leading cloud service providers along with Amazon Web Service and Microsoft Azure Cloud and owns 7% of the total cloud market share. Gartner has positioned Google as a Magic Quadrant leader among the furthest 3 positioned vendor. Google Cloud's global network spans across 25 regions with 76 zones and is available for the users from over 200 plus countries and territories. Now, a region is a specific geographical location where you can host your resources. A region can have 3 or more zones. Also, many enterprises are increasingly adopting Google Cloud Platform because the services offered by Google Cloud are more secure and cost-effective. Now, let us take a look at the core services provided by GCP. First is the Google Compute Engine, which is Google Infrastructure as a Service virtual machine offering. It allows customers to use powerful virtual machines in the cloud as server resources instead of acquiring and managing server hardware. Second is the GCP Cloud Storage. It can store the entire organized databases, raw video streams, and even the matrix for machine learning models. It is an object storage system. Its records maintain both the identity and the structure of any class of data given to it. Third is networking. Now, GCP provides tools that makes it easier to manage and scale your networks. It provides a single place to publish, discover, and connect all application services, reducing the management and operational complexity. The next service domain is big data. Now, GCP provides multiple services like Dataflow, Dataproc, and Data Fusion to help you create a complete cloud-based big data infrastructure that supports big data storage and analysis. The advantage of hosting big data infrastructure in the cloud is that it provides unlimited data storage and easy option for parallel big data processing and analysis. Next, GCP also provides all the tools developers and the development team need to be productive while writing, deploying, and debugging applications hosted in the Google Cloud. The next service domain is identity and security. With GCP IAM, you manage access control by defining who has what access for which resources. It lets the administrator authorize who can take action on specific resources, giving you full control and visibility to manage Google Cloud resources. Next is the GCP IoT service, which provides an intelligent IoT platform which is scalable, fully managed, and integrated. It lets you connect, store, and analyze data at the edge and in the cloud. The next service domain is artificial intelligence. GCP provides fast, scalable, and easy-to-use AI offerings, including an AI platform, video and image analysis, speech recognition, and multi-language processing. This was about Google Cloud Platform. Now let us move on to the next topic and see what is Google Kubernetes Engine. Google Kubernetes Engine provides a managed environment for deploying, managing, and scaling your containerized application using the Google infrastructure. The GKE environment consists of multiple machines, specifically compute engine instance, which are grouped together to form a cluster. Now a cluster is the foundation of Google Kubernetes Engine. The Kubernetes objects that represent your containerized application all run on top of your cluster. Now to understand GKE better, let us understand its architecture and its working. As you know, all Kubernetes objects that represent your containerized application run on top of a cluster. It is a foundation of GKE. A cluster consists of at least one control plane and multiple worker machines called nodes. These control plane and node machines run on Kubernetes Cluster Orchestration System. The control plane runs the control plane processes, including the Kubernetes API servers, scheduler, and core resource controllers. The control plane is responsible for deciding what runs on each and every node. This can include scheduling workloads like containerized applications and managing the workload's lifecycle, scaling, and upgrades. The control plane also manages network and storage resources for those workloads. Now all the interaction with the clusters are done via Kubernetes API calls. And the control plane runs the Kubernetes API server processes to handle those requests. You can make Kubernetes API calls directly via HTTP/gRPC or indirectly by running commands from the Kubernetes command line client, that is kubectl, or interacting with the UI in the Cloud Console. Now coming to the nodes. Now nodes are the worker machines that run your containerized application, which is your containers and other workloads. They run the services that are necessary to support the containers running in your workloads. Each node is managed from the control plane, which receives update on each node's self-reported status. Next, we have something called the user pods. Now, pods are the most basic and smallest deployment object in Kubernetes. It can contain one or more containers. So now when the pod runs multiple containers, the containers are managed as a single entity, and it shares the pod's resources such as networking and storage. They're connected to various GCP services such as VPC networking, persistent disk, load balancer, and other cloud operations. This was the architecture of GKE. Now let us understand its working. GKE works with containerized applications. These containers, whether for application or batch jobs, are collectively called as workloads. And before you deploy these workloads on GKE, you must first package it into a container. Now to create a continuous integration and continuous delivery pipeline, you can use Cloud Code to write your application, then send the code to a repository which launches a build process in Cloud Build. This build process builds container images from a variety of source code repository. These container images are stored in container registry and are ready to be deployed in the Google Kubernetes Engine. You can then create a GKE cluster using Cloud Console UI, gcloud command line interface, or the APIs. After this, with a few clicks, you can deploy your application on GKE. Now I guess you have some idea about Google Kubernetes Engine. Now let us move on to the next topic and see some of the advantage of Google Kubernetes Engine. With Google Kubernetes Engine, you gain the benefits of advanced cluster management features that Google Cloud provides. First is load balancing for compute engine instance. Google Cloud offers server-side load balancing so you can distribute incoming traffic across multiple virtual machine instances. Load balancer can scale your application, support heavy traffic, detect and automatically remove unhealthy virtual machine instances using health checks, and route traffic to the closest virtual machine. This is a managed service, which means its components are redundant and highly available. So if a load balancing component fails, it is restarted or replaced automatically and immediately. The next benefit is auto scaling. GKE's cluster autoscaler automatically resizes the number of nodes in a given node pool based on the demand of your workloads. You don't need to manually add or remove nodes or over-provision your node pools. Instead, you specify a minimum and maximum size for the node pool, and the rest is automatic. The next benefit is auto-updating. Auto updates will help you keep the nodes in your cluster up to date with the cluster control plane version when your control plane is updated. With auto update, you don't have to manually track and update your nodes when the control plane is updated on your behalf. It also provides better security by automatically ensuring that security updates are applied and kept up to date with the latest Kubernetes features. The next benefit is monitoring and logging. Google Kubernetes Engine includes native integration with cloud monitoring and cloud logging. When you create a GKE cluster running on the Google Cloud, Cloud Operations for GKE is enabled by default and provides a monitoring dashboard specifically tailored for Kubernetes. With Cloud Operations for GKE, you can control whether or not cloud logging collects application logs. You also have the option to disable the cloud monitoring and cloud logging integration altogether. These were some of the benefits of Google Kubernetes Engine. Now let us move on to a demo part and see how to deploy a containerized application on Google Cloud Platform. So in a demo, we are going to package a sample web application into a Docker container image and then run that container image on a GKE cluster. So for that, I've logged in into a GCP account. Now it is very simple to create a new GCP account. All you have to do is enter your debit card or credit card detail and give your address. Then you might be charged maybe ₹1 for it, but even that will be refunded later. Now, as you sign into a new account, GCP will provide you $300 of free credit. You can use this amount to explore Google Cloud services. You won't be charged until you choose to upgrade, and it will be valid for 90 days. So first, let us create a new project. So we'll just go here, select a new project. We can name a project anything we want. So we'll just name it Kubernetes. Let the rest be same and we'll just create it. Now a project is created, we'll just select it. So for our demo, we're going to use Cloud Shell. Now Cloud Shell is an online development and operational environment. It can be accessed from anywhere with the browser. The reason we're using Cloud Shell is we do not have to install any command line tools for a demo. So we'll just click on Activate Cloud Shell over here. Then you can see a Cloud Shell terminal which is being created at the bottom of your screen. So the first step, as I've mentioned before, is to build a container image. For this tutorial, we're going to deploy a sample web application called Hello App, which is a web server written in Go programming language. It responds to all requests with the message Hello World on port 8080. But before we deploy the Hello App to GKE, we must package the Hello App source code as a Docker image, and to do that, we need the source code and the Docker file. Now the Docker file contains information about how the image is built. So first, let us download the source code and Docker file for the Hello App application. Git clone https github.com Google Cloud Platform Kubernetes Engine samples. So the Hello App application is available in this website. So we've just mentioned the website URL over here. Just click on enter. So it says that the directory already exists. So we get a message saying the directory already exists. So we'll just change the directory. Next, we have to set the project ID environment variable to the Google Cloud project ID. You can find the project ID over here. But I guess my project ID is the project ID environment variable. So let's just confirm it. So for that, we'll just type echo $. Next, you have to set project ID environment variable to your Google Cloud project ID. So for that, you have to type export project ID is equal to, you can find your project ID over here. So you can just copy it from here and paste it over here. The project ID variable associates the container image with your project's container registry. Now to confirm a project ID, we'll just type echo $project ID. Here you can see this is the project ID. After confirming the project ID, it is time to build Docker image for the Hello app. So for that, we'll type docker build space -t space gcr.io/$ project ID / hello app version 1. Now this is the name given to a Docker image, and GRE refers to the container registry. Oh, we just forgot one more thing over here. That is space a dot. Now it will ask you to authorize Cloud Shell. You can just select authorize over here. Now you can see a Docker image is being created. We'll just extend this. Now you can see our Docker image was successfully built. Now to just confirm if a Docker image was built, we'll just type Docker images. Now you can see a Docker image is built. It was created a minute ago and the size of it. After this, we have to push our Docker image to the container registry so GKE clusters can download it and run the container image. So for this, we are going to enable the container registry API. We'll just type gcloud services enable container registry dot google apis.com. Next, we have to authenticate to container registry by configuring the Docker command line tool. For that, we are going to type gcloud authenticate configure Docker. Now this is just a warning message saying that we have a lot of credential and it might be slow. So now we have authenticated our container registry. Now we have to push the Docker image to the container registry. So for that, we're going to type docker push the name of our Docker image. Now a Docker image is being built in the container registry. Now you can see a Docker image is pushed to our container registry. Now the next step is to create a Google Kubernetes Engine cluster. So for this, we're just going to minimize it and just go to Kubernetes. You can either select Kubernetes Engine from here, or you can just type Kubernetes over here. Kubernetes Engine. We'll just click on enable over here. Now this might take a couple of seconds. You can scroll down and read an overview about it. You can read about Google and the various other products which are offered by them. Now this is what the Google Kubernetes Engine console would look like. So it will ask us to first create a Kubernetes cluster. So we'll just go ahead and create one. Now we have two options over here. One is standard and the other one is autopilot. In standard, you manage your cluster's underlying infrastructure, which will give you node configuration flexibility. And in autopilot, GKE provisions and manages the cluster's underlying infrastructure. So we'll just go with standard over here and click on configure. So we can name our cluster whatever we want. We'll just name it cluster hello app. You can select any zone from here. These are the available zones. So we'll just select maybe US West one. Now you can select the zone which is nearest to you. You can select the version. We'll just go to static version and just create a cluster. Now creating a cluster might take a couple of minutes. So we'll wait for some time and refresh it to see if it is created or not. You can see there is a green tick over here, which means a cluster is successfully created. We have already pushed the Docker image to a container registry. The next step is deploying the sample application to Google Kubernetes Engine. For this step, you have to create a Kubernetes deployment to run the application on the cluster and also create something called the horizontal pod autoscaler, which scales the number of pods. It can be anywhere from 1 to 5 based on the CPU load. So for that, we'll go to workloads and click on deploy. We have an existing container image, so we'll just select it. Go to select. This is our project ID and this is the name of the Docker image. So we'll just expand it and select this. Our Docker image is selected. We click on continue. Now we have to configure it. So we can name our application anything we want. So we'll just name it demo application. We'll let the namespace be default. Next we have label, which is basically for identification. So we'll let the key be app and the value be demo application. We'll not make any changes in that. And this is our cluster on which the demo application is going to be deployed. Now when we see the YAML, okay, so we have an error here. We cannot use uppercase. So we'll just make it lowercase, demo application. Now when we see the YAML file, you can see two Kubernetes API resources about to be deployed into your clusters. The first one is deployment, and next is the horizontal pod autoscaler. Next, we'll just click on deploy, and our deployment is being created. Now this might take only a couple of seconds. Here you can see the CPU usage, memory usage, and the disk usage, but as of now there is no data available. Now if you go to details, you'll see our cluster name, the namespace which I have mentioned, when was it created and at what time, the labels, how many replicas were made. There were 3 replicas which were made. So after the deployment, we're going to expose the sample application to the internet. So for that, we have an option here called as expose. So we'll just click on this. In the target port, we'll select 8080. Now this is the port the Hello app container listens to, as I had mentioned at the starting of the demo. The service type, let it be load balancer itself. And we can name our service anything we want. Let it be demo application service itself. And we're just going to click on expose over here. Now a new service has been created and it is waiting for a load balancer with an external IP to be created. Now this might also take a couple of seconds. Now a service has been created. So when we go to details, you can see the cluster name, the namespace, when was it created, the label, the pods, the type load balancer, and external endpoint. So we'll just click on this, or you can just copy this and paste it in a new tab. So when we click on this, we are directed to a sample application. So here is a sample web application. Now you see our sample application is exposed to the internet through Kubernetes service. And here is the hello world message with the version and the host name.
Having covered Google Kubernetes Engine in our previous module, we will now explore Kubernetes on AWS to learn about deploying Kubernetes clusters on Amazon Web Services. AWS or Amazon Web Services is one of the most popular global cloud computing platforms. Using AWS, users can host and manage a variety of services on internet using pay-as-you-go model. What I mean by pay-as-you-go model is users have to just pay for the services that they're utilizing on AWS cloud. And various services that Amazon Web Services offers include basic ones such as compute, storage, database, network, and many more. And cutting-edge services like machine learning, analytics, artificial intelligence, IoT, and many more. Amazon Web Services has been frontrunner in cloud computing race for many years now, and it doesn't seem to be slowing down. Officially, it has about more than 1 million customers across multitude of domains. Let's take a look at few of them. To begin with, we have Unilever. It's one of the most popular multinational manufacturer of food, household, and other consumer products. It uses multiple AWS services to support 1,000 plus digital marketing properties. Using these digital marketing properties, it can increase the speed at which marketing campaigns can be made. Other than that, it also uses AWS for backup and disaster recovery as well. Moving on, we have Netflix. You can say that Netflix is one of the most prominent and early user of AWS. Well, after a disaster struck its on-premise data center in year 2008, Netflix migrated its entire architecture to AWS cloud. And since then, Netflix has been using AWS for a variety of features. But mainly, AWS enables Netflix to quickly deploy thousands of servers and terabytes of storage within just few minutes. Next in the list, we have BMW. BMW has built its new car as a sensor service in only 6 months using various AWS services like Amazon S3, Amazon SNS, DynamoDB, Amazon RDS, and Elastic Beanstalk, and many other services. Finally, we have Adobe System. As you know, Adobe is the world's largest maker of multimedia and creative software. It uses AWS to deliver mission critical and multi-terabyte operating environments to its customer. For example, I'm sure you might have heard of Adobe Connect and Flash Media Player and many other services. All these applications are made using various AWS services. Well, these are just few use cases. If you want to know more, maybe you can refer to AWS use cases in AWS documentation. So why do you think AWS customer list is so extensive when there are other popular cloud providers in market? Why do you think AWS is such a hit? Well, it could be due to many reasons. It could be due to the fact that AWS offers scalable, flexible, reliable, and agile environment to its users. Or it could be due to the fact that you can get cost effectiveness while using AWS services. But mostly, it is due to broad range of services that AWS offers across multiple domains. One of its most popular and flagship services include compute services. Under compute services, we have Amazon EC2. It's a primary and flexible service that provide you reasonable cloud compute capacity in form of simple EC2 instances. And then we have AWS Lambda. It's a core serverless computing service. Using AWS Lambda, you can easily build and run application and services without even bothering about underlying infrastructure like network and storage. We also have Amazon ECS. Amazon ECS is nothing but Amazon Elastic Container Service. It's one of the highly scalable and highly performance container management service that supports different kind of containers. And using Amazon ECS, you can easily run application on managed cluster of EC2 instances. Apart from these services, you also have other compute services as well. But as for today's session, we'll be mainly concentrating on Amazon ECS. Then let's proceed. So, what are containers? Before we get into what containers are, you need to understand what a virtual machine is. Virtual machine is a software-based application environment that is installed to simulate the underlying hardware. So to put it simply, virtual machine gives you an illusion that you're running multiple computers on hardware when in reality you're just using one. So basically, virtual machines offer you virtualization. If we take a look at a diagram which you can see on the screen, you can see that at the bottom layer you have host machine or host operating system. This host operating system assigns different resources like RAM and CPU to all the virtual machines. So all these virtual machines share the resources that are available to them. And then there is hypervisor. It acts as an agent between all the virtual machines and your host machine. And finally, sitting on top of hypervisor, we have virtual machine. As you can already see, every virtual machine has its own underlying operating system, has its own binaries and libraries, and an application that it services. Now, talking about containers, at their core, they're very similar to virtual machines, except that instead of virtualizing entire computer like we do in virtual machine, we just virtualize the underlying operating system in containers. So in container technology, a single guest operating system on host machine can run many different creative applications. This makes containers much more efficient, fast, and lightweight when compared to virtual machines. So in simple terms, you can think of running a container like running a virtual machine just without the overhead of spinning up entire operating system. So now you know what containers are. But how do you create one? How do you create a container? Amazon Elastic Container Service for Kubernetes is a managed service which allows users to run Kubernetes on AWS cloud without having to manage underlying Kubernetes control plane. Let's go ahead and take a look at a few other benefits. Like we discussed just now, you don't have to manage any control plane when you're using Amazon EKS service. Amazon EKS runs the Kubernetes management infrastructure across multiple AWS availability zones. So you simply provision worker nodes, you create them, and then connect them to your EKS cluster endpoint. Moving on, infrastructure running on Amazon EKS is secure by default. This is mainly because Amazon EKS sets up secure and encrypted communication channels between your worker nodes and your Kubernetes cluster endpoint. Then applications which are managed by Amazon EKS are fully compatible with those on standard Kubernetes environment. What I mean by that is, you can easily migrate any standard Kubernetes application to Amazon EKS without modifying any code. Just like that, you can transfer from standard Kubernetes environment to AWS Cloud. And finally, AWS actively works with Kubernetes community. It also makes contributions to Kubernetes codebase that helps AWS EKS users to use other AWS services as well. So I hope now you know what Amazon EKS services and what it does. Now let's go ahead and see how it actually works. Just so you know, we'll be following the same set of steps in the demo part of the session as well. So make a note of them. Okay then. Getting started with Amazon Elastic Container Service for Kubernetes is fairly simple. First, you need to create an Amazon EKS cluster. This, you can do it using AWS Management Console or AWS CLI. So once you've created a cluster, you need to create your worker nodes and then add them to the cluster which you created earlier. As for the demo part of the session, we'll be using a CloudFormation template to create and configure worker nodes. So once your cluster is ready and once your worker nodes are there, then you need a tool to access your Kubernetes cluster, right? So this is where you can use Kubectl or Kubefeed or Minikube and many other options. So as for the demo part of the session, we'll be using Kubectl to access Kubernetes cluster. And finally, once the cluster and worker nodes are up and running, you can easily launch your application on Amazon EKS cluster the same way you would do with any other Kubernetes environment. So I hope you have noted down the steps. I hope you have understood what Amazon EKS is and what you do with it. Now let's go ahead and see how to create a cluster and how to create worker nodes and attach them to it and how to launch an application. So I'll be launching a simple JenkinsX application here. So let's get started with the demo. So guys, this is my AWS Management Console. Before we go ahead and create Amazon EKS cluster, there are certain prerequisites. Firstly, we need to create an IAM role. This is mainly to assign permissions to Kubernetes to control resources on your behalf. Secondly, you need to create a VPC and security groups for your cluster to use. So first, let's go ahead and create an IAM role. So I'm going to search for IAM here. Click on IAM. You have roles here. Click on that. And click on create role. Since we're assigning permissions to Kubernetes service, so select EKS here and click on next permissions. As you can see, this role basically follows two policies. You have Amazon EKS cluster policy, which mainly assigns permissions to Kubernetes to manage resources on your behalf. Then you have Amazon EKS service policy. This policy assigns permissions to EKS to create and manage necessary resources to operate your EKS cluster. So now once you've chosen the policies, you can click on review here. Let's give role a name. Let's say EKS role. Since every information is right here, I'm going to click on create role. So the role is now created. Now we'll have to create VPC and security groups. This VPC and security groups are nothing but resources that you use on AWS Cloud. So I can go ahead and create them using a CloudFormation template. Basically, CloudFormation is a service which allows you to use a single text file to manage all your resources that you're using on AWS Cloud. So as you can see, this is my CloudFormation console. And I'm going to click on create stack here. Well, you have an option to create your own template or use a sample one. but I'll be using a new specific URL here. So for that, open Amazon EKS documentation. Click on Get Started here. Okay, when you scroll down, here's the URL. I'm going to copy it and paste it. Well, if you want to know what template actually is, you can go ahead and click on View in Designer here. Basically, it's going to create a VPC and a security group and 3 subnets. Click on Next. We'll have to give stack a name. So let's say EKS service. As you can see, this is the VPC block subnet 1, subnet 2, and subnet 3. Click on Next. So this page is optional. If you want to assign any additional tags, then you can go ahead and do it. Or if you want to assign any IAM role so that cloud confirmation can access your resources on your behalf, then you can go ahead and do that as well. I'm going to leave this page blank and click on Next here. So review URL, right, it's right. And then click on Create Stack here. Well, it's going to take a minute for So as you know, we have used a CloudFormation template here to create VPC and security groups. Well, you can create this on your own as well. You have a service called VPC here. You can go ahead and create VPC using that as well. If you want to know more, then refer to Amazon EKS documentation. It's given properly over there. So bear with me, guys. It's going to take maybe 1 minute. So once we're done with the prerequisites, that's IAM role and VPC, we'll go ahead and create a cluster. So it's created successfully. Now let's go ahead and create a cluster. Before that, click on the stack which you just created. Go for outputs. And maybe you can just copy all this VPC ID, subnet ID, and security groups in a editor so you can refer to them easily. Okay, I'm going to paste it over here. Yeah, it should be fine. Let's go back. Now let's go ahead and create EKS cluster. So when you search for EKS, this is the page where you land. Click on Next Step here. Give a unique name. I'm going to use JenkinsX cluster. Version, it'll take the default current version. And IAM role, as we know, we created one earlier. That should be this, right? Okay, then VPC. Let me go back and check the ID. It says it ends with CB. It's that, and the subnets which are related to VPC have already been specified here. Then security group as well. This one. So once you're sure that you've given correct details, correct VPC and the subnets and security group, click on Create here. So guys, it's going to take a while for the cluster to get created. So let's go ahead and install some software. Like I said earlier, you need a tool to communicate with Kubernetes cluster. We'll be using Kubectl here. So let me show you how to install it. Go back to EKS documentation part. And if you scroll down, it says install Kubectl here. Let me open it in new tab. So depending on the operating system you're using, you can download it. I'm using Windows, so firstly you need to open your PowerShell. Well, you're using curl command to download the software here. I've already downloaded it. Once you've done that, you need to add this binary to your path. And suppose if you have any directory which is already there in the path, and if you've stored this Kubectl.exe file there in that directory, then you know that you don't have to change the path. I've already installed it, so I've created a separate folder called Kubernetes and I've stored Kubectl.exe here. So all you have to do is create a new directory like I did. Copy your Kubectl.exe binary to the new directory. Then you have to edit your path environment variable. That is, you can click on this PC here and right click on properties, add system settings, environment variables, and path. Click on edit here. As you can see, I've already added the path here. So make sure you've made necessary changes in the path. Let me see if the cluster is created. It's still creating. Anyway, in addition to Kubectl, you have to install AWS IAM Authenticator as well. It's basically a tool for using AWS IAM credentials to authenticate a Kubernetes cluster. So let's say you are an admin, you're running a Kubernetes cluster on AWS. So you already need to manage AWS IAM credentials to create and update your cluster. In addition to that, you also need to check if the user is authorized to access your cluster or not. Well, this is a lot of work to do. Instead, you can use AWS IAM Authenticator. This assigns IAM users to some certain role and it determines if a user has access to cluster or not, if he can use or if he can access the cluster or not. So let's see how you can install that. Going back to documentation page, it says to install AWS IAM Authenticator here. Well, again, depending on the operating system you're using, you can just click on the link or you can use curl command on PowerShell to download it. So once you've downloaded, again, you can, for easy access, you can go ahead and store it in the same directory where you've stored your Kubectl.exe binary. As you can see, I have it here. So make sure you install Kubectl and AWS IAM Authenticator properly. Okay, it's taking quite long. So since it's taking long, let's go ahead and check if Kubectl and AWS IAM Authenticator are installed properly or not. So let me go to my Kubernetes folder. There, if it's installed properly, then it should give you an output for this command. I'm just checking the client version here. So since it's giving me output, I'm sure that installation was proper. Same for AWS IAM Authenticator as well. You can give help command. Yeah, well, it's working. Both of them are installed properly. So now let's go back and see if the cluster is created yet. So finally it's created. It usually doesn't take this long, but sometimes it might take. Anyways, now that we've created cluster, we need to make the Kubectl tool which we installed earlier to point to cluster so that we can access the Kubernetes cluster. So let's go back to PowerShell. So we'll be using a command called update kubeconfig. When we use this command, a configuration file will be created by default. If you have created cluster earlier, this config file will be updated. If you haven't, then it will be created. Well, you can configure your tool to point to cluster using AWS CLI, or you can do it using AWS Management Console as well. But I'm using AWS CLI. If you're using AWS CLI, make sure that you've installed the current version of it. Let me check for the version here. And in addition to that, you also make sure that the Python version is above 3 point. Okay, so let's go ahead and use update config command. And I need the name of the cluster. I'm going to copy this and paste it here. it says added new context so and so to config file. Let's go back and check. Localhost and users. I have .cube here. Under that I have config. And when I click on open with, as you can see, a cluster has been added here. So now that the cluster is created, our next step is to create worker nodes. Again, as you know, worker nodes are nothing but EC2 instances. Those are nothing but resources that you use on AWS cloud. So again, I'm using your CloudFormation template to create this worker nodes. Click on CloudFormation or search for CloudFormation. Click on create stack here. Again, I'll be using the URL. Let's go back to EKS documentation, and in the step 3, you have URL. Paste it here. So basically, using this template, we are going to create worker nodes. Again, give your stack a unique name. Let's say JenkinsX cluster worker nodes. One more important thing, guys, here the cluster name should be exact same as the one which you created earlier. Don't make a mistake, otherwise your worker nodes won't be able to connect to the main cluster. So to avoid making that, let me copy the exact name from EKS console. So I'm going to copy this cluster name and paste it here. Now the security groups are the same ones which we created earlier. So this should be it. Let me just check. Yeah. And give your entire node a name. Like 1 is the minimum number of instances that your auto-scale group will create, and 3 is the maximum number of instances or worker nodes. Well, like I said, worker nodes are nothing but EC2 instances, so obviously you'll be needing an Amazon machine image. For that, let's go back to documentation part again, and you have AMI here. Well, make sure to check out in which region you are. I'm in North Virginia region, so I'm using the North Virginia region. So I'm copying this ID. And you'll have to give a key name as well. I've already created one. If you haven't, just go to EC2 services and under networks, let me show you that. So under network and security, you have key pair option. You can go ahead and click on create key pair. Once the key is created, you download the file. Once you've done that, you can see your key here. Well, if you want to assign any additional features, you can do so using Bootstrap arguments. And finally, VPC ID here. And make sure you've selected all the correct subnets. So once you're sure that you've given all the details correctly, click on next option here. Like I said, this page is optional. So if you want to add any tags or assign any IAM role, you can do that here. I'm going to skip this and click on next. Before you go ahead and click on create, just review if you've given correct details like the cluster name and number of nodes, node group, AMI and all that details. And click on this. It says I acknowledge that AWS CloudFormation might create IAM resources on my behalf. And then click on create stack. So guys, it's gonna take a while. Till the stacks gets created, let's go ahead and take a look architecture. So guys, as you know, Amazon EKS is a fully managed service where you can deploy, manage, and scale different type of containers using Kubernetes on AWS. And this EKS service runs control plane across multiple availability zones. So as you can see, I have my EKS control plane here in EKS VPC, and on the other side, I have worker nodes running on my VPC. Now once the worker nodes are created, we have to configure these worker nodes to connect to EKS cluster. For that, we need to make some network changes. Like we need to ingest ENI, that's nothing but Elastic Network Interface. Basically, it's a component of VPC and is managed by EKS control plane. So if your EKS cluster or Kubernetes cluster wants to interact with EC2 nodes or your worker nodes or applications that are running on this worker nodes, then it'll use this Elastic Network Interface to do so. Similarly, suppose your applications or your EC2 worker nodes want to interact with cluster, then they'll be using network load balancer here. So like I said, the architecture is basically very simple. You have your Kubernetes cluster and you have control plane using which you can control your Kubernetes cluster. You have your Kubectl using which you can access your cluster. Then suppose if your cluster wants to communicate to worker nodes, it will be using Elastic Network Interface card. Similarly, if your worker nodes want to communicate with cluster, then they'll be using a network load balancer. So I hope you've understood. Let's go back and see if the stack is created or not yet. So it's not created. So while you guys are waiting for this to get created, maybe you can go ahead and install Kubectl AWS IAM Authenticator and maybe start working with me in parallel. Go ahead and create clusters and all the CloudFormation stacks and all. So once this worker nodes get created, all we do is we connect this worker nodes so that they can start interacting with cluster. As when we add this worker nodes to cluster, then we'll launch a simple JenkinsX application on it. As you can see, the worker nodes are finally created. Let's go back to PowerShell. There's a command called get nodes. It basically lists out all the worker nodes that you've created. It says no resources found because we just created worker nodes. We have not connected them to cluster. So to do that, we use a Kubernetes object of type ConfigMap. So in my text editor, I have a file with .yml extension. As you can see, it's a Kubernetes object of type ConfigMap. Here you can see an ARN. Just now when we created a stack, ARN should have been created as well. So you can click on this and go for output. You'll find a ARN here, copy it and paste it here. I hope I've copied the right one, right? It ends with VA. Yeah. Save it and then store it in the same folder where you've stored your Kubectl.exe file as well. Save and yes. Now, if we try this command again, it's again going to say no resources found because we just created a ConfigMap file. We didn't apply the configuration yet. For that, Kubectl apply -f, your file name. Okay, let me check. Sorry for the mistake. That's the file name. It says config map created. Let me clear the window. Now to check if the configuration was done properly or not, Kubectl get notes. As you can see, notes are properly created and they're attached to cluster properly. Now, so like I said, we created a cluster, we created worker nodes and attached them to cluster. Now all we have to do is we have to launch a simple application on this cluster. So I'm going to launch a simple Nginx application here. For that, I have two files. I have a Kubernetes object of type deployment. Using this, I can launch an application on Kubernetes. So as you can see, it's of type deployment and file name is Nginx. You have something called pods. These are nothing but group of containers. Kubernetes runs containers on EC2 instances and it includes containers and specifications for how they should run and network and storage details and all. So these pods basically contain all that information. So I'm saying deploy 2 pods matching the template. And this is the application name, version, and this is the target port which I'll use when I'm trying to open application on web browser. Now suppose, what if node containing all these pods die? Well, you might lose the copy of your application, right? So to avoid that, you have a Kubernetes object of type service. So this Kubernetes object of type service is an abstraction which defines a logical set of pods running somewhere in your cluster. And all these clusters are provided with same functionality as the ones you've created in your deployment object. So I'm going to go ahead and save this file in the same folder where I've saved ConfigMap as well. So Nginx. Similarly, this as well. Save. Now let's go back to PowerShell. So as you can see, I have both Nginx documentation object and service object as well. Now we just save the files in the folder. We'll have to create an application. For that, we'll be using create command. Create -f and folder name. It says deployment Kubernetes object of type deployment is created. Now same for the service. That is created as well. So if you have to confirm that, then Kubectl get svc or services wide format. So as I said, this is master Kubernetes, which we created earlier, the cluster. And this is the application which we just launched on cluster. So this is the external IP address that we are going to paste it in the browser to take a look at application. But before that, just go ahead and we'll see all the information about this Nginx application using describe command. SVC Nginx. So as you can see, using describe command, when you use describe command, you get all the information about your application. You have type, which is load balancer. You have external IP address. You have target port using which you can open your application. So I'm going to copy this and paste it in my browser. Like I said, target port is 80. Well, there's some error. Give me a minute. Sorry guys, just give me a minute. Yeah. So as you can see, application is successfully launched. So like I said, using Kubernetes on AWS is fairly easy. Let's go through the steps which we went. First, we created a cluster. Before that, there were some prerequisites like IAM role to assign permissions to your Kubernetes cluster, and then VPCs and subnets on which your cluster can work on. Once we've done that, we created a cluster, then we created worker nodes and then configured them so that they're attached to cluster successfully. Once your worker and cluster nodes are up and running, then we launched a simple Nginx application. So just don't stop here. Go ahead and try to create your own cluster and launch your own application on it. With Kubernetes on AWS covered, we will look at Azure Kubernetes services to manage Kubernetes cluster on Microsoft Azure.
Let's try and understand what Azure Kubernetes service is. Now, I'm not going to get into the details of this service right away, but just to give you an introduction, Azure Kubernetes service is a fully managed container management service. It is provided by Microsoft Azure, obviously, which is a very popular cloud service provider. And recent stats also state that it is one of the leading public cloud service providers in the market. So when you talk about Azure Kubernetes, it is basically managed by Microsoft Azure. What it does is it offers serverless continuous integration and deployment experience. Now, what does that mean? What we can do with it? We'll discuss all those things as we get into the details of Azure Kubernetes service. For now, we need to understand quite a few other concepts before we get to that point. But to summarize a few of its benefits, what Azure Kubernetes service does is, what it offers is end-to-end deployment, scalability, and availability. Now, how do these things work? We'll discuss that. But before that, let's try and understand what evolution of software development and deployment is and how it has evolved with time, right? So we all know how applications were built and how they've progressed with time, right? So if you talk about the popular ways in which software development and deployment has evolved, we all think of waterfall model, agile model, and DevOps, which is the current way in which we basically go ahead and deploy applications, right? Or basically not only develop, but also maintain, monitor, and deploy applications, right? So let's try and understand all of these one by one. Let's see how they evolve with time. So when you talk about waterfall model, agile model, or DevOps, they all have these three things, which basically sets them apart, right? The application architecture, be it their deployment or packaging. And finally, the application infrastructure that we can think of. Now, when you talk about the application architecture, the first one, that is your waterfall model, is known for its monolithic architectures, right? Something that we came away from. If you talk about current generation, We are more into the microservices model that is handled by a DevOps, right? So when you talk about waterfall, we had monolithic applications. That means everything was inside a single application. Your servers, right? Your applications, be it your management tools and stuff like that, everything was inside a single application. And these kind of architectures were called as monolithic architectures. Now, with time, we had agile model where we had multi-tier applications where some of your applications or some of the functionalities of your applications were handed over to some other domain or to some other tier, right? And hence we had multiple tiers. Say, for example, you would have your application tier in one place and you'd have your basically your database tier in other place, right? Something like that. And when you talk about DevOps, they took this functionality to a further classified, I would say, architecture where we had microservices or granular parts of your application that could function independently. Now, why do we need these kind of changes, right? Why did we not opt for monolithic applications? Now, when you talk about monolithic applications, these were bulky and these were very rigid, not easy to basically go ahead and modify. If you had to change the entire thing. When you talk about Agile, it gave you more flexibility. How? We had multi-tiers, right? So if one of the tiers is not functioning, right? So we could actually go ahead and work on that tier and it would not affect the remaining functionality. But when you talk about DevOps or when you talk about microservices in particular, it basically breaks down your application into granular chunks where each of these applications performs as a whole, but you can think of them as an individual part, which you can basically go ahead and function or operate on individually, and also ensure that you can basically make changes to these individual parts individually without affecting the functioning of the entire application. Now, when we talk about deployment and packaging, we have different ways in which these applications are hosted, right? Or in which these different ways of software development and deployment work, right? So when you talk about deployment packaging, your waterfall model supported or supports your physical servers, right? You have a physical server. Similarly, when you talk about your DevOps, or rather we have Agile first. So when you talk about Agile, you had your virtual servers. Now, if you talk about cloud computing, yes, to some extent, it supports virtualization, but back in those days, virtual servers were a little different. So if you talk about Agile model, it basically lies on a deployment model which is based on virtual servers. When you talk about microservices, on the other hand, they are more based on containers kind of an deployment is what I would say. Similarly, if you go ahead and discuss their application infrastructure. Now, for your waterfall models, we had data centers that basically had all these applications being hosted, right? Your monolithic applications. Similarly, when you talk about Agile, we mostly move to the hosted platforms, right? And when you talk about current microservices or your container infrastructure, we talk about cloud hosting. And that is why we've come up with this session where we'd be understanding how containers work on top of cloud. That is your Kubernetes orchestration tool. In this case, would be working on our Microsoft Azure cloud platform. So I believe the evolution of development and deployment is clear to you all. Let us now go ahead and understand or discuss some of the other bits that are there on our plate. Now, before we actually go ahead and understand how Kubernetes works, right? And why are we talking about containers and stuff? We need to understand how containers are different from virtual machines, because virtual machines are something that people have been using and many of them have migrated to containers. Why? Because both of them, they have their benefits and reasons for these benefits. So let us try and understand how a container is different from a virtual machine. More than a comparison, it is just understanding how they're different from each other. Now, this image should give you an understanding as to how these two things are different. The one on the left hand side, you have your container, and on the right hand side, you have your virtual machine. Now, when you talk about virtual machine, what a virtual machine does is, on top of your server, it lets you host your guest operating systems. To give you an example, when you talk about a service, right, or if you talk about a cloud platform like Microsoft Azure, where you have Azure virtual machines, which again lets you spawn instances or virtual machines. Now, these virtual machines or instances can have different guest OSs. Say, for example, if you launch a virtual machine that basically has a guest OS of Linux, and there's another virtual machine that has a guest OS of your Windows, right? So we are talking about two different virtual machines or entities which function on the same server, but they have different operating systems. That means if I want an application to run in Windows, I can do that using my VM, that is Windows in nature. And similarly, if I want something to run on top of Linux, I can use the virtual machine that is Linux in nature, right? So that is what virtual machines offer you. Okay. But there's a catch here. When you talk about a virtual machine, you're talking about a server, right? On top of that server, you'd be having your host operating system on which you'd be running a hypervisor. Now, this is more of a middleware, okay? Or a service that supports all the applications that are there on top of it, including the operating system, the guest operating system that we are talking about. Now, here, the problem is, as you can see, the virtual machines that you see on the left-hand side, right? They'll have separate guest OSs, they'll have their bins, and then on top of that, they'll be having the applications that are running. Now, what is the disadvantage here? Here, what happens is, each time you have a virtual machine that is operating, we need to ensure that there's a guest OS there. So there's a dependency on this. And what this does is it makes it difficult for you to basically break this virtual machine from the existing infrastructure or architecture and make it run somewhere else, right? Because this is a complicated process. But when you talk about your containers, this is where the difference lies. Say, for example, I'll be having a Docker engine in this case, right? It can be anything. I mean, when you talk about Docker engine, it is a type of tool that provides you containers, okay? So supports container spawning for you in simple words. There are other container tools as well. We are not here to discuss Docker, but Docker is one of the most popular container tools. That is why you see Docker here. So think of it as your container image, what you see there in the left-hand side. So you can see that there's a server host, you have your hypervisor, you have your guest OS. So guest OS here is common, right? So when you have a guest OS here, what that means is all the containers that would be running on top of it would be running on the same guest OS. So you do not have a dependency where basically you have to ensure that all the guest OS requirements are also there in your container. So your container is more independent of the operating system, right? The only concern here though is in case of containers, you have to ensure that if you have one hypervisor or one Docker engine that is running for you, right? In that Docker engine where there's a single guest OS, in that case, you'll be running all your containers that are supported by that guest OS, right? Now, if my guest OS is Windows, I cannot expect myself to run Linux containers there. I'm just giving you an example, okay? So there's a drawback there. But the benefit here is, right, since your applications, your bins and your library files are independent, you can package them in a container and move them across easily. So you can run it on other Docker engines as well to support your claim. What that does is, since you have this freedom here where you're not dependent on your guest OS, right, or you do not have a guest OS inside your container, you get certain benefits. It makes your containers faster, okay, makes them reliable, and at the same time makes them efficient. So that is what basically containers are, and that is how they're different from virtual machines. So I hope by now the point here is clear to you all, as in how do these things function. Okay, let us now go ahead and understand the other bits. Let us now go ahead and understand Azure Kubernetes Service. Now, to give you a brief about Azure Kubernetes Service, as I've already mentioned, it is a Kubernetes service that is hosted on the Azure cloud platform. Okay, so let me just go back to the slide one and explain that again so that we can go ahead and understand how working of Azure Kubernetes happens. So we've already seen this slide, right? What is Azure Kubernetes service, but now it would make a lot more sense for you. Okay, so what can happen or what Azure Kubernetes service offers to you. Now, if you talk about Azure to start with, it is a popular cloud service provider. What that means is with Azure Kubernetes or with Microsoft Azure, you can basically have various services that help you in software development, planning, management, right? Be it your administrative practices, development practices, or architectural practices related to a software. All these things can be hosted on a public server in this case, which again can be your Microsoft Azure cloud. Now, what it does is it basically gives you all the services that are needed to carry out all the actions that I just mentioned. where you can rent these resources or follow a pay-as-you-go model and use these services to benefit your requirement. Okay. Now, when you talk about a platform like Microsoft Azure, which again is a cloud platform, as I've just mentioned, the possibility of dealing with applications are plenty, or the possibilities rather are plenty. So you can do so many things. So what that does is that gives developers or application owners options to work with these applications in numerous ways. Okay. It simplifies their complications, right? Since if you're talking about a platform like Microsoft Azure, it helps you basically orchestrate quite a lot of activities, be it managing your servers, infrastructure, right? Be it basically load balancing, be it auto scaling, all these things can be controlled by using the cloud platform. So what that does is that gives developers this added benefit, okay, or the application owners this added benefit. And that is why what these cloud platforms are doing these days is they are encroaching or basically covering different domains, be it your big data, DevOps, analytics, right? All these things are or can be implemented using these cloud platforms, because when you talk about these cloud platforms, they're already owning various markets of software development and application hosting. Okay. So that is why having something like Kubernetes work on top of Azure is a benefit. Why? Because some of the complications that you'd find difficult to implement using Kubernetes can be controlled by using Microsoft Azure. And that is why you have these added benefits, be it your end-to-end deployment, be it your availability or scalability. If you talk about some of the benefits that it actually offers, what it does is you pay only for the nodes that you use. That means last time I checked, Microsoft Azure did not charge you for your master node. You only get charged for your worker nodes that you use. Okay. Your cluster upgrades are easier, so you do not have to worry about the patching part and stuff like that. Integration with various Azure and other tools and services becomes easier. Not just that, what you can also do is you can actually go ahead and enforce various rules that are under Azure policy across multiple clusters to have uniformity if you need to, right? What you can also do is you can scale Kubernetes and other nodes using autoscaler that Microsoft Azure supports. And you can even expand your scale even greater by scheduling your containers on Azure containers. So that is what Microsoft Azure Kubernetes service provides you with. Okay. Let us now move further in this Azure Kubernetes service tutorial video, and let's try and understand some of the other important pointers, like how does the architecture of Azure Kubernetes services works. Okay, to understand the working of AKS or Azure Kubernetes service, right? You can see this diagram on the screen. It's a fairly simple diagram and it tells you what Azure Kubernetes service does. Okay, so we've already seen how Azure Kubernetes architecture works, right? I mean, we know what all components it has and stuff like that. This is a more detailed view. So what you'll have is you'll have again a Kubernetes master node or cluster is what you can call it. Okay, so in this master node, the functionality would be same. It would be controlling how the deployment and how the management of your containers work. So basically, Azure will manage your master node. It will basically help you control quite a few activities that are there. As a customer, you'd be managing the applications only. There too, you would have support from Microsoft Azure. How we would understand that? Now, if you talk about the control plane, what you have here is you have your API server. Now, when you talk about your API server, what it does is it basically tells you how the underlying Kubernetes APIs are exposed. Okay. What this component basically does is it provides the interaction for your management tools, be it your Kubectl or the Kubernetes dashboard. Similarly, you have your etcd. Now, etcd basically what it does is it maintains the state of your Kubernetes. When I say the state of Kubernetes, I'm talking about the Kubernetes cluster, and basically it helps you control all the configuration that is there. This thing is highly available and it is key value based in nature. Okay. What you also have here is basically you have a scheduler. What your scheduler does is it lets you create and scale your applications to basically determine which nodes can run on what workload and stuff like that. Okay. And finally, you have your controller manager. Now, this is an important bit again. What it does is it controls or oversees a number of smaller controllers. whether they're performing their actions or not. And what it also helps you in doing is replicating the pods that you have and handling your nodal operations as well. So this is what your control plane does, and it is basically managed by your Azure. Now, what is the benefit of having Azure manage it, right? Since Azure is managing it, you do not have to worry about the configuration part, setting up part, right? Your cluster node is basically set up by Microsoft Azure, and that is what it simplifies. Then the other bit is your customer managed bit, be it your kubelet, right? Kube proxy, your container, and container runtime. To understand this better, I think this diagram should draw a clearer or a better picture for you. Okay. So basically, when you talk about your customer part, now there are quite a few things that you need to know. I've mentioned kubelet, which basically lets you run your pods, right? Your pods are run by your kubelet. That is what your kubelet does. Okay. There are other things as well that you need to know here. You have your Azure Virtual Network Interface. Now, it is something that takes care of all the interface requirements that you might otherwise have. Okay. And similarly, you have your kube proxy, right? Kube proxy again works together with your virtual network interface, right? Or basically your Azure virtual network and tells you what needs to be done. Okay. Now, all these things, they reside on a virtual machine again. So we've discussed all the differences and benefits of it. So what Azure does is it basically launches a virtual machine for you, on top of which your containers would reside. Okay. So when you talk about these containers again, these are nothing but your applications that are running for you. Okay. And these are the services that would help you actually implement or control all these applications that are there. You can actually go ahead and scale up your virtual machines to meet the requirements of your application in different ways. So this is how the working of AKS is. I mean, this is how the master node works, and this is how your basically customer node or your worker nodes work when you talk about AKS. We'll see these as we get into the demo part. But before that, let's go ahead and understand a use case or see a use case as to how vehicle safety with AKS is supported. Now, when we say vehicle safety, we are talking about a use case that was set forth by Bosch. Okay, Bosch, as we all know, is a very popular company which has numerous thousands of employees working across the globe for meeting different technological needs of the world. Okay, in this particular use case, what they thought of was the amount of accidents that happen due to wrong way driving. Okay, and what they thought was, could we find a solution that could basically help us overcome this bit of problem? Okay, so what were the problems that they were facing, right? When you talk about wrong way driving problems, right? What are the issues that we face? Okay, because of wrong way driving, there could be a lot of accidents, unplanned casualties and stuff like that. But if I am to avoid wrong way driving using technology, it's a very tedious task. The reason for that is, what I can try and do here is I can basically set up an application that notifies me of wrong way driving, right? But then for that to happen, I have to have a lot of data that is in real time. And when I'm driving, my only way of fetching data is by using cell phones and GPS, right? But then again, there are problems with these things. When you talk about cell phones, they basically function very well in a radius of 5 meters distance when you talk about their operational radius or their limitations when you talk about range on exchanging this data. Okay, so you can transfer data to a larger audiences. We see that through WhatsApp and stuff. But if you talk about GPS kind of data, we are talking about multiple points or multiple data that we are dealing with. And to deal with them parallelly can be a difficult task. So because of that, Bosch felt was that this was an impossible task to deal with. Why? In order to get the last piece of information out of the noisy sensor data can be a problem. And in order to develop a highly scalable and ultra flexible service to process this data in real time can also be a tedious task. What they also figured out was, to solve this problem, they needed this data in real time and in very short duration. If we could do that, we could actually go ahead and save accidents and we could save these wrong way driving incidents. And that is why they decided to work with Microsoft Azure, which was their already supporting partner. What they also did was they ensured that they did go ahead and accommodate Azure Kubernetes service in their infrastructure. What this did was it ensured that Bosch would get repeatable, manageable clusters of containers, And since they work in such shorter durations, do not have latencies in minutes, but rather in seconds, they offered a simple form of services for them to work with. And what that ensured was they had the average time to calculate whether a driver is going the wrong way or not in milliseconds. So around 60 milliseconds they could figure out. That is around a second where they could figure out whether a driver was in the wrong way or not. And that is what basically your Azure Kubernetes service enabled them to do. Their major problem, that is they had the time constraint, that is something it helped them solve. And because of that, they could come up with this wrong way driving problem solution where they basically use Microsoft Azure to host their data and basically Azure Kubernetes service to basically help them in simple provisioning, scaling of applications, and ensuring that the real-time data is made available to the drivers within a span of 60 milliseconds, which again is a big achievement. So that is what AKS or Azure Kubernetes service had to offer. If you go to Microsoft Azure's website, there's so many good use cases that talk about AKS. So you might want to go ahead and take a look at that as well. As far as the session goes, we'd go ahead and take a look at the demo and understand how we can actually go ahead and set up an Azure Kubernetes cluster and a lot more. Okay, so guys, let's go ahead and get into the demo part now. This is how the Azure portal looks like. Okay, I've signed into the Azure portal. Now for people who are new to Microsoft Azure, what Microsoft Azure does is it gives you an Azure portal where you can implement all the cloud related activities that concern Microsoft Azure. Okay, so if you want to practice from scratch, it also offers a free tier account where you have a number of services available free of cost. Okay, or rather in case of Azure, it works differently. For AWS, you have those free services. With Azure, you have this $200 of credit that it gives you. So you can spend those $200 on creating resources for 11 months duration. Post that, those will expire. So if you do not have an account, you can just go ahead and create a free tier account, fill in the details, right? And you should have this free Azure portal for your usage. Okay. In my case, this is a paid account. This is the company's account. So it's called as pay as you go in my case. In your case, it would be a free tier account, but the functionality would be similar for you as well. The only thing is with the paid account, you have more services available to you, and even the larger instances is something that you can actually go ahead and spawn and use because you're paying for those, right? Under free tier, you don't have to worry about paying for them, right? So there are certain restrictions and limits there. So do go ahead and register to Microsoft Azure's portal. Okay. Now coming back to the demo part, what we are going to do now is we are going to create a Kubernetes cluster. And on top of that, we are going to deploy an application. And the application would be a basic pre-built app by Microsoft Azure. We are not going to create a new app. I'll be sharing the code for the application, so do not worry about that. So we are just going to go ahead and use that pre-built code, and we are going to deploy that code on top of Kubernetes cluster that we have. Okay. So the main thing to note here is we have to see how easily the cluster is created. We are not concerned about the orchestration process at all here. Everything is taken care by your Microsoft Azure, and that is what we are going to look into. So let's not waste any time. Just quickly go ahead and get an instance in place, rather a cluster in place. Okay. So to do that, we are going to click on this icon and say create a resource. Okay. Here you can see all the service domains that are there for offering. So I'm going to click on the containers one and click on Kubernetes service. Once you do that, you see you'll be brought to this page and you'll get all the details, right? AKS manages your hosted Kubernetes environment, making it quick and easy for you to manage containerized applications. The main point is without having to container orchestrate or have any expertise in that. Okay. It eliminates the burden of ongoing operations and maintaining, provisioning, upgrading, scaling your resources rather, which happens on demand here. So you don't have to worry about those things. So let's just go ahead and create a resource group. So for people who do not know what resource groups are, resource group is nothing but you can think of it as a small container or a folder where you put forth all the necessary things that are important for your resource to work. Now, in this case, our resource is Kubernetes. So quite a few other nitty-gritties related to it would be in the resource group. Okay. So let's just go ahead and create one. So I'm going to click on create new. Let's just say we have RG for demo. I'm going to give a simple name so that I can remember that. Okay. So I'm going to say, okay, I'm going to create a cluster. I'm going to call it Kube cluster. Okay. This is enough. So Kube, let's call it Kube cluster. Okay, and this is in place. Where do I want it? If you're using a pay-as-you-go model, there won't be any restrictions here. If you're using free tier, there might be some. Okay, so just select any region that you want to do. I'm gonna randomly select a region now. What region it should be? My region would be, okay, let's pick this one. And it would ask me how many nodes do you want to create. Let's create one. Since it's a very simple demo, we do not need more nodes. Okay, we've discussed what nodes are, right? So that is what we are doing. We are creating a node here where our application would run basically. So I'm gonna say review, or let's just go ahead and see if we have all the settings. Node pools, authentication, you have two options, whether you want your server or rather your cloud platform to manage your identity pools and basically create resources accordingly. You can do that, or you can select a service principal, which is an older way to do it, where you use an Azure Active Directory to do that. So there's no rule here. You can go for this one as well. I'm just going to do this just because I've thought of showing it to you. I selected that. It does not hold a lot of impact on our demo. Okay, just going to say create and review. Okay, so for creating this thing now, it will review all the requirements. If the requirements are in place, what it will do is it will just go ahead and create your cluster and put everything in place. Okay, so it says, do you want to create it now? I'll say yes, create. Okay, let's just refresh and see whether our application is done. It's still deploying. Let's wait for this deployment to get in place, and once it's done, we'll just go ahead and get these things in place. After this, the process is very simple. Okay, we are gonna just go ahead and put in certain set of commands and our job would be done. So you don't have to wait for too long post that. Okay, let's just refresh it again and see whether it's in place. Normally it takes a couple of minutes, so could take longer, right? But it's a very easy deployment process. So let me give you an idea as in what happens when you say that the deployment is happening. So first, your Kubernetes will actually go ahead and launch a Linux instance to start. Okay, so once the Linux instance is in place, that is when we'll actually go ahead and put forth all our resources on top of it. In that Linux instance, we'll set up a cluster, right? All the nitty-gritties that we need, and on top of that cluster, our application would start working. Here in this case, it would probably set up a cache, could be a Redis as well. We'll have to go ahead and look into it, whether it's that one. Okay, and then accordingly, we can go ahead and implement everything on top of that. But we don't have to get into the complications of things. It's a fairly simple process for us. Okay. Okay, let's just go ahead and refresh it once more. Okay, it's done. Your deployment has been complete is what it says. That means we are good to go ahead and use our resource. You can do other things as well on top of it. It is suggesting what all you can do. Okay, so we are going to do one of these things. Do not worry. So just go to the resource in our case. Okay, and in this resource, you can see there's all the information that you need. Okay, you'll get to know where it is hosted and stuff like that, what kind of instance it is, where it is located, everything. One node pool is what you have, right? So you have all the information to actually go ahead and connect to it. So in your case, I'm hopeful that it would happen faster than what you see in my case, or on my screen rather. You see, Cloud Shell is up and running. So let's just go ahead now and basically get credentials, right? Here, let's get the credentials or merge our cluster, okay, so that we can start using it. So how do we do that? We use this command. We say AKS, okay, and in this case, what we are going to do is we are going to say get credentials. Okay, now the next thing is, what do we need? Resource group details. So I'm going to say resource dash group, and I'm going to give the resource group name, which I am certain that we should see if we just scroll up. Okay, so the resource name is RG for demo that we used. Okay, RG for demo. And what we also need is we need the name of the cluster, and in that case it is Kube cluster. So you can do it vice versa as well. You don't have to go this order. You can start by giving in the details for your cluster and then the detail for your resource group. I'm just going to hit the enter button now. Merged Kube cluster as a current context in this path is what it says. Okay. Now let's just go ahead and get the details for the node. In this case, we know there's only one node, but you could be working on multiple nodes, right? So in that case, you have to use this command. You say kubectl. Now it is basically a client-side interactive tool for interacting with your Kubernetes. Okay, so that is what kubectl is all about. Okay, and you say get nodes. If there are multiple nodes, it will give you multiple nodes. If there's only one node, it will give you only one node. So there you go. You can see that there's one node that we have with us. Okay, we have all the details. It's been running for 5 minutes, it says, right? Because that is when we started the node. Okay, now the next thing is we are gonna go ahead and select the YAML file where we've actually put forth the details for our application, right? So how do we do that? For that, we are going to go ahead and use this command. Okay, nano, okay, space Azure. The name of the application is, or the application rather, is related to voting. So that is why I'm going to use this name, and I'm going to say .yaml. Okay. Okay. So guys, I've already pasted a piece of code here because I tried implementing this demo before. So you'll see that there's code here. Okay. So in this case, what we are going to do is we are going to remove this code just to be safe. I'm going to just paste the code again. So basically, this is where you'll have all the details. What is the API that is being used? What is the container port, right? What is the memory that you are using? What call are you making, right? All those details are here. Do not worry, I'll share the link to this piece of code in the description. If not, you can just look for Azure demos or getting started with Azure on your browser and you'll find this piece of code. It's available everywhere. You'll get this code on GitHub as well. I do not own this code, so I will not take any right in saying that this is something that I've created. It is a code that has been used and it is somebody else's work. Okay. So you may check out online the details. I'll also pass in the details in the description. Okay. So everything is removed now. I'm just going to go ahead and paste my piece of code here. Okay. I'm going to say paste, and all the same code is again here with us. Okay. Now, how do I go ahead with it? In this case, I'm going to say justify, cut, uncut. Do I want to replace? I'm just going to say exit for now. So it's Control X in my case. And I'm going to say no, we'll discard the changes. So we'll say yes. So Y. That means it will save my code. Okay. I'm going to hit enter now. So it will take me back to my cluster. Okay. The next step is, now what we are going to do is we are going to go ahead and call out this YAML file. Okay. So once we do that, this is how we are going to do it. We're going to say kubectl again. Okay. And apply /f Azure. What was the name again? /vote dot YAML. I'm going to hit the enter button. And there you go. What it has done is it has created a vote back application. Its front is created, its back is created, right? So we need to see how it looks like, right? So we are going to find out all the details, as in if we want to watch this app working, we need the details for it. So we are just going to go ahead and use a command called as get service. Okay, so get service is in place. And in this case, again, my app name Azure vote, but this time I want the front. Okay, so I'm going to say front and I'm going to say watch and hit the enter button. I basically made a blunder here, and that blunder is we have to call this command through kubectl, right? So in this case, again, we'll have to type the remaining command again. So I'm just going to do it quickly. Okay, get service Azure vote dash front watch. And there you go. You have your external IP here. So guys, at times what you see here, your external IP, if your system is very slow, which is in my case, but I don't know how it happened. Its age is only 85 seconds is what it says. So normally it takes time for you to see this external IP. Okay. But luckily we can see it. So I'm going to just copy it here. Okay. And I'm going to paste it here. And this way we should be able to see the application that we've created. Okay. So you can see you can vote here. One, let me vote for dogs, twice, thrice, and I can just go ahead and reset it as well. Okay. So guys, this is how you actually go ahead and create a cluster. Okay. A suggestion here would be you delete all the resources that is there. Delete this one, delete the resource group, and also the Azure Active Directory so that you do not get charged. If you want to see what all we did here, right, and how the performance went on, Azure lets you track all the working as well, right? If you want to take a look at the insights and stuff, if you click here, you'll have all those details as well. So there you go. If I just refresh it, you should have all the details, right? How long did we use the cluster? This is where the usage started. Okay, so you'll get all these details that you want. So you can do that. So that's it. I believe this demo was clear to you people, and you got to know what things we've worked on, how we've used these things, and how basically your Kubernetes cluster works. Okay, so we've created a simple Kubernetes cluster and explored it. Ensure when you go back, you just delete. Just go to the resources and delete the resource group, the cluster, and the Active Directory, if any.
Next, we will prepare for the Certified Kubernetes Administrator exam with an overview and study tips.
So firstly, let us understand what is the Certified Kubernetes Administrator exam. Now, before starting the CKA exam preparation, it is really essential to know about the exam itself first. The Certified Kubernetes Administrator, that is CKA exam, is the brainchild of the Cloud and Native Computing Foundation in collaboration with the Linux Foundation. Google joined hands with the Linux Foundation way back in July 2015 with the release of Kubernetes version 1.0, and the CNCF was born. Now, the primary objective of the CNCF is the development of sustainable ecosystems using Kubernetes. The CKA exam is a unique initiative by CNCF for expanding a community of organizations that works around a combination of high-quality projects for container orchestration and microservices architecture. Now, the Certified Kubernetes Administrator exam preparation is ideal for testing your skills for the exam. The CKA certification exam aims at bringing standardization to the Kubernetes ecosystem, and the large-scale adoption of Kubernetes makes the exam a worthy investment. However, aspiring candidates should know that the exam will not be as easy as they expect. Rather than putting up multiple choice questions, the exam tests the knowledge of candidates on a very practical level. In addition, the exam follows a very strict curriculum, thereby implying the need for a comprehensive certified Kubernetes administrator training before appearing for the exam. The exam is an online, proctored, performance-based test that really requires solving multiple tasks from a command line running Kubernetes. The Certified Kubernetes Administrator program provides assurance that CKAs have the skills, knowledge, and competency to perform the responsibilities of Kubernetes administrators. Now, the next question that really arises is why the CKA exam? Why not any other exam? Now, the first and the most important benefit of the CKA exam is that it gives you an unfair advantage over a non-certified professional, right? If you are CKA certified, then you definitely have a greater advantage over the people who are not certified. The next benefit is that it gives you better job prospects and higher salary. If you are CKA certified, you'll definitely have a better chance of increasing your salary at work. The next advantage is that since all companies have already or are trying to move toward K8s, that is Kubernetes, it is now or never to write this exam. There are also wide open jobs in the IT fields for CKAs, and it provides you with global recognition for your knowledge, skills, and experience. So I definitely think it is the right time to write this exam and also gain the certification. Let's move ahead and talk about the next important thing, that is the exam overview. Okay, so firstly, the exam is an online proctored-based performance-based test that requires solving multiple tasks from a command line running Kubernetes. I've already discussed this before. The candidates have 2 hours to complete the tasks, but the total duration of the examination is about 3 hours. The exam is based on Kubernetes v1.20. The CKA exam environment will be aligned with the most recent K8's minor version within approximately 4 to 8 weeks of the K8's release date. Based on Kubernetes version 1.17, the CKA exam will test your capabilities across different domains. And also the registration fee for the exam is $300. The exam is available in 3 languages, that is English, Japanese, and simplified Chinese. Now that we know and understood the format, the duration of the exam, its cost, and the various languages that it's available in, so now let's move ahead and understand the target audience for the examination. The target audience for the CKA exam is also a very important concern for certified Kubernetes administrator exam preparation. You really need to know whether you are the right candidate for the exam, or the other way around, whether the exam is right for you or not. Now, the ideal candidates for the CKA exam include any individual who aspires to learn about working with Kubernetes. This certification is for Kubernetes administrators, cloud administrators, and other IT professionals who manage Kubernetes instances. The certification exam, however, is specifically fit for Kubernetes cluster administrators. So if you're any one of this, like a cloud administrator or someone who manages Kubernetes instances and want to skill up, this exam is perfect for you. But this examination is mainly ideal for a Kubernetes cluster administrator. But if you really want to switch careers, or if you want to switch roles in your work, then you can definitely write this exam too as a person who works with Kubernetes. Let's move ahead and talk about the next really important thing, that is the exams curriculum. Now, the preparation of a candidate for the CKA certification exam could improve considerably through a detailed observation of exam objectives. The exam objectives help candidates in driving their preparations in a specific direction. Now, for example, detailed knowledge of the subtopics can really help candidates in finding the right learning materials for preparation. Certified Kubernetes Administrator exam preparation should also focus on the weighting assigned to each exam objective. What this can do is it can help you recognize the importance of each domain in the exam and prepare accordingly. The CKA certification exam emphasizes on testing skills that are highly required in the case of successful Kubernetes administrators. Now, a certified Kubernetes administrator study guide outlines all of the mentioned domains which are essential for your preparation. The study guide can also help you find the subtopics in each domain covered in the CKA exam. Now let us check out the topics and the various subtopics involved in each of these topics in the CKA exam. So the first topic that carries the weightage of almost 25% is cluster architecture, installation, and configuration. So here you'll have to manage role-based access control and learn how to use Kubectl to install a basic cluster. You will also have to learn how to manage a highly available Kubernetes cluster, provision underlying infrastructure to deploy a Kubernetes cluster, and also perform a version upgrade on a Kubernetes cluster using Kubeadm. You will also have to learn to implement etcd backup and restore. Moving on to the next topic, which carries 15% of weightage, is the workloads and scheduling. Here it is important to understand deployments and how to perform rolling update and rollbacks. You will also have to learn config maps and secrets to configure applications, know how to scale applications, understand the primitives used to create robust, self-healing application deployments, and how resource limits can really affect pod scheduling. You must also be aware of manifest management and common templating tools in this particular topic. Moving ahead, with a weightage of 20%, we have services and networking. Here you will have to understand how to host networking configuration on the cluster nodes. You will also need to understand connectivity between pods, cluster IP, node port, load balancer server types, and endpoints. You will have to know how to use Ingress controllers and Ingress resources. Also learn how to configure and use core DNS. Finally, you will learn how to choose an appropriate container network interface plugin. In the next topic, we have storage, which carries the weightage of 10%. In weightage, you must understand different topics like storage classes, persistent volumes, volume mode, access modes, and reclaim policies for volumes. You will also have to work on persistent volume claims primitive and know how to configure applications with persistent storage. Finally, troubleshooting holds the most amount of weightage, that is 30%. Here you will have to evaluate cluster and node logging, understand how to monitor applications, manage a container std out and stdr logs, troubleshoot application failure, cluster component failure, and networking. Now that we've understood the curriculum in detail, let's move ahead and check out the learning path. Firstly, you will have to familiarize with the Linux command line. You will have to know what is Linux and the essentials of it. Candidates here have to master the Linux command line for ensuring that they can master the certified Kubernetes administrator questions. You should practice by using a text editor and remember useful shortcuts. In addition to this, candidates should also learn about the creation and management of system services, also have to learn the basics of Kubernetes, and it would be even better if you would learn the basics of cloud infrastructure technologies. Next important point is that you must be very familiar with the exam. The first requirement for your preparations is the Certified Kubernetes Administrator Study Guide. You can study the guide on the official website of CNCF or the Linux Foundation. You must understand and take a closer look at subtopics covered in each domain and the weight of each domain. This way you can know what you're up against, thereby giving you a competitive edge for your preparations. The next important addition in any certified Kubernetes administrator preparation guide refers to online training courses. Candidates can access the free Introduction to Kubernetes course by the Linux Foundation to understand all key concepts in Kubernetes. In addition, the course Fundamentals of Kubernetes by the Linux Foundation also helps in capitalizing on introductory learning resources to train candidates for requirements of the CKA certification exam. You can also choose popular training providers such as Cloud Native Computing Foundation, Edureka for certified Kubernetes administrator exam preparation. Candidates can get the assurance of guidance by trustworthy and subject matter experts with training courses. Now, the final yet most reasonable advice to prepare for CKA exam is to practice. Always take some time to reflect on what you learn and then implement it in practice. Start with the basics and then move gradually towards the higher levels of a certified Kubernetes administrator preparation guides. With this, let's go ahead and check out the benefits of CKA. Now you may be wondering about the reasons to put so much effort into certified Kubernetes administrator examination preparation. Well, there are a lot of objectives to cover, and you should know that the certification has some benefits to gain confidence. So here are some of the returns that you could get for your efforts in preparing for certified Kubernetes administrator questions. First of all, the CKA certification helps you make your resume unique from the pack. Companies are definitely relying more and more on Kubernetes, thereby giving you a unique opportunity to outperform your competition. Top certifications such as CKA bring exceptional promises for a rise in your salary. Companies are willing to pay more to certified Kubernetes professionals because the certifications validate the abilities of candidates to address all professional responsibilities effectively. Passing the certification exam is a very rewarding experience that can contribute to a personal growth in the very long term. Most important of all, going through a comprehensive certified Kubernetes administrator preparation guide for the exam diversifies your knowledge and skills. So what are some tips to prepare for the exam? Firstly, you must be extremely familiar with Kubernetes documentation portal. You can also access K8's documents during the exam for reference. You can create a bookmark folder to access directly the official documentation. For example, bookmark for pod, bookmark for deployment, etc. Make sure you are comfortable with the official document. You are also allowed to bookmark document pages in your browser and use during the particular exam. Do not access any websites during the exam, and there's only one tab that can be opened. Attempt the questions which have more weightage. Also try to make use of imperative commands rather than creating YAML files manually, as that consumes most of the time during the exam. Also try to make use of allies for the frequently used commands that help save time during the examination. You will also be asked for each question to change the context to change the node. So don't panic then. The command to do this is displayed at the start of each question, that is kubectl config use -context context name. Rather than creating the resources directly, it is definitely better to generate the template and export it to a YAML file. To save time, use short allies for resources, for example, kubectl get ns rather than kubectl get namespaces. These are some of the tips to prepare for the exam. Finally, Kubernetes, as we've already discussed before, we have to train ourselves before we write the exam. Kubernetes training by Edureka is curated by top industry experts. This Kubernetes certification course helps you in clearing the Certified Kubernetes Administrator exam in the first attempt. This interactive Kubernetes certification training is created to help you learn how to set up your own Kubernetes cluster, configure a networking between pods, and secure the cluster against unauthorized access. This Kubernetes training course is live, instructor-led, and helps you master key Kubernetes concepts with hands-on demonstrations. Edureka's Kubernetes training is designed in reference to CNCF's Certified Kubernetes Administrator exam. This Kubernetes certification course will give you an in-depth knowledge of various aspects of the examination, such as Kubernetes core concepts, pod scheduling, Kubernetes networking, logging, monitoring, cluster security, and troubleshooting. This Kubernetes training will also provide you with a set of MCQs, demonstrations, and an exam-level industry-grade project, which will definitely help you prepare for the CKA exam. So what are you waiting for? Enroll now in this Kubernetes certified training and be a certified Kubernetes professional with Edureka.
With exam preparation complete, we will review Kubernetes security best practices to ensure your clusters are secure.
Kubernetes security challenges. Now you can use plenty of non-Kubernetes specific security tools and approaches. You can layer traditional network firewalls and intrusion detection systems. But it is a possibility for you to have an air-gapped deployment. And wherever humans interact with your system, they may constitute a risk to security, either maliciously or just due to human error. Now, there are various ways that an attacker could attempt to compromise your Kubernetes cluster and the applications running on it. So now the diagram that you can see on the screen has some vulnerabilities or security problems and risks that can occur in your Kubernetes cluster. One of them is easy access to the etcd API. Also, the breachers can access via Kubernetes API or proxies. They can intercept or modify or inject control plane traffic. They can also access the machine or VMs as a whole. They can access via Kubelet API and exploit vulnerability in application code. All these vulnerabilities and security risks that I just mentioned can cause a great deal of data loss or information from your organization, and this can eventually cause a huge loss. So to avoid all of these risks that Kubernetes clusters fail, let's move ahead and talk about some of the security principles. The first one is defense in depth. Now picture a medieval castle under siege. Okay, it has strong high walls to keep undesirables or their enemies out, and the wall is surrounded by a moat with access via a drawbridge that is lowered only occasionally to let people in and out. The castle obviously has thick doors and bars across all windows. Archers patrol the castle walls, ready to fire at any attacker. Now the castle has several layers of defense. Attackers who can swim might be prepared to cross the moat, but then they have the walls to scale and the likelihood of being picked off by an archer. It might be possible to compromise any given layer in the defensive structure, but by having several layers, it is really hard for an attacker to successfully enter the castle. This is the same ideology that we will have to apply in Kubernetes. It is preferable to have several layers of defense against attacks on your Kubernetes cluster. Now, if you're relying on a single defensive measure, attackers might find their way around it. The second Kubernetes security principle is the principle of least privilege, that tells us to restrict access so that different components can access only the information and resources they really need to cooperate correctly. Now, in the event of a component being compromised, an attacker can reach only the subset of information and resources available to that component. This limits the blast radius of the attack. Now, let's take an example of an e-commerce store. Okay, let's assume it is built using a microservice architecture with functionality broken into several small discrete components. Now, even if the product and user information is held in the same database, different microservices might each be granted access to only the appropriate parts of that database. A product search microservice needs read-only access to the product tables, but nothing more. Now, if the microservice somehow gets compromised or simply has a bug, the broken service cannot override product information because it has only read access, or even extract user information because it has no access to that data at all. Applying the principle of least privilege means that we make it more difficult for an attacker to cause damage. The same principle can apply to humans too. Now, in some organizations, sharing production credentials with all staff may make sense. In others, it's critical that only a small set of people have access, especially if that access is too sensitive information such as medical or financial records. The third Kubernetes security principles is limiting the attack surface. Now, the attack surface is the set of all possible ways a system can be attacked. The more complex the system, the bigger the attack surface, and therefore the more likely it is that an attacker will find a way in. Consider the castle metaphor again that we discussed previously. The longer the length of the castle walls, the more archers we would need to patrol them efficiently. A circular castle will be most efficient from this point of view. A complicated shape with lots of nooks and crannies would need more archers for the same interior volume. Now, in software systems too, the fundamental way to reduce the attack surface is to minimize the amount of code. So the greater the complexity, the more likely the latent vulnerabilities exist, even in well-tested code. With this, we move on to the main part of today's session, that is, we will be discussing the Kubernetes security practices. In the early days of Kubernetes, the default settings left the control plane insecure in important ways. The situation is further complicated by the fact that different installation tools may configure your deployment in different ways. The default settings now have been improving from a security point of view, but it is well worth checking the configuration you're using. Now we're just going to talk about the configuration settings that are important to get right for the Kubernetes control plane components, and then we'll talk about some tools that can be used to verify the deployed configuration. So the first one is the API server. As its name suggests, the main function of the Kubernetes API server is to offer a REST API for controlling Kubernetes. This is powerful. A user who has full permissions on this API has the equivalent of root access on every machine in the cluster. The command line tool kubectl is a client for this API, making requests of the API server to manage resources and workloads. Anyone who has write access to this Kubernetes API can control the cluster in the same way. By default, the API server will listen on what is rightfully called the insecure port, that is port 8080. Any request to this port bypass authentication and authorization checks. Now, if you leave this port open by mistake, anyone who gains access to the host your master is running on has full control over your entire cluster. So it is important to close the insecure port by setting the API server insecure port flag to 0 and ensuring that the insecure bind address is not set. The next way to secure your cluster is by using Kubelet. The kubelet is the agent on each node that is responsible for interacting with the container runtime to launch pods and report node and pod status and metrics. Now, each kubelet in the cluster also operates an API through which other components ask it to do things like starting and stopping pods. If unauthorized users can access the API on any node to execute code on the cluster, it is possible to gain control of the entire cluster. Fortunately, layers of defense are now available in Kubernetes that make it easy to prevent this kind of attack. Firstly, you can limit the API access to authenticated requests, that is, anonymous requests are ignored. And secondly, you can leverage access control to stop unauthorized actions from being performed. More specifically, there are some configuration options to lock down the kubelets and help minimize the attack surface. That is, you can disable anonymous access with the anonymous authentication is equal to false, or ensure that requests are authorized by setting authorization mode to something other than always allow. You can also limit the permissions of kubelets by including node restriction. Finally, you can set a read-only port is equal to 0 to turn off the read-only port. The next way to secure the cluster is by running etcd carefully. Kubernetes stores configuration and state information in a distributed key value store called etcd. Anyone who can write to etcd can effectively control your Kubernetes cluster. Even just reading the contents of etcd could easily provide helpful hints to a would-be attacker. Therefore, you need to ensure that only authenticated access is permitted. The Kubernetes dashboard has historically been used by attackers to gain control of Kubernetes clusters. It is a powerful tool, and in older versions of Kubernetes, the default settings made it easy to abuse. For example, the dashboard sometimes has full admin privileges by default. You might want to take several steps to ensure that your Kubernetes dashboard is not an easy entry point for attackers, including but not limited to the following, that is to allow only authenticated access, use RBAC, which we will talk about later on in the session. Also make sure the dashboard service account has limited access, and definitely do not expose your dashboard to the public internet. Finally, you can secure your cluster by validating the configuration. Now, once you have set up your Kubernetes cluster, there are two main options for validating whether it is configured safely. These options are configuration testing, where tests validate the deployment against a recommended set of testings, and penetration testing, where tests explore the cluster from the perspective of an attacker. Now that we've discussed the first part of Kubernetes security practices, let's move on to the second way, authentication. Now, if you've been using public cloud offerings such as AWS, Microsoft Azure, or Google Cloud Platform, you might have come across the term identity and access management, which allows you to define access to resources for users and services. Now, all components such as a kubelet running on a node, as well as users issuing kubectl commands, need to communicate with the API server. To process the request, the API server first has to verify who is using the request. The server has to establish the identity of the caller, or in other words, to authenticate the caller. So we'll discuss how authentication in Kubernetes works and the options you have in hand as a cluster operator. The first one is identity. Now, for the API server to authenticate a request, the request issuer needs to possess an identity. At the time of writing, Kubernetes doesn't have a first-class notion of a human user, but rather assumes that users are managed outside Kubernetes via a directory service, such as a lightweight directory access protocol or a single sign-on login standards like security assertion markup language or Kerberos. This is the standard approach in production, but if you are not using such a system, other authentication strategies are available. User accounts are considered cluster-wide, so make sure that the usernames are unique across namespaces. It's obviously not just humans who interact with Kubernetes. We often want a programmatic way for applications to communicate with the Kubernetes API, for example, to query, create, or update resources such as pods, services, or deployments. To that end, Kubernetes has a top-level resource to represent the identity of an application, the service account. Now, a service account is a namespace resource that you can use if your application needs to communicate with the API server. Here, many business applications don't really need to manipulate Kubernetes resources in this way, so they can have the service account with limited permissions. The next one is to know some authentication concepts. Now, the flow Kubernetes uses to authenticate a client's request is by firstly having the client present its credentials to the API server. Then the API server uses one of the configured authentication plugins, and then moving on, the identity provider verifies the request information, including the username and the group membership. Finally, the credentials are in order. The API server now moves on to check permissions. Otherwise, it simply returns an HTTP 401 unauthorized client error status response code, and with that, the request fails. Kubernetes also supports user impersonation. That is, a user can act as another user. For example, a cluster admin, you could use impersonation to debug any authorization issues. Moving on to the next practice, we have authentication strategies. A couple of authentication strategies are available in Kubernetes, represented by authentication plugins. Depending on the size of the deployment, the target users, and organizational policies, you as a cluster admin can choose static password or token files, or even X.509 certificates, OpenID Connect, Bootstrap tokens, authenticating proxies, and also webhook token authentication. Finally, we move on to the last practice, that is tooling. Now, the majority of the effort in the context of authentication is with the Kubernetes cluster administration. You would start off with the existing infrastructure that you need to integrate with, such as an LDPA server your organization already uses to capture team members and group-related information. You also want to take into account the environment the cluster is running in, like a public cloud provider, a managed service, or an on-premises deployment. The latter is important as you may have different options depending on the environment and may end up having more or less work with the authentication bits based on what authentication strategy you go for. Tools like Keycloak, Dex, AWS IAM Authenticator for Kubernetes, Guard, all of these tools really help you with this. So it is a really good practice to work with these tools. Moving on to the next Kubernetes security practices, we have authorization. Now, authorization is assigning permissions to users and applications and in turn enforcing those. Authorization in Kubernetes verifies whether a certain action is allowed by a certain user or application, and if it is allowed, it performs that action or otherwise rejects it and potentially logs the attempt. Firstly, you will have to be aware of some concepts of authorization. Kubernetes authorizes API requests by using the API server, evaluating the request attributes against the policies, and subsequently allowing or denying the request. By default, the permissions are denied unless explicitly allowed by a policy. So I will discuss the authorization flow as we did for the authentication flow. Firstly, the client's request is authenticated. Secondly, if the authentication was successful, the credentials are taken as one input of the authorization module. Thirdly, the second input to the authorization module is a vector containing the request path, resource, verb, and namespace. Finally, if the user or application is permitted to execute a certain action on a certain resource, the request is passed on further to the next component in the chain, the admission controller. Now, if not, the authorization module requests an HTTP 403 forbidden client error status response code, and with that, the request fails. Now that we know how authorization works in principle in Kubernetes, let's look at the ways permissions can be enforced. So we'll be discussing authorization modes. Kubernetes offers multiple ways to enforce permissions, represented by various authorization modes and modules. The first one is node authorization. The second one is attribute-based access control. And the third one is webhook. The next important practice is access control with RBAC. Developed originally at Red Hat in the context of OpenShift, role-based access control was upstreamed to Kubernetes and is stable as of version 1.8 access. You should use RBAC for access control and not use ABAC, or even worse, use none. There are a few parts when dealing with RBAC, like entity, resource, role, and role binding. The actions on a resource that a role uses in its rules are the so-called verbs, such as get, list, create, update, patch, etc. Concerning the roles, we differentiate between two types, cluster-wide and namespace-wide. You will have to figure out what you should use, a role or a cluster role and or role binding. Now let's move on and discuss some of the tools. Okay, there's several tools that focus on authorization with RBAC. Some of them are Audit to RBAC, RBAC Manager, and Kube to IAM. Moving on to the next Kubernetes security practices, we have securing your container images. Now, until now, we've been discussing things mainly from the point of view of a Kubernetes cluster administrator. Moving on, we will switch gears and focus more on developers, operators, or even DevOps teams who really want to deploy code to run on the cluster. So the software that you run in Kubernetes cluster gets there in the form of container images. The first way is to scan and patch container images. Now, to detect vulnerabilities, you need to use a container image scanner. The basic function of a container image scanner is to inspect the packages included in an image and report on any known vulnerabilities included in those packages. At a minimum, this looks at the packages installed through a package manager like YAML or apt packages. Some scanners may also examine files installed at image build time, for example, through ADD, copy, or run operations in a Docker file. Some scanners also report on known malware or the presence of sensitive data like passwords and tokens. Now, to ensure that you're not running vulnerable code in your deployment, You should scan any third-party container images as well as the ones built by your own organization. New vulnerabilities continue to be found in existing software, so it is important to rescan your image on a regular basis. The next one is to patch container images. Once you've identified that you have a container image that includes a package with a vulnerability, you need to update the container to use a fixed version of the package. Please don't be tempted to SSH into your running containers and run something like YUM update or apt get update, as this is an anti-pattern for containers. It quickly becomes unfeasible to manually patch like this when running hundreds of thousands of instances across a cluster. Factor in the self-healing nature of Kubernetes, which ensures that a failed container will be replaced with a new one, and auto-scaling, which can create and destroy containers automatically, and it becomes clear that it's not really possible to keep up with the patching process manually. The key to patching in a container deployment is to rebuild a new container image and then redeploy the containers based on that new image. The build part is typically automated through a continuous integration pipeline, and this may be executed to cover continuous deployment as well. While CI/CD and its bright new cousin GitOps are a part of DevOps, it is worth examining how security tooling fits into the CI/CD pipeline. With this, we reach to the second part, that is CI/CD best practices. Now, image scanning can be integrated in the CI/CD pipeline to automate the process of rejecting images. Many scanners can report a pass or fail for each image, either on basic criteria or more complex custom policies. You can use this fail or pass in several phases in your CI/CD pipeline. That is, a failed scan can result in a failed build, a failed scan before deployment can prevent the image from being deployed, and a failed scan on an image that's already in production can result in an alert so that operators can take remedial action. A good best practice is to use automation to scan all images before they're stored in a container registry, rejecting any images that fail the scan. The next question to consider then is the use of a secure container registry. Several projects aim to help with the problem of ensuring the provenance of the application software running a deployment, like the TUF project. Grafana is another approach to storing and assuring image metadata, and also the In-Toto project provides a framework to protect the integrity of the components installed into an image. And finally, we also have commercial security solutions that can add validations that the image being deployed is a precisely approved version that matches your policies. Finally, the last way to secure your container images is by minimizing images to reduce the attack surface. We already discussed the principle of limiting the attack surface, right? You can take it as a general rule that the smaller the image, the smaller the attack surface. Now, by minimizing the amount of code you include in the image, you can definitely reduce the likelihood of a vulnerability. There is rarely a good reason to include an SSH daemon. Also, along these similar lines, other utilities in your images may not be required by the application code. Excluding them will make the running container less useful to an attacker who manages to compromise it. Let me explain this with an example. Suppose that a container has access to database credentials that it accesses by reading from a secrets file. Now, if the container image does not include utilities like CAT or MORE, it will be much harder for attackers to read the credentials even if they gain access to the running container. Now, if the image doesn't have a shell like sh or bash included in the image, this will make an attack even harder. Taking this idea even further, if your application code can be built as a static binary, you can build an image that contains nothing but that binary. This image will have no utilities that an attacker can take advantage of. As a counterpart, however, consider that by excluding core tooling such as CAT, troubleshooting will also be hard for you, so you want to aim for a sensible trade-off here. Finally, we'll be talking about how to run containers securely. Now that we know how to build container images in a secure manner, we move on to the topic of running those images as containers in Kubernetes. So the first thing that we're going to do is just say no to root. There's little need to run containers at root. There are some exceptions though. If your container needs to modify the host system, for example, modifying the kernel's configuration, you can use it as root. Or if your container needs to bind to privileged ports on the node, then you can be the root. Or even if you're installing software into container at runtime, traditional package management systems might require root to function or store files in a certain location with a different user ID. than the user executing the program. Now, if your container does not fall in any of these categories that I just mentioned, then according to the principle of least privilege, it would make sense to run it as a non-root user. You can do this by including a user command in the Docker file, defining a user identity that the code should run under. Now let's move on and see how the API server enforces policies. Now, when a client submits a request to the API server and that request has been authenticated and the client is authorized to carry out the operation, there is one more step the API server performs before persisting the resource in etcd, that is admission control. A whole slew of admission controls are included in the API server that you, as a cluster admin, can configure. The official docs list explains that more than 30 controllers in great detail. Some relevant ones in the context of running containers securely are always pull images, deny escalating execution, pod security policies, node restriction, limit range, and resource quota. Now let's move on and discuss security boundaries and how to release them. By security boundary, we mean a set of controls to prevent a process from affecting other processes and/or accessing data from other users. From the most outer to the most inner layers of isolation, these boundaries are cluster, node, namespace, pod, and container. Remember that maximizing the defense here requires a joint effort by developers and cluster or namespace admins, since some of the responsibilities fall into the realm of the former and others fall into the realm of the latter. Kubernetes offer 2 pod level security policy mechanism, allowing you to restrict what processes can do within a pod and how pods are allowed to communicate. So here we have security context and policies. A security context defines privilege and access control settings on either the pod or container level. With this, we have discussed all the Kubernetes security practices. Let's move ahead to the case study, cryptocurrency mining. A famous attack on Tesla exploited control plane insecurities to allow hackers to use the company's resources to mine cryptocurrency. Additional research shows other approaches that would-be miners are attempting. Ensuring that only trusted images can run in your cluster would prevent, for example, a bad actor with approved access to the cluster from running an expected mining image. Runtime protection can add another layer of defense to ensure that even if an approved image has a vulnerability that allows code to be injected into a running container, that code definitely cannot be executed. Monitoring for unusual activities such as unexpected CPU usage and unexpected resources being scaled out can help you spot when your resources are being used by an attacker.
Finally, we will go over Kubernetes interview questions to help you prepare for job interviews and demonstrate your expertise.
Kubernetes prerequisite knowledge. So there are 2 important prerequisites that you must be aware with. That is, firstly, you will have to know Linux basics, okay? It is important to learn Linux basic commands that are commonly used when working with containers. And the second one is you will have to be aware of YAML basics, okay? So to acquire the skills that you need to deploy, administrate, and maintain modern cloud technologies, you will definitely need to know a solid amount of prerequisite information on the topic at hand, that is Linux commands and concepts. Since many of the modern cloud technologies leverage the GNU or Linux operating system at their core, it is definitely important for you to know some basics of the Linux command line interface, and it will also allow you to begin with Docker and Kubernetes, and it will also give you a push start to learning Docker and Kubernetes. You can begin with learning how files and directories work, how to change directories with the cd command. You can learn about the absolute path. You can also learn about a relative path and many more topics. The next prerequisite knowledge that you must be aware is of the YAML file. Okay. Now, if you're someone who's been doing software development for a while, particularly with Kubernetes or containers, you have definitely run into a YAML file. YAML is the short form for yet another markup language, which is basically a text format used to specify data related to configuration. So it is really important for you to learn the structure of YAML and the basics of how to write a YAML file. So initially, to start off, you can learn the definition of a YAML file, why developers use YAML, the relationship between YAML and JSON and XML, the basic structure of a YAML file, and finally, how to use a YAML file in Kubernetes. So now that we've discussed some of the prerequisites that we will have to be aware of before we attend a Kubernetes interview, let's move ahead to the next part of this session. Kubernetes basic interview questions. So in the basic interview questions, we'll be discussing 20 questions. And the first question is, what is container orchestration? In modern development, applications are no longer monolithic, but instead are composed of dozens or hundreds of loosely compiled, containerized components that need to work together to allow a given application to function as designed. Container orchestration refers to the process of organizing the work of individual components and application layers. While platforms like Apache, Mesos, Google Kubernetes, and Docker Swarm each have their own specific methodologies for container management, container orchestration engines allows users to control when containers start and stop, group them into clusters, and coordinate all of the processes that compose an application. Container orchestration tools allow users to guide container deployment and automate updates, health monitoring, and failover procedures. So basically, container orchestration refers to the process of organizing the work of individual components and application layers. The second question is, explain the value and benefits of container orchestration. Containers are lightweight and ephemeral by nature. Running them in production can quickly become a massive effort, particularly when paired with microservices, which typically each run in their own containers. A containerized application might translate into operating hundreds or thousands of containers, especially when building and operating any large-scale system. This can introduce significant complexity if managed manually. Container orchestration is what makes that operational complexity manageable for development and operations, or DevOps, because it provides a declarative way of automating much of the work. This makes it a good fit for DevOps teams and culture, which typically strive to operate with much greater speed and agility than traditional software teams. Container orchestration is key to working with containers, and it allows organizations to unlock their full benefits. It also offers its own benefits for a containerized environment, including simplified operations, which is the most important benefit of container orchestration and the main reason for its adoption. Containers introduce a large amount of complexity that can quickly get out of control without container orchestration to manage it. The second benefit is resilience. Container orchestration tools can automatically restart or scale a container or cluster, boosting resilience. The third benefit is added security. Container orchestration's automated approach helps keep containerized applications secure by reducing or eliminating the chance of human error. The third question is, what is the difference between deploying an application on hosts versus containers? Now, the left side architecture represents deploying applications on hosts. So this kind of architecture will have an operating system, and then the operating system will have a kernel which will have various libraries installed on the operating system needed for the application. So in this kind of framework, you can have n number of applications, and all the applications will share the libraries present in that operating system, whereas while deploying applications in containers, the architecture is slightly different. This kind of architecture will have a kernel, and that is the only thing that's going to be common between all the applications. So if there is a particular application which needs Java, then that application will get access to Java. And if there's another application which needs Python, then only that particular application will have access to Python. The individual blocks that you can see on the right side of the diagram are basically containerized, and these are isolated from other applications. So the applications have the necessary libraries and binaries isolated from the rest of the system and cannot be encroached by any other application. Moving on to the fourth question, we have what are Kubernetes or K8s? Kubernetes is an open source container orchestration system for automating computer application deployment, scaling, and management. It was originally designed by Google and is now maintained by the Cloud Native Computing Foundation. Moving on to the fifth and most important question, how is Kubernetes different from Docker Swarm? There are several features that you can compare Kubernetes and Docker Swarm with. The first one is based on its installation and cluster configuration. The setup in Kubernetes is extremely complicated, whereas the setup to install Docker Swarm is extremely easy. Moving on to the second feature, we have graphical user interface. Kubernetes has its own graphical user interface, which is known as Kubernetes dashboard, whereas Docker Swarm has no graphical user interface. The third feature is scalability. Kubernetes is highly scalable. You can scale as much as you'd like to, whereas Docker Swarm scales even faster than Kubernetes. Moving on to the fourth feature, we have auto-scaling. Kubernetes can perform auto-scaling, but Docker Swarm cannot perform auto-scaling. Now moving on to the fifth feature, we have load balancing. Kubernetes expects manual intervention when it comes to load balancing, whereas Docker Swarm has the advantage on this side, that is, it can support auto load balancing. The sixth feature is rolling updates and rollbacks. Kubernetes can deploy rolling updates and does automatic rollbacks, whereas Docker Swarm can deploy rolling updates but not automatic rollback. The comparison for the seventh feature is based on data volumes. Kubernetes can definitely share storage volumes only with the other containers of the same pod, whereas Docker Swarm can share storage volumes with any other container. The last feature that we'll be comparing both of these technologies with is based on logging and monitoring. Kubernetes has some inbuilt tools for logging and monitoring, whereas Docker Swarm has some third-party tools like ELK Stack, which should be used for logging and monitoring. Moving on to the sixth question, we have how is Kubernetes related to Docker? Although Kubernetes and Docker are distinct technologies, they are highly complementary and make a very powerful combination. Docker provides the containerization piece, enabling developers to easily package applications into small isolated containers via the command line. Here, developers can then run those applications across the IT environment without really having to worry about compatibility issues. If an application runs on a single node during testing, it will run anywhere. When demand surges, Kubernetes provides orchestration of Docker containers, scheduling and automatically deploying them across IT environments to ensure high availability. In addition to running containers, Kubernetes provides the benefits of load balancing, self-healing, and automated rollouts and rollbacks. Plus, it has a graphical user interface for ease of use. For companies that really anticipate scaling their infrastructure in the future, it might make sense to use Kubernetes from the very start. And for those already using Docker, Kubernetes make use of existing containers and workloads while taking on the complex issues involved in moving to scale. Moving on to the seventh question, we have what are the features of Kubernetes? There are 4 important features of Kubernetes that I would like to address. The first one is automated scheduling. Kubernetes provides advanced scheduler to launch container on cluster nodes. The second feature is self-healing capabilities, which will allow you to reschedule, replace, and restart the containers which are dead. The third feature is automated rollouts and rollback. Kubernetes supports rollouts and rollbacks for the desired state of the containerized application. The fourth feature is it supports horizontal scaling and load balancing. Kubernetes can scale up and scale down the application as per the requirements. Moving on to the 8th question, we have how does Kubernetes simplify containerized deployment? As a typical application would have a cluster of containers running across multiple hosts, all these containers would definitely need to talk to each other. So to do this, you need something big that would allow load balance, scale, and monitor the containers. Since Kubernetes is cloud agnostic and can run on any public or private providers, it must be your choice to simplify containerized deployment. Moving on to the 9th question, we have what is Google Container Engine? Google Container Engine is a management and orchestration system for Docker container and container clusters that run within Google's public cloud services. Google Container Engine is based on Kubernetes, Google's open source container management system. The 10th question is, what is Heapster? Heapster is a cluster-wide aggregator of data provided by Kubelet running on each node. This container management tool is supported natively on Kubernetes cluster and runs as a pod just like any other pod in the cluster. So it basically discovers all nodes in the cluster and queries usage information from the Kubernetes nodes in the cluster via an on-machine Kubernetes agent. Moving on to the 11th question, we have what is a node in Kubernetes. A node is a worker machine in Kubernetes and may be either a virtual or a physical machine depending on the cluster. Each node is managed by the master. A node can have multiple pods, and the Kubernetes master automatically handles scheduling the pods across the nodes in the cluster. In the next question, we'll understand what is Minikube. Minikube is a tool that lets you run Kubernetes locally. Minikube runs a single node Kubernetes cluster on your personal computer, that is Windows or Mac OS or Linux PCs, so you can try out Kubernetes or for daily development work. So basically, Minikube is a utility that you can use to run Kubernetes on your local machine. Creates a single node cluster contained in a virtual machine. This cluster lets you work on Kubernetes operations without really requiring the time and resource consuming installation of full-blown Kubernetes. In the 13th question, we will address what is kubectl. The Kubernetes command line tool is known as the kubectl, which will allow you to run commands against Kubernetes clusters. You can use kubectl to deploy applications, inspect and manage cluster resources, and even view logs. The 14th question will address what is kubelet. The kubelet is the primary node agent that runs on each node. It can register the node with the API server using one of the host name, a flag to override the host name, or specific logic for a cloud provider. The kubelet works in terms of a pod spec. A pod spec is a YAML or JSON object that really describes a pod. The 15th question addresses what is Kubeadm. Kubeadm is a tool built to provide Kubeadm init and Kubeadm join as best practice fast paths for creating Kubernetes clusters. Kubeadm performs the actions necessary to get a minimum viable cluster up and running. By design, it cares only about bootstrapping, not about provisioning machines. In the 16th questions, we will understand what are daemon sets. A daemon set ensures that all or some nodes run a copy of a pod. As nodes are added to the cluster, pods are added to them. As nodes are removed from the cluster, those pods are garbage collected. The daemon set feature is used to ensure that some or all of your pods are scheduled and running on every single available node. This essentially runs a copy of the desired pod across all the nodes. So when a new node is added to a Kubernetes cluster, a new pod will be added to that newly attached node. In the 17th question, we will understand what is the init container and when can it be used. In Kubernetes, an init container is the one that starts and executes before other containers in the same pod. It is meant to perform initialization logic for the main application hosted on the pod. For example, create the necessary user accounts, perform database migrations, create database schemas, and so on. Init containers can contain utilities or custom code for setup that are not present in an application image. For example, there is no need to make an image from another image just to use a tool like sed, awk, Python, or dig during setup. Moving on to the 18th question, we will understand how to monitor the Kubernetes cluster. There are several tools to monitor the cluster. For example, we could use kubelet. So in a Kubernetes cluster, kubelet acts as a bridge between the master and the nodes. It is the primary node agent that runs on each node and maintains a set of pods. Kubelet watches for pod specs via the Kubernetes API server and collects resource utilization statistics and pod and event status. Kubelet fetches individual container usage statistics from Docker's container advisor, but Kubelet also accepts pod specs provided through different mechanisms and ensures that the containers described in those pod specs are up and running. These aggregated pod resource usage statistics are exposed via a REST API. The second one could be a container advisor, that is a C advisor, which is basically a container resource usage and performance analysis agent. It is integrated into the kubelet binary. C advisor auto-discovers all containers in a machine and collects statistics about memory, network usage, file system, and CPU. C advisor has native support for Docker containers. It does not operate at the pod level but on each node. Be advised, however, C advisor is a simple to use but limited tool. So if you are looking to store metrics for long-term use or perform complex monitoring actions, C advisor will definitely not fit your needs. You can also use the Kubernetes dashboard, which is a web-based user interface add-on for Kubernetes clusters. It has many features that allow users to create and manage workloads as well as do discovery, load balancing, configuration, storage, and monitoring. It is helpful for small clusters and for people starting to learn Kubernetes. This tool offers different views for CPU and memory usage metrics aggregated across all the nodes. It can also be used to monitor the health status of workloads. Installing Kubernetes dashboard is quite easy and can be done using ready-to-use YAML files. Another really important tool that can be used is Prometheus, which is one of the most popular monitoring tools used with Kubernetes. It is community-driven and a member of the Cloud Native Computing Foundation. This project, developed first by SoundCloud and afterward donated to the CNCF, is inspired by Google Bog Monitor. Prometheus stores all its data as a time series. This data can be queried via the PromQL query language and visualized with a built-in expression browser. Since Prometheus is not a dashboard, it relies on Grafana for visualizing data. Version 1.0 of this tool was released in 2016, and it is becoming one of the most used Kubernetes monitoring tools. Other tools from Kubernetes ecosystem, including STO, include a built-in Prometheus adapter that exposes generated metrics. Prometheus can be installed directly as a single binary that you can run on your host or as a Docker container. Running Prometheus on top of Kubernetes can be easily accomplished with the Prometheus operator. We also have KubeWatch, which is basically a Kubernetes watcher that publishes event notification in a Slack channel. This tool allows you to specify the resources you want to monitor. It is written in Golang and uses a Kubernetes client library to interact with the Kubernetes API server. Using a simple YAML file, you can choose the resources to watch, including daemon sets, deployments, pods, replica sets, replication controllers, services, secrets, and configuration maps. Moving on to the 19th question, how to get the central logs from pod. The architecture depends upon the application and many other factors. Some of the common logging patterns are node-level logging agent, streaming sidecar container with the logging agent, export logs directly from the application. In the setup, journal beat and file beat are running as daemon set. Logs collected by these are dumped into the Kafka.Topic, which is eventually dumped to the ELK stack. The same can be achieved using EFK stack and Fluent dbit. The 20th question is, how do we control the resource usage of pod? With the use of limit and request, resource usage of a pod can be controlled. The request could be the number of resources being requested for a container. If a container exceeds its request for resources, it can be throttled back down to its request. The limit is an upper cap on the resources a single container can use. If it tries to exceed this predefined limit, it can be terminated if K8s decides that another container needs these resources. Now, if you are sensitive towards pod restarts, it makes much sense to have the sum of all container resource limits equal to or less than the total resource capacity for your cluster. In the next part of the session, we'll discuss Kubernetes intermediate questions. The first question is, what are the different components of Kubernetes architecture? When you deploy Kubernetes, you get a cluster. A Kubernetes cluster consists of a set of worker machines called nodes that run containerized applications. Every cluster has at least one worker node. The worker node hosts the pods that are the components of the application workload. The control plane manages the worker nodes and the pods in the cluster. In production environments, the control plane usually runs across multiple computers, and a cluster usually runs multiple nodes, providing fault tolerance and high availability. So here the control plane components make global decisions about the cluster, for example, scheduling, as well as detecting and responding to cluster events. For example, starting up a new pod when a deployment's replicas field is unsatisfied. Control plane components can be run on any machine in the cluster. However, for simplicity, setup scripts typically start all control plane components on the same machine and do not run user containers on this machine. Node components, on the other hand, run on every node, maintaining running pods and providing the Kubernetes runtime environment. Moving on to the second question of the intermediate questions, we have, what do you understand by kube proxy? Kube proxy is a network proxy that runs on each node in your cluster, implementing part of the Kubernetes service concept. Kubeproxy maintains network rules on nodes, and these network rules allow network communication to your pods from network sessions inside or outside of your cluster. Kubeproxy uses the operating system packet filtering a layer if there is one and it's available. Otherwise, Kubeproxy forwards the traffic itself. What is the role of Kube API Server and Kube Scheduler? The API Server is a component of the Kubernetes control plane that exposes the Kubernetes API. The API Server is the front end for the Kubernetes control plane. The main implementation of a Kubernetes API Server is Kube API Server. Kube API Server is designed to scale horizontally, that is, it scales by deploying more instances. You can run several instances of Kube API Server and balance traffic between those instances. Kube Scheduler, on the other hand, is the control plane component that watches for newly created pods with no assigned node and selects a node for them to run on. Factors taken into account for scheduling decisions include individual and collective resource requirements, hardware or software or policy constraints, affinity and anti-affinity specifications, data locality, inter-workload interference, and deadlines. Moving on to the fourth question, we have, can you explain Kubernetes Controller Manager and Cloud Controller Manager? Firstly, I will explain Kube Controller Manager. It is a control plane component that runs controller processes. Logically, each controller is a separate process, but to reduce complexity, they are all combined into a single binary and run in a single process. Some types of these controllers are a node controller, which is responsible for noticing and responding when nodes go down. Job controller, which watches for job objects that represent one-off tasks, then creates pods to run those tasks to completion. Moving on, we have endpoints controller, which populates the endpoints object, that is, joins services and pods. Then we have service account and token controllers, which creates default accounts and API access tokens for new namespaces. The Cloud Controller Manager, on the other hand, is a Kubernetes control plane component that embeds cloud-specific control logic. The Cloud Controller Manager lets you link your cluster into your cloud provider's API and separates out the components that interact with that cloud platform from components that only interact with your cluster. The Cloud Controller Manager only runs controllers that are specific to your cloud provider. Now, if you're running Kubernetes on your own premises or in a learning environment inside your PC, the cluster does not have a Cloud Controller Manager. As with the Kube Controller Manager, the Cloud Controller Manager combines several logically independent control loops into a single binary that you run as a single process. You can scale horizontally, that is, run more than one copy to improve performance or to help tolerate failures. So there are some containers that can have cloud provider dependencies. That is node controller. This is for checking the cloud provider to determine if a node has been deleted in the cloud after it stops responding. Route controller for setting up routes in the underlying cloud infrastructure. Service controller for creating, updating, and deleting cloud provider load balancers. Now we have the fifth question, what is etcd? etcd is an open source distributed key value store that serves as the backbone of distributed systems by providing a canonical hub for cluster coordination. It was built specifically for running clusters on Core OS, but works on OS X, Linux, as well as BSD operating systems. etcd is used by many companies in their production system. It is written in Go and uses the Raft consensus algorithm to manage a highly available replicated log. etcd was basically designed to be the backbone of any distributed system, which is why projects like Google Kubernetes, Cloud Foundry, and Fleet rely on etcd. etcd is the primary data store of Kubernetes, storing and replicating all Kubernetes cluster state. So this is used as distributed key value store for Kubernetes, Google's cluster container management. Moving on to the sixth question, we have what are the various K8s services running on nodes and describe the role of each service. Firstly, we have cluster IP, which exposes the service on a cluster internal IP. It makes the service only reachable from within the cluster. This is basically the default service type. Then we have the node port, which exposes the service on each node's IP at a static port. A cluster IP service to which node port service will route is automatically created. The fourth type of service is the load balancer, which exposes the service externally using a cloud provider's load balancer. Services to which the external load balancer will route are automatically created. The last type of service is the external name, which maps the service to the contents of the external name field by returning a CNAME record with its value. No proxying of any kind is set up. Moving on to the seventh question, we have, what do you understand about load balancers in Kubernetes? Load balancing is a critical strategy for maximizing availability and scalability. It is basically the process of distributing network traffic efficiently among multiple backend services. A number of Kubernetes load balancer strategies and algorithms for managing external traffic to pods exist. In the eighth question, we're going to understand what is Ingress network and how does it work. Ingress network is a collection of rules that acts as an entry point to the Kubernetes cluster. This allows inbound connections, which can be configured to give services externally through reachable URLs, load balance traffic, or by offering a name-based virtual hosting. So, Ingress is an API object that manages external access to the services in a cluster, usually by HTTP, and is the most powerful way of exposing service. Now let us understand the working of Ingress network with an example. There are two nodes having the pod and root network namespaces with a Linux bridge. In addition to this, there is also a new virtual Ethernet device called Funnel0, that is network plugin added to the root network. Now suppose we want the packet to run from pod 1 to pod 4. So the packet leaves pod 1's network at Ethernet 0 and enters the root network at VETS 0. Then it is passed to CBR0, which makes the ARP request to find out the destination, and it is found out that nobody on this node has the destination IP address. So the bridge sends the packet to Funnel0 as the node's route table is configured with Funnel0. Now the Funnel daemon talks to the API server of Kubernetes to know all the pod IPs and their respective nodes to create mappings for pods IPs to node IPs. The network plugin wraps this packet in a UDP packet with extra headers, changing the source and destination IPs to their respective nodes, and sends this packet out via Ethernet 0. Now, since the route table already knows how to route traffic between nodes, it sends the packet to the destination node 2. Packet arrives at Ethernet 0 of node 2 and goes back to Funnel 0 to decapsulate and emits it back to the route network namespace. Again, the packet is forwarded to the Linux bridge to make an ARP request to find out the IP address that belongs to VET1. The packet finally crosses the root network and reaches the destination pod 4. Now that we've understood what is Ingress network and how does it work, moving on to the next question, we have, what do you understand from the Cloud Controller Manager? Cloud infrastructure technologies let you run Kubernetes on public, private, and hybrid clouds. Kubernetes believes in automated, API-driven infrastructure without tight coupling between components. The Cloud Controller Manager is a Kubernetes control plane component that embeds cloud-specific control logic. The Cloud Control Manager lets you link your cluster into your cloud provider's API and separates out the components that interact with that cloud platform from components that only interact with your cluster. By decoupling the interoperability logic between Kubernetes and the underlying cloud infrastructure, the Cloud Controller Manager component enables cloud providers to release features at a different pace compared to the main Kubernetes project. The Cloud Controller Manager is structured using a plugin mechanism that allows different cloud providers to integrate their platforms with Kubernetes. The Cloud Controller Manager runs in the control plane as a replicated set of processes. Usually there are containers and pods. Each Cloud Controller Manager implements multiple controllers in a single process. With this, we reach to the 10th question, what is container resource monitoring? As for users, it is really important to understand the performance of the application and resource utilization at all the different abstraction layers. Kubernetes factor the management of the cluster by creating abstraction at different levels like container, pods, services, and the entire cluster. Now, each level can be monitored, and this is nothing but container resource monitoring. The various container resource monitoring tools are Grafana, Heapster, Advisor, InfluxDB, and Prometheus. Grafana is a time series database to store the data captured by all Heapster pods, whereas Heapster gathers data in events from the containers and pods within the cluster. Advisor, on the other hand, is an inbuilt tool in a kubelet that automatically discovers all the active containers and monitors them. InfluxDB is a database that is used along with Heapster for visualizing data within the Kubernetes environment. Prometheus, on the other hand, is a project of CNCF which provides a powerful querying, alerting, and visualization capabilities. Moving on to the 11th question, what is the difference between a replica set and a replication controller? Replica set and replication controller do almost the same thing. Both of them ensure that a specified number of pod replicas are running at a given time. The difference comes with the usage of selectors to replicate pods. Replica set use set-based selectors while replication controllers use equity-based selectors. Now let's discuss about equity-based selectors. This type of selector allows filtering by label key and values. So in layman terms, the equity-based selector will only look for the pods which will have the exact same phrase as that of the label. For example, suppose your label key says app is equal to ngx, then with this selector you can only look for those pods with label app equal to nginx. Selector-based selectors, on the other hand, is a type of selector which allows filtering keys according to a set of values. So in other words, the selector-based selector will look for pods whose labels have been mentioned in the set. For example, say your label key says app in nginx, nps, apache. Then with this selector, if your app is equal to any of nginx, nps, or apache, then the selector will take it as a true result. Moving on to the 12th question, we have what is a headless service? A headless service is a service with a service IP, but instead of load balancing, it will return the IPs of our associated pods. This allows us to interact directly with the pods instead of a proxy. Headless service is similar to that of normal services, but does not have a cluster IP. The service enables you to directly reach out the pods without the need of accessing it through a proxy. Moving on to the 13th question, we have what are the best security measures that you can take while using Kubernetes. Firstly, you can enable role-based access control. You can also use a third-party authentication for API server. You can protect etcd with TLS and firewall. You can also isolate Kubernetes nodes. You can monitor network traffic to limit communications. You can use process whitelisting, turn on audit logging, and also remember to keep Kubernetes version up to date. There is also lockdown kubelet which will allow you to secure your cluster. Moving on to the 14th question, we have what are federated clusters. Multiple Kubernetes clusters can be managed as a single cluster with the help of federated clusters. So you can create multiple Kubernetes clusters within a data center or cloud and use federation to control and manage them all at one place. The federated clusters can achieve this by doing the following things. That is, cross-cluster discovery and sync resources across clusters. Cross-cluster discovery provides the ability to have DNS and load balancer with backend from all the participating clusters, whereas sync resources across clusters keeps the resource sync across multiple clusters to deploy same deployment set across multiple clusters. Moving on to the 15th question, we have what is pod distribution budget. Pod distribution budgets specify the number of concurrent disruptions that you allow for your pods. Disruptions may be caused by deliberate or accidental pod deletion. When a Kubernetes node runs out of RAM or disk space, it will evict pods in an attempt to keep the node running properly. Moving on, we have why use namespaces. What is the problem with using default namespace? Namespaces are intended for use in environments with many users spread across multiple teams or projects. For clusters with a few to 10 of users, you should not need to create or think about namespaces at all. Start using namespaces when you need the features they provide. Namespaces provide a scope for names. Names of resources need to be unique within a namespace, but not across namespaces. Namespaces cannot be nested inside one another, and each Kubernetes resource can only be in one namespace. There are ways to divide cluster resources between multiple users via resource quota. It is not at all necessary to use multiple namespaces to separate slightly different resources, such as different versions of the same software. Use labels to distinguish resources within the same namespace. So while using the default namespace alone, it becomes really hard over time to get an overview of all the applications you can manage in your cluster. Namespaces can make it easier to organize the applications into groups that really make sense, like a namespace of all the monitoring applications and a namespace for all the security applications, etc. In the 17th question, we will understand what is Ingress default backend. Ingress default backend specifies what to do with an incoming request to the Kubernetes cluster that isn't mapped to any backend. That is, what do we do when no rules being defined for the incoming HTTP request if the default backend service is not defined? It is recommended to define it so that users still see some kind of message instead of an unclear error. The default backend is a service which handles all URL paths and hosts the NGINX controller doesn't understand, that is, all the requests that are not mapped with the ingress. Basically, a default backend exposes two URLs, helz that returns 200, that returns 404. In the 18th question, let us understand how to run a pod on a particular node. There are various methods that are able to achieve this. Firstly, we can use node name, which specifies the name of a node in a pod spec configuration. It will try to run the pod on a specific node. Node selector, on the other hand, assigns a specific label to the node which has special resources and use the same label in pod spec so that pod will run only on that node. Node affinities, on the other hand, require during scheduling, ignore during execution, and prefer during scheduling, ignore during execution are hard and soft requirements for running the pod on specific nodes. This will be replacing node selector in the future. That is, it depends on the node labels. Moving on to the 19th question, we have what are the different ways to provide external network connectivity to K8s. By default, pod should be able to reach the external network, but in terms of vice versa, we need to make some changes. There are some options to connect with pod from the outer world. Firstly, we can use a node port, which will expose one port on each node to communicate with it. We can use load balancers, which have L4 layer of TCP IP protocols. We can also use Ingress, which is L7 layer of TCP IP protocol. The last question of the intermediate questions part, we have how can we forward the port 8080 container to 8080 service to 8080 ingress to AT browser, and how can this be done? The ingress is exposing port 80 externally for the browser to access and connecting to a service that listens on 8080. The ingress will listen on port 80 by default. An ingress controller is a pod that receives external traffic and handles the ingress and is configured by an ingress resource. For this, you need to configure the ingress selector, and if no ingress controller select is mentioned, then no ingress controller will manage the ingress. Now let's move ahead and discuss some important Kubernetes MCQs. So the first question is, what is the basic operational unit of Kubernetes? We have pod, task, nodes, and none of the above. So the answer here is pod. Moving on to the second question, we have dash can be considered as the primary data store of Kubernetes. The options are pod, etcd, node, and all of the above. The answer here is etcd. In the third question, we have which of the following ensures containers are running in a pod. The options are pod, etcd, kubelet, and all of the above. Here the answer is kubelet. In the fourth question, we have replication controllers and deployment controllers are a part of dash. Here we have options Kubeadm, API controller manager, master controller manager, and none of the above. The answer here is master controller manager. Moving on to the fifth question, we have who developed Kubernetes? A. Google, B. Apple Incorporation, C. IBM, and D. Microsoft. The answer here is Google. Moving on to the sixth question, we have Kubernetes is a dash platform. The options are portable, extensible, open source, and all of the above. The answer is all of the above. In the seventh question, we have which of the following manages the assigning nodes to pods depending on resource availability. The options are etcd, kubectl, scheduler, and none of the above. The answer here is scheduler. In the eighth question, we have Kubernetes is written in what programming languages? The options are Go, HTML, PHP, and Python. The answer here is Go. In the ninth question, we have to create a new deployment Kubernetes, Use the command dash, that is kubectl run, Kubernetes git deployment, Kubernetes set deployment, and none of the above. The answer here is kubectl run. The last MCQ is, what is the use of Google Kubernetes engine? Option 1 says resize application controllers. Option B says debug container clusters. Option C says update and upgrade container clusters. And D says all of the above. The answer is all of the above. Now let's move on to the last part of the session and talk about Kubernetes certification. Kubernetes training by Edureka is curated by top industry experts. This Kubernetes certification course helps you in clearing the Certified Kubernetes Administrator exam in the first attempt. This interactive Kubernetes certification training is created to help you learn how to set up your own Kubernetes cluster, configure networking between pods, and secure the cluster against unauthorized access. This Kubernetes training course is live, instructor-led, and helps you master key Kubernetes concepts with hands-on demonstration. So what are you waiting for? Enroll now in this Kubernetes certification training and be a certified Kubernetes professional with Edureka. With this, we come to the end of today's session. I hope you had a great time understanding and learning the various questions that can be asked in a Kubernetes interview. If you have any queries, feel free to leave them in the comment section below, and we will get back to you as soon as possible. Until next time, thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!